Hello, Subhashish. Can you hear me? Hello.
Hello.
Subhashish, you can hear me.
Yeah, no, I can hear you. Yeah.
Okay. You want to test your screen or it's okay?
I have already tested, but my talk is the first one, so I
Yes,
can.
you can test it. I have made you a host. You can go ahead and share.
Okay, just a minute.
Hello, am I audible?
Yes or no?
Yes, Anamitra. Hi, can you hear me?
Yeah, I can hear you.
Oh, okay, cool.
Yeah. So Subhashish is just trying his screen out his screen. After
Huh.
that, maybe you can give it a try.
Okay, perfect. Thank you.
Sure. Subhashish, I can
So
see your
is
screen.
it visible? Okay.
Yes. Uh,
Okay, so should I make it a full screen
yes, please.
or presentation? Let's see. Yes, okay.
Yeah, it's okay. I can see it in full screen mode.
Okay, good.
You want to move your cursor if you want to use. I mean, let's see if it's visible. I can see your cursor.
Okay,
Okay, sure. I can see the next slide as well.
okay, thanks.
All right. So, Arnav, you want to give it a try?
Uh,
Shubhashish, can you please unshare for a second?
Yeah, understand. Mhm. Okay, is it?
Yeah, it's gone.
so, should I try?
Yes, Arnav, please
Yeah,
try.
yeah, yeah. So, share screen. Let me just try this. Share. I
Yes, I
think,
can see your screen.
right. So, now let me try the presentation, which is always confusing. Sorry, what is. Presentation. Is this okay?
Yes, it's okay. I can see it in full screen.
And you can see the arrow, right?
I can see your cursor.
Yeah, yeah,
Uh,
yeah.
yeah, I
This,
can see the
this
light
fine?
change.
Okay,
Yeah,
so I'll stop share. Okay.
yeah. Okay,
Yeah.
thank you.
Okay. Thanks.
Saurav Nandi,
Yes, yes.
yeah, so please go ahead and give it a try.
Thanks. Yeah. Let me share screen. Desktop. Just a minute. Huh?
I can see your screen.
Yes. Slideshow. Okay, so you can see the slides. If I change it, you can also see that, right?
Yes, correct. I can
And
move
you
your
can
cursor.
also see my cursor moving
Yes,
around.
yes.
Great. Okay, thanks.
Okay, sure.
So I will stop share.
Thanks.
Yeah, welcome.
Anamitra, just to check, it's 20 plus 5, right?
Yes, it's 20
Okay.
plus 5.
Okay.
Yeah.
Okay. Yeah. And I hope you guys are doing well out there.
Yeah, I hope the same for you guys.
Yeah.
Kolkata,
Yeah.
I
Yeah.
hear from, I hear from Kalpataru that in Kolkata, sort of things are a bit more open. People are
Yeah.
more out on the street than here.
Well, people are more outgoing, but of course, that doesn't mean that
Yeah.
everything is gone. Yeah.
That's the
So,
scary
yeah.
bit.
Yeah. Yeah. Okay.
Sure. Amit is not. Amit probably will join in a bit. And I think Arnab Das is yet to join. So let's wait a bit.
Hello. Hello.
Hello, Amit. We can hear you.
Yeah. Okay. So you can hear me. Good. Uh, so I'm supposed to chair this session. Uh, is anybody there from NICER, Anamitra or others? I mean, I have to know. Uh, okay. Anamitra is there. Anamitra. So, Anamitra, tell me what I need to do the chairing. I mean, what kind of I mean, you will make me some kind of a host or what? Anumitra, you are muted.
Sorry about that. So I have already made you a co-host, and all the speakers of your session will also be made co-host. That I have already done. And
Okay.
I think with Arnab Das, we'll just quickly check his screen. Other people have checked their sort of screen sharing.
Mhm.
And so it's 20 plus 5 minutes. So you basically remind them as usual.
Yeah.
Other than that, much you can of course have the godlike power of muting people.
Okay, I see. I never did that in Zoom. I mean, I don't know even how to do that. So everybody must be happy. I,
Amita, just don't mute the speaker, okay?
Yeah.
okay.
So Arnab Das, you
Well,
are
I will try to keep this in mind.
okay.
Arnab.
Sure.
Uh,
Okay.
so Arnab Das, I have made you a co-host. You can hear me.
So there are three talks with 25 minutes duration, but then there is one with 12 minutes duration.
Yes, 10
Is
plus 2.
that
Yeah,
true?
that is correct.
Okay, 10 plus 2. Okay.
10 plus 2.
Okay, so if all the speakers are there, so when it is for them, I'll try to remind you after about 18 minutes of your 20 minutes time, and then I will say
Yeah.
after 20 minutes that the time is over, and then 25 minutes is gets over. Okay,
So
that's how we
now
will
I can
go.
see your screen. Maybe you can go full screen. Oh, the screen went away. So Arnav is the third. Arnav, you can hear me? I mean, Arnav Das. I know there are two Arnavs in the session. I can see your screen. Maybe say something. I could not hear your audio. Just write to him. Just the chat thing.
Can you hear me?
So, okay. Now
Yes, I can hear you. Yeah.
Yeah.
Maybe you want to go full screen?
That should, whatever. Is it okay now?
Yeah, it's visible. Your cursor is also visible.
Okay, wonderful. Okay, great.
Okay.
So
So fine.
I should stop share now, right?
Yes, yes, please. Thank you. So Shubhashish, you can perhaps keep your thing shared because you're the first speaker. So Amit, should we wait for a couple of minutes because there are only 12 participants so far? So maybe should we wait? It's up to you.
Anything you tell me. You are the boss.
No, you are the one with the godlike powers. So you can.
Just for a little while. You have
Okay.
that all the time during the conference, I think.
I see. Maybe, okay.
So should we start at 9:20 then instead of 9:15?
I think that's fine. If it's okay with everybody and you guys, I think you can shift it by 5 minutes.
Okay, so then let's do that. I mean, if nobody is objecting, but I guess longer delay is probably difficult, right? I mean, because
Because then we will eat in because the break is about 15 minutes. So we might
right.
have to start a bit. Yeah, that's okay. I think 5 to 10 minutes one can adjust.
So 5 or 10, tell me, because I will make my coffee
let's do 5.
accordingly.
Let's do it 5. Yeah.
5 means that already 2 minutes are gone, so 3 more minutes.
Yeah, 3 more minutes. Correct.
Okay.
Hi, Anamitra. How is the whole meeting going?
Hello, Professor Manti. Things are fine. I saw you in the beginning of the first session
Yeah,
of yesterday's.
I only attend the first session because it starts at 8 to 11 here. I'm in California. So
Uh-huh.
by 11 o'clock, 8, 9:30, 10, I quit. Then you go through the all night. Anyway, it's all exciting, very lot of exciting talks. Great.
Sure. This is a nice meeting.
Yeah, good.
Sure. Thanks. So you're not coming to India this time? Hello. Is off. Hi, Ravi. So we're starting in 5 minutes, just because there aren't too many people. What is the time? 1 more minute.
Everybody likes butterflies now.
There's a butterfly here.
There is a butterfly.
Okay. Oh, I see.
You muted?
No. So Amit, maybe we can start. Hello, Amit. Maybe we can start.
Oh, okay. So I muted myself.
Sure.
So okay. So it's a good time to start. Good morning, everybody. On this third day of Young Investigators Meet of this year, which is, as you know already, it's online. It's going great. So today we have in this session four talks. As you probably have seen already in the schedule. So we start with the first one to be presented by Subhasis Sinha from IISER Kolkata, and the title of the talk is "Fingerprint of Chaos and Scars in Kicked Dickey Model: An out of time ordered correlated study." Okay, Subhasis, so please start. And as I was mentioning, that I will give you, I will alert you about the time limit. So please keep your microphone on and
Hello. Hello, can you hear me? Hello.
Yes, you're audible.
Yes, yes. Sorry.
Okay.
Yeah.
Okay, so I thought that my connection was already gone, so there is some problem. Okay. So yeah, I'll just show it.
But your slides are not visible completely.
Yeah, I'll just do it in the presentation mode. Now it is okay? Is it okay?
Yeah, it's fine now.
Okay, so first of all, I thank the organizer for this meeting and also thank Summit for introduction. So so the title of so basically today what I'm going to present is that how to detect the chaos in the kick decay model, but not in the using the standard type of technique, but it's a newly developed technique known as the time or out of time ordered correlators, OTOC typically we call it these days. And so the plan is the following. The first, I'll just give a brief introduction to this subject and the Dickey model. What is the Dickey model and the driven version of this Dickey model, the classical dynamics of the system, then detection of chaos from using this technique, that is the out of time ordered correlators. Then in this context, I'll just briefly mention our previous work on a very disjoint thing, which is a delocalization phenomena in the Andre Aubry model, but there is some connection I just mentioned. That's just a brief connection. And then the dynamical signature of quantum scar in these models, finally summary. So quantum many-body chaos has become a very interesting topic in recent years because of the to understand the ergodic behavior of the quantum system, particularly the closed quantum system, in connection to this thermalization, etc. So typically, the back of our mind, there is always a belief that the chaos plays the important role in phase-space mixing, but there is no such straightforward way to understand chaos in the quantum system because there is no such phase-space trajectories actually. So there is some proposal like the eigenstate thermalization hypothesis to understand the thermalization. And there are also in the quantum system, a certain system which does not at all thermalize, like the many-body localized system, or there are certain states which shows the athermal behavior deviates from the eigenstate thermalization hypothesis. So these are the many-body quantum scar, very new phenomena that is discovered in recent years. So, but there is some this random matrix theory plays a very central role in all these cases. This ergodic behavior of this quantum generic quantum many body system, but it's a very difficult to understand whether there is an underlying chaos in responsible for these types of phenomena in the interacting quantum system. There's some existing tools that like understanding the spectral property of the quantum system and try to see some analogy with the random matrix theory. All these things are available tool, but there is only the very recently the new technique has been used, that is called the out of time ordered correlators to find out not only to detect chaos but to quantify the chaos. So that's the main focus of the present study. So here we'll apply this technique to the a previously introduced model known as the kick-dicky model. So yeah, certain advantage in detecting the chaos. That's why we have used that chosen this model. I'll describe this. So Dickey model was originally introduced to describe the n2-level systems like atoms interacting with a single bosonic mode. So there's a photon mode basically in a cavity. So the atoms are can be modeled just by the two-level systems, which are represented by the sigma z Pauli matrix, and this A dagger, etc. These are the these photon modes, and the interaction term that's given by this, that's a sigma x into A plus A dagger. So it's just give rise to the excitation and de-excitation of the atoms in presence of this photon mode. And if we use the total spin notations, that is the S is total, all these sigma is added up. So then one can consider, one can just describe this model in terms of very large spin of magnitude n by 2, where n is the number of atoms here. So it's basically effectively looks like a large spin interacting with an bosonic mode or an oscillator in that way. And this model is interesting in a sense that it undergoes a quantum phase transition to a super radiant phase. So that's given by this, some original studies have been done where there's a non-vanishing expectation of these photon fields are there, which shows the super radiant, which are the basically super radiant phase. And also the spin shows a change in the orientation, large spin. So this model has become recently very interesting because of the experimental realization with Bose-Einstein condensates, which are placed in the cavity. And this similar to, these are not exactly the same like a Dickey model, but a similar type of model can be constructed out of this Bose-Einstein condensate, which also shows this Dickey-like transition, the super radiant transition, which can be detected by the change in the sort of density structure in the condensate, as well as the photon number in the cavity. So this cavity mode is coupled to the condensate. This way, this can be realized in the experiment. And also, it is interesting in a sense that there's some sort of non-equilibrium transition, etc. and so on. But that's not the main focus of this present work. So we have taken a variant of this model, which we call the kick-dicky model, which is a driven Dickey type model. So Hamiltonian is given by this. So first part is the time independent part, which just describes the which is basically the non-interacting large spin, and the photon modes are there. And the kicking part basically describes the interaction between, there's a periodic kicking, by the way, after time period capital T, there's a kicking term, and the kicking term gives rise to the interaction between the spin and the bosonic part. And this model was actually originally was considered by us in this work. It was done in collaboration with my former student Shayok Ray and my colleague Anandamon Ghosh. But we were that time interested to understand the subsystem thermalization and the connection between chaos, all these things. So main advantage of this model is that we can just write down the, as usual for any periodically driven quantum system, can be described by in terms of the Fluke operator, which are the time evolution operator within the one kicking period or one time period. So the stroboscopic evolution of the wave function can be written in terms of the Fluke operator in this form, f dagger n acting on this I, and the operator evolution also can be given by this equation. That's the advantage. So one can write down the stroboscopic evolution of the operator, and this can be written in a closed form. That is the main advantage of this kick decay model. So we can write down a dynamical map of these operators in this form, where R is of course a very complicated matrix, and the dynamical variables are the three spin component of this large spin. And for the photon modes can be written in terms of the oscillator coordinates, which are the P and Q. Okay, so this is the thing, and this way one can just do the quantum evolution of this system. Okay, the main advantage is that if one uses scaled variables like a spin variable, which is scaled by the magnitude of the spin, which is a large quantity in this case, and Q is a PQ as a another scale variables, which are actually scaled by this square root of S spin magnitude. Then it turns out that all these commutators can be written in terms of an effective H bar or Planck constant, which turns out to be 1 by S. So as S become larger, one can reach the classical limit in this case. So it is very easily one can obtain from this operator dynamical map of the operators, one can get the dynamical map of the classical variable. The classical dynamical maps can be obtained in the limit of S tending to infinity. And one can analyze those dynamical maps to find out the different steady states, and also the fixed point analysis, or how the fixed point become unstable, or whether the phase space become regular or chaotic, all these types of things, and also calculate the Lyapunov exponent to quantify the chaos, all these things. So main important thing that I want to focus on, because there is certain some reason is also there. So we just focus on two trivial fixed point in this map, one which are the north and south pole of the Bloch sphere in the spin space, given by these states, and photon occupancy is basically 0 here. And so these are representing the north and south pole. It turns out that the north pole become unstable at some coupling strength, which is given by lambda Cn, and the south pole turns out to undergo a bifurcation corresponding to lambda Cs. And this bifurcation is also very interesting, because in the limit of this kicking time, when the kicking time tending to 0, then one can just get exactly the effective Hamiltonian in this driven model, and the effective Hamiltonian become nothing but the decay model. So this bifurcation in the dynamical state actually correspond to the quantum phase transition in the decay model, and the original state, that is the south pole, that become dynamically unstable in this case in after this critical coupling strength lambda Cs. And interestingly, this correspond to the super radiant phase, this bifurcated line. But after certain increased kicking strength, this also become unstable. That is the dynamical property. In fact, the system goes to chaotic regime. That's why there is no fixed point, no stable fixed point finally exists. So this is the analysis, classical analysis. So the fixed point structure shows very interesting diagram. It shows the bifurcation. Then again, there is a bifurcation. But the important point is the stable fixed point, stable region of the fixed points. These are reduced very much. And as the kicking strength increase, all these fixed point becomes more or less unstable. And if one can calculate the average Lyapunov exponent in the phase space, then it turns out that it has a growth after certain critical value. Basically, when these trivial fixed points becomes unstable, then this growth will be larger, and it shows the onset of chaos, that which is also visible from the phase portrait. So first top panel actually shows the spin space, the how this phase space trajectories behaves, and bottom this is the oscillator dynamics. So in both cases, we see that when the kicking strength is small, there are regular behavior, and the intermediate kicking strength, there's a mixed phase space structure. So of course, there is a south pole is very much stable, so there's a lot of regular orbits are there. But in the central region or in the near the north pole, this becomes more chaotic. And finally, the system becomes very much chaotic in the large kicking strength. So there's an onset of chaos can be understood from the classical dynamical maps here. And how to diagnose the chaos in the quantum system? There's a standard techniques are available, which are the analyzing the spectral properties of the Fluke eigenphases. So we calculate the eigenphase, and as the Fluke matrix is unitary, so this eigenvalues will look like this: e to the power I phi. These are the eigenphases plays the main role, and these are the eigenvector, Fluke eigenvector phi news. So if one study the spectral statistics or the level spacing distribution of these phi news, then it turns out that it goes from the Poinsot to Wigner-Dyson. It's not exactly GOE, it's basically GUE because it's a unitary. But anyway, it doesn't matter, it's almost same. So it changes from a Poinsot to Wigner-Dyson like statistic, which we have seen there. That's plotted here, the level spacing distribution. For small kicking, it is the regular behavior and Poissonian distribution, whereas in the large kicking, then become the Wigner-Dyson. Also, there is another quantity which quantifies the onset of or shows the onset of chaos, is the ratio between the consecutive level spacing, which is called the R new average. And it turns out that it actually shows a smooth crossover from the Poisson to the GOE limit, and the intermediate limit, there's some sort of mixed phase space type of picture that appears. And if we also study it from the reduced density matrix, if we just these are dynamics basically, if we start with a very localized coherent state kind of wave packet, and in the dynamics after certain kicking, we can sufficient number of kicking, one can find that reduced density matrix in the spin space look like that. When there's an intermediate coupling strength, it shows that there's a tendency to become the diagonal density matrix, which is like a pre-thermalization type of state. And for the large kicking strength, it become more or less diagonal. So that has some connection with the thermalization, etc. That was the original purpose of introducing this model. But now in this work, actually, we want to study this onset of chaos from the alternate measure, that is the using out of time order correlator. So out of time order correlator is defined in this way. There's a in terms of these two operators, which are W and V defined. So this can be it can be chosen accordingly from depending on the system. And typically when it was introduced, people generally considered this thing as a unitary, but there is no need to consider there to be the unitary operator. Here we considered the operator which are not really unitary. But and finally, these commutators have been these commutators are evaluated using the trace over this density matrix. So density choice of density matrix is also depends, like if it is a zero temperature or ground, one can just construct the density matrix from the ground state or some particular state. And in the thermal regime, one can also construct the density matrix from the thermal density matrix, etc. Or here we use the microcanonical density matrix most of these cases. We'll just discuss this. The main advantage of using point of using or introducing these types of correlator is the following: that if one consider a canonically conjugate variables of the system, that's the Q and P, then it turns out that in the semi-classical limit, this commutator of QT and P, that will just become the Poisson bracket, and this can be written as a del qt by del q0, which is a type of a Lupin, meaning which in the chaotic regime is expected to grow as e to the power lambda 2 lambda e to the power lambda t in this case. So if we consider this dagger all this, then it will become this correlator turns out to be something like h effective square into e to the power 2 lambda t, where lambda is expected to be the classical Lupin exponent. So the main idea is that whether from this commutator or from this unequal time correlators, whether one can commutators rather unequal time commutators, if one can extract the Lupin exponent from its growth rate. So typical behavior of these correlators look like this. So there is a initial, there's a region where there's a no growth, almost there is no growth. There's a shorter time scale which is called the diffusion time scale, TS, and after the diffusion, and there's a certain another time scale which is called this Ehrenfest time, TE. There's a exponential growth of this correlator is observed. And this Ehrenfest time is the time where there's the classicality is expected to valid, meaning there is a correspondence between classical and quantum dynamics, which we have studied, that there is certain regime time scale the classical and quantum dynamics matches, and later there will be just deviation. And finally, in this correlated, the interesting part is beyond this Ehrenfest time, there is another regime that comes, which is not really looked into carefully. There is a sort of saturation regime of this correlator. So we'll mainly focus on this new thing is that the saturation regime. In fact, apart from this growth regime, the saturation regime also plays an important role in the onset of chaos. So we'll see that here. Study. So we calculated for this kick-Dickey model, these correlators for the both for this spin space as well as in the oscillator space. So oscillator space, we just do the standard thing, that is a QP commutators. So we expect that in the oscillator space correlators, one can extract the classical Lupin exponent. And this first panel, in the top panel, actually shows this correlator for the correlator for the oscillator variables for different values of kicking strength. So when the kicking strength is very small, so it's a regular regime, and the correlator does not actually increase, it does not grow, it is become very small, and small oscillations are found. And in the intermediate regime, when there's a mixed phase type of behavior obtained, so there's a growth in the oscillator and also the growth in the correlator, and there is some oscillation type of things are present. Whereas in the chaotic regime, there's a really a stiff growth, and then it goes to the saturation type of things in the oscillator. So we have seen that the growth rate does not really capture the Lupin exponent. In the mixed phase space regime, for the intermediate coupling, there is a deviation. So we plotted these red lines are basically the expected behavior of this growth, which is given by this H effective square into 2 lambda t. This is the expected behavior, and we have plotted this thing, this red line. And it turns out in the intermediate regime, there is a
Hi,
deviation.
Subhashis. So
Okay,
sorry to disturb you, but you have finished 19 minutes of your presentation.
Okay,
Okay.
thank you. Thank you. So I'll just try to finish it in 5 minutes. Okay. Okay, so there is a growth rate cannot be captured appropriately, but in the chaotic regime, there is a reasonable agreement with this Lupin exponent. And in the spin regime or spin case, we also see the similar behavior, but interestingly, there is the growth rate does not match with the classical Lupin exponent. However, there is a saturation type of thing. So from this saturation value, it is one can detect the chaos. So we calculated the saturation thing for this spin space using a microcanonical density matrix constructed from the Fluke eigenvectors. And it turns out that this saturation regime actually increases with the increasing kicking strength. And finally, it just saturates at a maximum limit, which is given by some random matrix consideration. If we consider the Fluke matrix in this case like a random matrix, random unitary matrix, then it turns out that also analytically turns out that this saturation value can be written as microcanonical average of the SZ square, which is some in accordance with the eigenstate thermalization hypothesis. And there's some random matrix calculation we have done, which is basically the mixing between the Poissonian and the GOE type of random matrix. And this capture effectively the same behavior which is observed for this kick decay model to understand the onset of chaos in the crossover of this regular to chaotic behavior from the saturation value. Same behavior can be captured from this mixing of these two types of random matrix. And interestingly, this study was initially originally done in the context of a delocalized, to understand the delocalization phenomena in a quasi-periodic potential known as the Andreev potential. Experimentally, it was done by this group of Emmanuel Bloch, etc. So what they have done, they have just have a oscillating type of time periodic quasi-periodic potential, and that shows a many body localized phase can become delocalized by tuning the time period, driving time period. And we analyze this thing. There's a sort of underlying chaos, whether the underlying chaos is responsible or not. That was our main aim. And we studied this with Shayok and Krishnendu in this work. So their first time we have studied the saturation value of the OTOC, and that correctly captures this delocalization phenomena that was originally we have done in 2018. And after that, there are certain works have been done. We have found as a on the saturation value, but somehow our work was not cited by many of us. Many of this work is uncited. So as usual, it's expected that thing, but it's interesting that the saturation value was plays a very crucial role in this case. Also, for detecting the quantum scars, this OTOC also plays an important role. In this case, as I mentioned, there are the South Pole and North Pole, those fixed points become unstable, and they also lead to the scarring, effect of scarring. And we have seen it from the overlap of the Fluke function as well as from the Husserl distribution of these Fluke states, etc. So which shows a peak in the density in the Husserl distribution in the North and South Pole. But interestingly, in the OTOC dynamics, if we scale it with the GOE type of saturation value of the GOE, then it turns out the OTOC dynamics of this starting from this particular region in the phase space where there is a scar, classically the scar can appear, it shows a very slow growth. Whereas the more chaotic regime, if we calculate this OTOC with the more chaotic regime, it shows a very large growth rate. So from looking at the behavior of the OTOC, this can distinguish the scarring effect, scar, and the chaotic regime. So this is, by the way, this is somewhat similar to our previous work of scarring in the Bose-Josephson junction in the pi mode. This North Pole is very similar to that. And sorry, I forgot to mention, probably this work is done with Sudip Sinha, who is my student, and Shayok Ray, my former student, and now he's a postdoc in Germany. So this is we'll submit it soon in this month, this work. So that's it. So the main conclusion is the saturation value of the OTOC that serve as an alternative measure for degree of chaos, and dynamical signature of scars also can be identified from the dynamics of the OTOC. So thank you. Sorry, I've taken probably 1-2 minutes extra.
Okay, so let's thank Suhashish for his presentation. Now we are really pressed for time, but maybe we have time for a quick question. Please, anybody wants to ask a question? So now other day people are saying raise your hand. Where does one raise hand? I don't even know that.
Amita, can I ask a question? This is Shubhro.
Sorry, someone was saying something.
Can I ask a question?
Yeah.
Okay. So the question
Who is this?
that,
Can you please tell your name?
this is Shubhro Bhattacharjee from ICTS.
Oh, Shubhro. Yeah, Shubhro. Yeah.
You showed this. You showed this product state of the photon and the spin. So do you know, I mean, I couldn't catch that. So that's the initial state, and then
actually,
do you know if there is how good is this product state as you evolve it with time?
Yeah, so basically we have done it in the two ways. This when you calculate this OTOC, then there is a density matrix we have to use. So for the local chaos, that what I mean is that for a local phase space point, what is the chaotic? Because since you calculate the Lyapunov exponent, is a local behavior. You start with some point in the phase space, and then you can calculate the Lyapunov exponent. So one can start with this coherent state. This is our this is the classical representation of this phase space behavior. So that can be captured from this two product state of the coherent state. Now, just the product state is not the thing, but the coherent state. So this captured the classicality of this phase space point, and then we extracted the growth rate or etc. And whether this matches with the Lyapunov exponent, that we study. In this.
But how good is this classical representation when you start evolving the state?
Oh, this is, of course. This is this is basically determined by the degree of chaoticity and the Ehrenfest time. So we have in our previous studies we have studied the dynamics, quantum dynamics of these coherent states, etc. So it turns out that coherent state become not really the coherent state; it just become mixed and flat when there is a mixed phase space or chaotic regime. But in the classic, meaning when the chaos is less or the regular regime, this is a good description.
But the photon, but somehow it still remains a product-like, such that the photon state behaves like almost a classical state, and it shows classical chaos.
Yeah, in the classical in the classical chaotic regime, what I mean is that when there is a classical chaotic regime which you analyze from the dynamical maps, there we find that in that regime, if we start with a coherent state, that will no longer will remain as a coherent state. That will become just a very much entangled, and this product state no longer become the product state. So there is all this entanglement. It will be more entangled. But if it is a regular regime, like lambda, when the kicking strength is same small, like 0.3, then this coherent state will, under the dynamical evolution, it still remain like a coherent state, or more or less like coherent state.
Okay, so
thanks.
So I think thanks Subhasis. So because we ran out of time a bit, so let's stop this. I mean, let's take all the other discussions at some other time maybe. But now let us proceed to the second talk. But before that, let's thank Subhasis once more. Okay. Uh, so the next presentation for this session is by Arnab Sen from ISCS, Indian Institute of Cultivation of Science. Arnab is setting up. So the title of his talk is just one second. Yeah, the title of Arnab's talk. Okay, now I can see this on on the screen itself. That is the quantum scars from zero modes in an abelian lattice gauge theory. Arnab, I will alert you after about 18 minutes, 18 to 19 minutes.
Sure,
and
sure.
then 20 minutes is the talk time, and then total
Okay.
time is 25 minutes.
And can you tell me if I'm audible?
Yeah, sure, you are.
Okay, thanks. Okay, so I'll start. So firstly, I'll like to thank the organizers for inviting me to this conference. I have been part of this thing from its inception, and I also thank them for carrying this in this very, very unusual year. Okay, so today I'll talk about some recent work which we have been doing, and part of it has been put up on the archive, in fact, today. So this is the archive reference, and there are many aspects which we still don't understand. So it'll be very nice to have your comments and suggestions. So this work, so I have been doing this work with Devashish Banerjee, who has a joint affiliation in Humboldt and has been also a faculty in the Shah Institute of Nuclear Physics for the past 1.5 years or something like that. And it's quite nice that I finally wrote a paper with him, because we were together in graduate school and we discussed a lot, but we just never wrote a paper. Okay. And I would also like to acknowledge useful discussions with Deeptiman Sen, Krishnendu Sen Gupta, and Uwe Jens Wiese. Okay, so we'll start now. So my job has been made quite easy by Shubhashish's presentation. So I'll sort of breeze through the introduction. So basically, we now know this eigenstate thermalization hypothesis is sort of a super universal thing in the sense that most interacting quantum systems are supposed to follow it. And this ETH, so I'll call this ETH from now on, ETH basically says that the bulk of the eigenstates which are away from the spectral edges, like this and this, are expected to look thermal if you look at local correlation functions or local observables, where when I say thermal, this temperature is essentially determined by the energy of the eigenstate that you're looking at. And there is very reasonable evidence from numerics and also from semi-classics that this is bound to happen in most interacting theories. And this eigenstate thermalization hypothesis, in fact, explains why if you start with a isolated quantum many-body system and you just take some simple high-energy initial state and you just let it evolve under the coherent dynamics of the system. So there is no heat bath connected to it. That's why the dynamics is completely coherent. In fact, even then, the local observables finally, after some time scale, some relaxation time scale, converge to their thermal values, even though there's no heat bath. So this ETH explains that. So then it's equally interesting to ask whether we can violate ETH, right? So because it seems to be such a super universal thing, of course, it's interesting to ask, is there a way out of it? So there are two very well-known routes which sort of tell you how to violate ETH. One of them is integrable systems, where there are lots of hidden conservation laws, and that in fact ensures that not only the low energy states, but in fact, all energy eigenstates have a quasi-particle description, okay? So that's why it violates ETH. And the second example is many-body localization, which happens in interacting theories in one dimensions with strong disorder. And there are some emergent conservation laws which come up, and these are called L-bits. And so in both cases, there is an extensive number of conservation laws which lead to the violation of ETH. So then we can ask a question that what about systems without any disorder, which are non-integrable? So there, can we have violations of ETH? So these are not integrable. So this first option goes out of the window, okay? This integrable system option goes out of the window. And they're translationally invariant, so many-body localization also goes out of the window. So here it has been recently realized that something called weak ergodicity breaking can take place here. Which happens because there are some highly atypical energy eigenstates, which are called quantum many-body scars, which are embedded in an otherwise ETH satisfying spectrum. Okay, and of course, it would have been totally unimportant if there was no way to observe them, because they are just some few states embedded in an exponentially large manifold of states. But then, interestingly, often these quantum scars leave a dynamical signature starting from simple initial states, in the sense that certain simple initial states do not thermalize in such systems, whereas most other initial states do thermalize, okay? So very roughly speaking, the sort of eigenstates can be roughly thought to be factorized into most of the states which are thermal, and some states which are highly anomalous, and they are these scars, okay? Okay, so much of the excitement in this field was generated by an experiment on a system of 51 Rydberg atoms, where experimentally it was shown that certain initial conditions took much longer to relax towards thermal equilibrium than most other initial conditions. So in fact, the authors saw signatures of persistent oscillations starting from a, if you wish, a charge density wave, which is like a 1, 0, 1, 0, 1, 0 kind of a state, where 1 denotes a Rydberg excitation and 0 denotes a Rydberg ground state. So this 1, 0, 1, 0 state kept oscillating between its symmetry partner 0, 1, 0, 1 back to itself with a very non-trivial frequency. And this is highly non-trivial because this is like a Rabi oscillation, but in a many-body Hilbert space. Okay, so it's totally counterintuitive. Whereas if the author started with another high energy state at a similar energy density, which is the so-called Rydberg vacuum, this thermalized very, very rapidly, and it was consistent with ETH. Okay, and it was soon realized that all this happens due to this phenomenon of quantum scars, which was also introduced in the previous talk. So in fact, the model which captures this experiment is quite interesting, but I'll rush through it for lack of time. So it's called this PXP model. But the central thing that I want you to keep in mind is that this model is defined on a one-dimensional line. It has spin half degrees of freedom, and it lives in a constrained Hilbert space. What that means is that you cannot flip the spins independently of each other. That's all it means. So suppose you look at two neighboring sites on your lattice, then a configuration where, so you can think of 0 as -1, okay, so whatever. So these are two directions of the spin half. So, so if you think of neighboring sites, then 0, 0, 1, 0, and 0, 1 are all okay. But 1, 1 is not allowed in your Hilbert space. Okay, so that's why it's a constrained Hilbert space. And then the dynamics of this PXP model is such that if you see something like this in your system where there is a 0 and a 1 and a 0, you just flip this 1 to a 0 and vice versa. So that's the quantum dynamics. And this system actually contains some highly anomalous states, which are called quantum scars. And they are distinguished in particular by their entanglement entropy. So even though they are high energy states and they are therefore expected to follow the volume law in entanglement scaling, they actually follow something completely different, and they have a much lower entanglement. Okay, and it happens that these anomalous states, these scars, actually have a very large overlap with this charge density or this nail state. Okay, and that's why you actually see anomalous dynamics when you start from the nail state, but you don't see anything when you start from this vacuum state, because the scars don't have a high overlap with the vacuum state. So that's the story here. So now we can ask, is there any other scenario where constrained Hilbert spaces are very natural? And the answer is very well known. It's yes. And constrained Hilbert spaces naturally arise in Hamiltonian formulations of lattice gauge theories. This is well known. And I think this was the first instance where this was formulated, but maybe I'm wrong. And the reason the Hilbert space is constrained is because gauge theories need to satisfy appropriate Gauss's law. And that's why the gauge invariant states automatically live in a constrained Hilbert space. In fact, this PXP model, which is a paradigmatic model of quantum scarring in a constrained Hilbert space, can be exactly mapped to something which is a one-dimensional gauge theory. It's called the lattice-Schwinger model, where there is a U1 gauge field which couples to staggered fermions. So this is sort of unimportant. All you just need to remember is that this is some gauge theory where there is both a gauge degree of freedom and a matter degree of freedom. And then this persistent oscillations from the nail state corresponds to something called the string inversion phenomenon in gauge theory. But okay, that's not the focus of this talk. So the question is, what about other gauge theories? And the second question is, in fact, is there some completely new mechanism of scarring which does not happen in the PXP model? So I'll answer both these questions in the affirmative in the next few slides. So let us consider an even simpler gauge theory, one without any dynamical matter. Okay, so this is in fact the simplest possible U1 lattice gauge theory. This is called the quantum link model. I'll just define it quickly for you. So basically, this is another Hamiltonian formulation where the local Hilbert space or the gauge links are represented by spin degrees of freedom. And the minimal spin that you can imagine is spin half. So if you take something else, for example, spin 1, that's also another completely kosher quantum lattice gauge theory. If you take then a large spin limit of this theory, that in fact gives you the well-known classical Wilsonian gauge field theory. Okay, and in fact, such lattice gauge theories are well known in condensed matter. For example, such a gauge theory also comes up in the three-dimensional diamond lattice. If you look at the famous work by Hermele, Fischer, and Balance on a certain quantum spin liquid. Okay, so so basically, these links here, which I have drawn, are the electric fluxes. Okay, So what is the Gauss's law here? The Gauss's law here is if you go to each vertex here, okay, then there is a 2 in, 2 out rule. So for example, if I go here, you can see that this electric flux goes out, this electric flux goes out, but this is coming in and this is coming in. And this is true for the entire lattice. So that's your constraint. That's your Gauss's law, which is your constraint Hilbert space as well. So you cannot take an electric flux and just flip it independently. That's why it's a constrained Hilbert space. So what is the Hamiltonian of this? So I need some gauge invariant local terms to define the Hamiltonian. So there are two very simple terms here. One, so both terms live on elementary plaquettes, which are these square plaquettes. So one term is one term is off diagonal in this electric flux basis. So you take any of these plaquettes where the fluxes go along a certain loop. Maybe that's clockwise, maybe that's anti-clockwise. So for example here, so this goes in a loop. So then if this O kinetic hits this plaquette, then the directionality reverses. Clockwise changes to anti-clockwise and anti-clockwise changes to clockwise. You can easily check that that does not violate the Gauss's law, okay? However, if you act the O kinetic on a plaquette where the fluxes do not go on a loop, okay, for example here, so just follow my cursor. So like this, like this, like this, but then this is not following a loop, then the O kinetic sort of annihilates this flux, okay? And the O potential term does nothing. It just counts the number of total flippable plaquettes. It just counts them, okay? So this is a flippable plaquette, this is a flippable plaquette, but this is not a flippable plaquette. So that's it. And your Hamiltonian is O kinetic plus lambda times O potential, where lambda is some coupling, which will be important for me, okay? So the route for scarring that we'll see here is that what will happen is that in this theory, if you go at lambda equal to 0, okay, so then it's just this O kinetic term. So in this theory, if you go at lambda equal to 0, there is an infinite number. So sorry, not infinite. There's an exponentially large number of exact zero modes. So these are exact zero modes. So meaning that their energy is exactly 0. It's not 10 to the minus 19 or something like that. It's exactly 0. So there are exponentially many exact zero modes at mid spectrum at lambda equal to 0. So you can actually see those states in the density of states here. So this is the numerically obtained density of states for, oh, sorry, I forgot to mention one thing. We are considering this gauge theory on ladders. So for example, I've shown here a 6x4 ladder. The reason we have to consider this theory on a ladder is because there's a pure gauge theory. So I cannot define it on a line. So the minimal thing I can do it is on a ladder of length 2, and then I can go to length 4 and so on and so forth. So I take Lx and Ly to be even, and Lx is not equal to Ly, and there are periodic boundary conditions in both directions, okay? So with these constraints, you can show that at lambda equal to 0, there's an infinite number, there's an exponentially large number of exact zero modes. So what happens is at lambda not equal to 0, and sorry, these exact zero modes, this large number of zero modes are protected by an index theorem. And at lambda not equal to 0, this massive degeneracy is immediately lifted. And the zero modes can mix among themselves and mix with the non-zero modes, so to generate the new eigenstates at a non-zero lambda. But what is special here is that there are some linear combinations of the zero modes which survive. And because these are linear combinations of zero modes, they have to diagonalize O kinetic with an eigenvalue of 0 by definition. But these special linear combinations also diagonalize this other gauge invariant operator O potential, and hence they are eigenstates of the full Hamiltonian. And these special linear combinations would be the quantum scars. And so this is sort of akin to an order by disorder mechanism, which is very well known in geometrically frustrated magnets. But this is happening in the Hilbert space, okay? Okay. So first thing is, why are there so many zero modes at lambda equal to 0? Because you would normally ask, why is there such a crazy degeneracy? So it turns out that this is a mixture of two things. One is that there is a certain operator C, which is defined by the product of electric fluxes along, along horizontal bonds, if you wish, like this, but on alternate horizontal bonds. So let's say just the even guys. So here, here, and so on. Okay. So then if you take a product of all these operators, you can easily show that this, sorry, I'm rushing through things. So you can see that this C anti-commutes with your Hamiltonian, which actually ensures that for every energy state at energy E, there is its partner, which has energy minus E. Okay. So that's statement number one. So the spectrum is symmetric.
Okay, so Arnab, you have spent 18 minutes.
Oh, I see.
responding to
I'll
that.
try to quickly wrap up. Thanks. So the spectrum is completely symmetric about E equal to 0 because of this constraint. But what is also furthermore the interesting thing is that this Hamiltonian also commutes with certain space reflection symmetries, as I have indicated here. Okay. And the third important thing is that this space reflection symmetry, which is a point group symmetry, commutes with this C, which is some kind of a chiral symmetry in some way, if you think of it. Okay. So if these three things happen together, then actually there's some remarkable work which shows that there must be an infinite, there must be an exponentially large degeneracy of zero modes. Sorry, I'm running out of time, but I really encourage you to read this paper for that. So basically, there is some kind of an index theorem which gives you that. So I checked the literature, and the earlier such example happened in super frustrated SUSY models, where there's something called a Witten index, but that only happens for the ground states, and these guys happen for high energy states. Okay, but anyway, so whatever, you can do some exact diagonalization on these ladders to basically verify the mechanism that I'm going to tell you now. So the mechanism is, as I already indicated, you turn on a lambda now, a finite lambda. At finite lambda, there's this index theorem goes out of the window. So the zero modes, which are exponentially large manifold, hybridize with another exponentially large manifold of the non-zero modes. But there are certain special linear combinations of the zero modes which actually continue to diagonalize the O potential operators. So they continue to stay as eigenstates of the full Hamiltonian. And it's easy to show that they violate ETH. One signature of that is the sorry, this is not half chain, this is half ladder. So one signature is, you can see I have drawn it at two non-zero couplings of lambda. You can see these scars very nicely here. This is for a ladder of width 2. Okay, that's the minimal width I can take for a periodic system. There are in fact 4 scars here. So this green is at a coupling lambda equal to minus 0.5, and this red is at a coupling of lambda equal to minus 1. It's important to stress here is that because the scar states simultaneously diagonalize O potential and O kinetic, they remain completely unchanged at any finite lambda. Okay. And then there are some further signatures that these scar states don't satisfy the usual volume law and so on and so forth. Then there are some other indicators of this. Sorry, I'm running out of time, which clearly show that there is this scarring. Just to contrast it with something else. So these scars happen
you have, by the way, Arnab, you finished your 20 minutes. But okay.
Sorry. I'll just wrap up. I'm sorry. Yeah. So I'll quickly wrap up in 1 minute. So basically, these scars also leave their signature in the dynamics of the theory. You can actually define very simple initial states with the right energy density, because the scars have a particular energy density. So your energy density should map. So for example, I'm showing this data for a 14x2 ladder. You can show that there are 6,433 initial states with the right average energy. And you can also show that there are only 18 of them which have a finite overlap with the quantum many-body scars. And the rest of the states do have zero overlap. So for example, these two states are such states which have zero overlap with the scar. They start with completely different initial value of some electric flux correlator, but you can see that they just converge to the same value as is expected for a thermal system. But this guy, this init 1, has a finite overlap with the scar, and you can see that it goes to a completely different value. So it's not thermalizing. Okay. And there are some very simple initial states which can be used to generate these anomalous states, okay, as I have drawn here. So there's some very interesting thing about what happens with wider ladders. So on a ladder of width 2, there are only 4 scars. You can show that. But on a ladder with width 4, this we don't completely understand yet. It's much more crazy. There are in fact 46 scars. So this is a peculiar geometric effect. There are 46 scars with a certain energy density. and there are 12 scars with a certain other energy density. So sorry, I've taken a lot of time, but I'll just wrap up. So the question is whether this mechanism also survives in two-dimensional systems, so L cross L systems. The answer is highly likely to be yes, because of the results on the wider lattices, wider width ladders. Okay, the second question is whether this scarring mechanism also survives in non-abelian lattice gauge theories. We are in fact exploring SU2 lattice gauge theories now, and probably it will. And then the third very interesting question is, right now what I gave you is some numerical verification of this mechanism. It'll be very nice to understand this analytically. There's in fact a lot of interesting mathematics here, which I don't have the time to go into. Sorry about that. And so I think I'll conclude my talk now, and sorry for rushing, and thanks for your attention. Yeah.
Okay, so let's thank Arnav for this nice talk. And we have a minute or at most two for questions. So there is time for one or two questions. Anybody has a question, please unmute and ask question. Okay, so I see raised hands. Okay, so
there are 3 raised hands.
3 raised hands. Yeah, I don't know how to raise. Yeah, but anyway, let's go to that. Yogendra, can you please unmute and ask your question?
Yes, yeah, I have a trivial question that is about quantum link model. So why is it called U1 there?
Oh, this is called U1. I didn't have time to go into that. As you know, gauge theories have some local symmetries, and if you write the Gauss's law for it and you convert, you just write the local symmetry for that, you see that there is a U1 gauge symmetry here. That's it. You can also have, for example, a Z2 gauge symmetry or a SU2 or whatever. In this particular case, there is a U1 gauge symmetry, and that's why it's called the U1 quantum link model.
I mean, whatever the Hamiltonian you constructed, it is based on the U1 gauge field, and I can also build SU2 one.
Yeah, that's correct. That's correct. That's correct. You can also build SU2 quantum link models. That's already known in the literature. These models have a long history. For example, I think the first such model was written in 1981. It was just not appreciated that it was a gauge theory. In 1997, then people started appreciating that these are Hamiltonian formulations of gauge theories. Yeah.
Okay, I mean, it depends on the Hamiltonian that I'm going to write, right?
Yeah, yeah, of course, yes.
Okay, so maybe just one more quick question. Sumiran, can you please unmute and ask your question?
Hello.
Hi.
Hi, Arnav. So I had a small question. So that C operator that you described, why was it defined on every alternate rows?
Oh, yeah. So it was defined on every alternate link because what was important for me to get this anti-commutation is that in this product, which defines the C operator, every elemental placket has only one such link. Okay, that's the important thing.
I see.
And then you can prove that that causes this anti-commutation. Yeah.
I see. But if I included...
Okay. Sorry, go ahead.
No, I was just wondering why you had to do every alternate row. What if I took every row? That is some redundancy.
No. If you do every row, then every elemental placket contains 2 guys, which are, then this operator does not anti-commute. You can just use Pauli matrices to prove all this. Okay. And in fact, this also happens in quantum dimer models, by the way, if you're interested. I mean, not the thing that I said, but just the C operator doing this.
I see. Okay.
Okay, so I know that Subhro also has a question, but can I request Subhro to take the question to the tea break session because we started a bit late.
Sure.
And okay, so thank you, Subhro. So okay, let's thank Arnab one more time for his talk, and then we will move to the next talk by another Arnab. Arnab Das from the same institute, Indian Association for Cultivation of Science. Yeah. And the title of his talk is Dynamics and Correlations at the Quantum Phase Transitions Beyond Kibbles Ring. Arnab, please. Yeah. Okay. So again, I will give you a ring at 18 minutes.
Am I audible?
I just heard a little bit of your voice, but I am not getting.
Is it okay now,
Now,
or
now it's better. Yeah, it's better.
okay, maybe yeah, okay, or maybe I just take off the mic.
Try that. Okay, so is it better now? Hi, can you hear me?
Yeah, we can hear you.
Okay. So, so first, thanks the organizers for keeping up this conference alive for quite some time, which is pretty remarkable. And of course, allowing me to present our work here. Though I am not quite young anymore, probably I'm one of the oldest at the age of getting, out of the boundary. But anyway, so so this work is on dynamics and correlations of quantum phase transitions beyond Kibble-Zurek. So this work can be actually presented in two different modes. One is a story mode, which I'll adapt this time anyway, because people are pretty frustrated with COVID. So I won't really frustrate them more with a lot of nasty looking special functions. And the other mode is, of course, that one, which consists of various, it looks like a more or less like a early 20th century mathematical physics talks on special functions. So, well, so my collaborators are Rodrish Weissner, Vishanu Roy Choudhury, and this is the archive version of the paper. So before, if you want to go beyond Kibble-Zurek, let's just first revisit Kibble-Zurek. So stop me in between if you want, it's fine, because I think this won't take much time, because I've put most of the things under the rug. So if there is any question or any confusion, just stop me in between the talk, that's fine. So Kibble-Zurek mechanism basically tells you about the defect you generate if you cross a standard second order phase transition, which is characterized by a local order parameter. So suppose there is a phase which is like paramagnetic, no long range order, and there is a second order phase transition, and on the other side of the transition point, there is a long range order phase. Then what happens if you just drive the system, one of the system parameters, for example, it can be temperature, if it's a finite temperature phase transition, it can be some other parameters, if it's a quantum phase transition, some coupling of the Hamiltonian to the quantum phase transition point. So the question is, if you do that, at some point you have to fall out of equilibrium, because your critical point, at the critical point, your relaxation time diverges. So unless you are infinitesimally slow, quasi-static in the sense of infinite time, you cannot follow the equilibrium state and fall out of equilibrium, and that will create defects. So you won't get exactly a perfect ferromagnet, but there will be some defects in it. So the Kibble-Zurek mechanism counts the number of defects and tells what the density should be. And it does it in an amazing way. It doesn't at all address the dynamics. It just extracts all the information from the equilibrium, from the equilibrium state on the disordered side. How does it do that? So suppose you have this critical point here, and suppose your distance from the critical point is epsilon, which is you are tuning some parameter lambda, which can be temperature or something else. And then, so this is the distance from the critical point. And then you know that there are this standard equilibrium scaling for the relaxation time and as well as the correlation length. So that both of them diverges in a universal manner close to the critical point. And suppose you are doing this linear ramp, you are changing this distance linearly with time with some rate tau q. And then what you do is you compare these two rates. There are two rates. One is given by the relaxation. What is the relaxation rate, which is given by the inverse of the your relaxation time, which is an equilibrium quantity as of now. And And there is another rate, which is just rate of change of epsilon per unit epsilon, which is induced by you as you tune the parameters. So basically you compare the two rates and you say that the system far away from the critical point, the system is always following the equilibrium state because your relaxation rate is much faster than the rate at which you're changing the system. And then it identifies a point where these two rate becomes equal. And since it's a linear ramp, this rate goes like this. And on the other hand, the inverse of this rate goes like this. And on the other hand, the relaxation time goes up like this power law. So there is a point where they intersect and this two becomes equal. And beyond that point, your system's relaxation time is much longer than the typical time scale at which you are making the changes in the system. So the system falls out of equilibrium. So drastic approximation, what is done here is you assume the up till this point, the dynamics is completely adiabatic. That is, you are completely following the equilibrium state. And from this point on, till you reach the other end of the transition point, there is a region called the impulse region where the system doesn't change at all. This statement is basically about the dynamics of the order parameter, because typically this is the relaxation time of the order parameter or order parameter correlations. And then again, on the other side of the transition, as you reach the other side of the transition, your relaxation time decreases, and then you reach another point where your rate equals with the relaxation rate of your system. And then on, you say again, this dynamics is completely adiabatic. Now you're with a different initial state. This state is exactly this rho t, where you actually assume the system is frozen. You carry this state over here, and then you do equilibrium dynamics with that initial state. So as you can see, if you take this scheme up, then of course you are not calculating the dynamics at all. We're just trying to identify the point where the system goes out of equilibrium. You say this is possible under this scheme. If you divide it by adiabatic, impulse adiabatic, then there is a point where it goes out of equilibrium. Identify this point, calculate everything here, and that gives you what is called the hat quantities. Epsilon hat is the distance where it goes out of equilibrium, and at that point there is a psi hat, which is the value of the correlation length at that point. These are all equilibrium quantities because your system have been following the equilibrium according to this approximation. Now, what Kibble and Zurek did, they said that, well, since it was approaching ordering transition, so there will be domain formations. And the typical length scale of these domains, since you are following the equilibrium state, will be of the order of the correlation length. So your correlation length freezes here. That means the linear dimension of each of these domains will be of order xi hat. And this xi hat can be calculated very easily from this relation, which shows where this point goes out of equilibrium, where the system goes out of equilibrium. If you put it in, you get these expressions out from simple algebra using these relations. So you knew this quantity xi hat. Of course, there are non-universal contributions, but the important thing is the scaling law tries to determine things, how it scales with your rates, tau q. That's universal. So how does it do that? So it says that these are the typical sizes of these domains. And in between the domains, there are trapped these prime order vacuums of the disordered states. So this doesn't have any order at this point. This is like a zero superfluid density state, for example, in a superfluid or something like that. So it's like a core of a vortex in this picture. And then when you reach this part, then coarsening happens. These domains increase. Some of this defect goes away. But nonetheless, the number of defects remains proportional to the initial seeds which are created at this point. So that's the assumption of Hibble-Zurek. And then eventually coarsens out, and this they develop the stiffness of the phase, and these defects cannot move very freely, and they are also separated by macroscopic distances, and they enjoy this topological protection due to the stiffness of the phase. And then they become topological defect after the coarsening happens a long time. Nonetheless, the assumption is their density still remains proportional to the number of the initial seeds. which is clearly proportional to 1 by xi to the power d if in d-dimensional system. So that gives the density of defects which scale as just plugging in this relations tau q to the power some universal power of the static critical exponents. So without doing any dynamics, you just get the scaling of the defect densities. So that's the story of Kibble-Zurek. So it was proposed in 1976 by Kibble, not the whole story, a part of it, and then Zurek made connections with a much general scenario and reduced the power laws, etc. And in quantum context, it was done by Bortan Damsky, Zoller, Zarmaga, and there are a lot of people who work from this country, like Amit Datta, Diti Mansen, and Krishnan, a lot on this quantum problem. So the thing is, this Kibble-Zurek mechanism turns out to be uncannily robust towards plausible flaws. For example, your adiabatic impulse approximation cannot be correct if you're very slow, where actually you are really skimming the lower part of your spectrum, the low energy part of your spectrum. Then actually your impulse regime can be quite long. You can spend a lot of time in the impulse regime. So it's not expected that the impulse regime will be completely impulse. So interestingly, if you do real calculations, it always turns out that this doesn't pose much threat to the scaling laws, this defect density scaling laws. It just changes some prefactors or a little bit corrections to the powers, but the main scenario remains qualitatively unchanged. There are some quantitative changes, of course. It's not clearly understood why there is this uncanny kind of robustness against these things. But the question we ask here is a bit different. We don't ask the question, what is the defect density, how it scales with tau q, your rate, but we ask what happens to the correlations. This is somehow a question people didn't ask for a long time. So since I'm in a story mode, just let me tell you, this calculation was done a long back. It's 2009 when I was just trying to, I was a first postdoc and was trying to understand Kibble-Zurek mechanism, and I did this problem for different kind of correlations. I thought of studying the correlations instead of densities. And I was mesmerized to see that you get a sea of special functions because it involves these parabolic cylinder functions which suffers from Stokes phenomena. So you go in different directions in the complex plane, they have completely different asymptotic expansion in terms of various special functions. So they're really ugly and you cannot handle them. But if you just look at them, surprisingly, everywhere where there is a scale appearing, this scale is consistent with Kibble-Zurek. This is like a magic. I mean, you do a lot of things, it's ugly special functions, but you don't look at the functions because you most of the time cannot manage them, but just look at the scales, they are Kibble-Zurek. So I thought, okay, that's it. It's amazing. I learned a beautiful thing. Kibble-Zurek is great, but there is nothing much to do because all the correlation tells that the scales should be determined by the Kibble-Zurek, whatever system you take. So more or less, that was my conclusion. And the calculation, it was a pretty nasty calculation, remained on my desk forever and gathering dust. Then Krishanu came up when I was in Max Planck and he wanted to learn some of these calculations because it involves special functions and there are certain ways you have to handle these differential equations. And we were just wondering over this beautiful thing that you have this uncontrollable swarm of functions, but the scales are correct, just given by the simple, very simple Kibble-Zurek mechanism. And then our other collaborator, Rodriguez, just popped in for with a coffee cup and said, hey, what are you guys doing? It looks like a 17th century stuff. What is this? So we were saying that, look, how beautiful Kibble-Zurek is. And then he said, okay, yes, but it's wonderful, of course, but what is this? This is a Gaussian correlation in space. I've never seen a Gaussian correlation in space. So that made us, we actually overlooked this part, this functional form of these things, because we are so carried over by this fact that the scales are all given by this simple principle for these complex differential equations. So he picked up this point that the functions are also quite interesting, and that started this project basically. So what we did is we not only found that there are bizarre looking correlations, which we usually do not see, but at the same time, these correlations are also something which you cannot, in principle, explain by Kibble-Zurek mechanism. They are qualitatively different from what Kibble-Zurek mechanism suggests. So we'll do this in quantum setting. So we'll take a quantum Ising chain with the standard one. So everybody knows this. So your critical point appears as H equal to J, and epsilon is this. And from your critical scaling, your tau is 1 by the gap, and the gap exponent is this, mu z. From this, you know that mu and z equal to 1 for this model. So what we look at for this model, looked at is the kink correlations. The kinks are the domain walls. So one spin up and one spin down, this kind of configurations we call kinks. They can be domain walls. They can be very short domain walls of one size, which we just don't call a domain really. But instead of looking at the densities of this kink, what Kibble-Zurek usually do, what we did is we tried to see the correlations between these kinks. So this operator counts the kinks. So if the two spins are aligned, this count is 0, so you don't count any kink. If they're opposite direction, there is a -1, minus, plus, and then I missed a half factor here. And then what we calculated is the connected correlator. So, but you can look at this thing is already a 4-point function, and if you go to the fermions, which will eventually go because it's an integrable model in terms of fermions, so you get a 4 fermionic correlators. So what we did is basically we did a duality transform, and that makes this model looking like that. And our kink correlators then reduces to this 2-point correlators in terms of these new objects, the newly defined operators. And then, of course, we do a linear ramp as we use a Kibble-Zurek mechanism. Our initial states are all up in the x direction. X is the order parameter direction. Then we do Jordan-Wigner transformations and some other transformations, some linear transformations in time as well, and some unitary transformations. And then our wave functions look like a product of wave functions in the K space. Of course, that Jordan-Wigner and Fourier is enough for that.
Hi, Arnab. Just wanted to remind you that you have taken 18 minutes so far.
Really? Come on.
Yeah,
okay,
I think so.
So this is a wave function, and then you have put this time-dependent Schrodinger equation. This turns out to be a Weber equation. And solution are parabolic center functions, and these, as I said, are horrible. They have these Stokes phenomena, and you have to find play around quite a bit to find out a convergent expansion of these functions in terms of other functions in the domain of your interest. If you do all this correctly, then it turns out your defect correlation actually decays not exponentially, but actually as a Gaussian, as a function of your distance. Now I'll be very fast now. So the idea is, if you followed Kibble-Zurek and did this adiabatic impulse, adiabatic stuff, what you would get is exponential. And clearly, this is a Gaussian, which is completely different functions. It's just not exponential with some different exponent, but it's just completely different function. It happens at tau greater than J limit, which is an approximation. I'm not going to the approximation anywhere. And we also, so since it was an approximation, we had to test it numerically. We did numerical simulations for this. For a very large system, you can do that. 10 to the power 4, 5, because it's an integrable system. And here is a feat of log rho r as a function of r square. And you can see a very nice linear fit. So this is a case where you stop at the g equal to 0 point, where you just the transverse field is 0. And this is the ramp which goes up to infinity. In both cases, you see this beautiful Gaussian correlation. And then you can see for the case where you stop at a finite value of TF, you might say, how stable is this Gaussian relation? So you can stay there and wait for infinite time. the Gaussian correlation still prevails. It's something like a very stable correlation which doesn't disappear with the coarsening phenomena. And most interestingly, you can show that in any energy density, we constructed various forms of energy eigenstates of the Hamiltonian. You will see that in most of the energy eigenstates we could explore, we always found that the correlation, this kinking correlation always decays exponentially. So basically, you cannot say that this comes somehow related to the behavior of the eigenstates of high energy or something like that, or even it can be shown with a little bit of mathematical manipulation and a small theorem that it cannot even be expressed as a diagonal ensemble average over these kind of states which has exponential correlation. So what we found that we had a general theory for that. So I'll just tell it in 1 minute. So this is we identified this. This is our correlation. So if you go to the boson, this is a density-density pair correlation. And then we realized that if you take really bosons in the non-degenerate limit, then density-density correlations actually shows Gaussian behavior. So we go to the this correlation maps to the hardcore boson density-density correlations. And if you actually go to bosons, forget everything, bosons at finite temperature in the highly non-degenerate limit, where they are behaving basically classically, then this is this is the correlation we get. So basically, the picture that emerges, in spite of the fact that it's a integrable model, in spite of the fact that we dealt not always with a state which is at equilibrium, the description of the kinks turns out to be a thermal description, which was completely excluded from Kevil-Zurek because this thermal description arises due to the excitations here, this departure from this green line here to this red line, which is the actual thing. So these excitations at the impulse range.
So Arnab, just another reminder, you have just 1 more minute out of your total 25 minutes, which includes questions.
Yeah, so that's the story. So we did some numerical checks to verify the thermal situation, which turns out to be pretty consistent. And there are some experimental domains where you can do this, experiments, and our things are robust in this thing. Okay, thanks a lot and stay safe.
Okay, so let's thank Arnab for his wonderful presentation. So we are actually just out of time, but we might have time for a quick question. So anybody, so let me check the raised hand. So I don't see any raised hand, but anybody willing to ask question, please unmute and ask question. Okay, I don't hear any questions. So maybe then we will move to the next talk. But before that, let us thank Arnab once again for his presentation. So with that, let us move to the last talk of this session, which is to be presented by Saurav Nandi from IIT Bombay. Wait a second. And then the title of his presentation is Dephasing in Strongly Disordered Interacting Quantum Wires. Okay, so this is a total of 12 minutes presentation, 10 plus 2. So maybe I will give you a ring at 9 minutes, Saurav. Is that okay? I don't know if it is me, Saurav. I can't hear you. Can other?
Yes, sorry. Actually, I had this. Sorry.
Okay. Yeah.
Just a minute. I hope you can see my screen or not.
Yes, we can.
Just a minute. Maybe. Okay, can you see it now? And I change my slide, then you can of course see, I guess.
Yeah, we can see this.
Okay, thanks.
So
Okay,
your
yes.
time starts now, and I give you a ring at 9 minutes from now.
Sure. Okay, so I'd like to start by thanking the organizers for giving me the opportunity to present my work over here. This is the title of my talk, and this work is already up in the archive in case you are interested. And I'm going to tell a part of this talk. So here's the model that we consider, and this happens to be the standard model for many-body localization physics that I'm going to talk about. These models, as you can see, describes interacting fermions in presence of random disorders. Okay, and as we know that these models at the level of eigenstate host these two phases of matter, the ETH phase and the MBL phase. If you tune W, for instance, here is kind of a broader picture. So the x-axis is your W, the disorder strength, and the y-axis you can think as 1 over L, L being your system size. Okay, so when 1 over L is 0, that is L tends to infinity, or you are in the thermodynamic limit, then there are these two asymptotic phase, ETH and MBL. This phase, you know, the eigenstate thermalization is valid, and there's the many-body localization phase where it is not valid. But the point is that as long as you are in any finite L, then you are going to have this critical fan type things which captures this 1 by L artifacts. So depending on your L, you can be in a regime where this critical phase can be broad enough. One has to be careful about that while doing numerics. So as we all know, MBL sort of poses a challenge in terms of numerics because there is some system size limitations and all that. However, as long as you are interested in dynamics, there are methods by which you can actually push your system size to be around 100 or so. But again, these methods have their own limitations. Some of them are useful or valid in very weak disorder, and some being valid in very strong disorder. And then there is this immediate question one can ask, what about the mean fields? Because if mean field works, then we can immediately ameliorate this problem of system size. And with this objective in mind, we try to address this question, and we perform a mean field calculation, which is the time dependent Hartree-Fock calculation. And we try to explore whether such mean fields, time dependent mean field theory can capture the MBL physics. And if it does, then to what extent? So that's the objective. And I'm not going to actually show you the details of the implementation of this time dependent Hartree-Fock mean fields because of lack of time. But if you are interested, I would be happy to talk with you about it after the talk. Since it's a very short talk, I will flash the conclusions right away in front of you, and then I will elaborate my points one by one. So essentially my conclusions are interaction induced dephasing is absent in TDHF. TDHF means time dependent Hartree-Fock. Then interaction manifests differently in different phases, and such manifestation usually diminishes once you do some incoherent averaging, particularly for large disorder. Then we will show that TDHF fails to capture the MBL physics. And finally, we show that the temporal fluctuations of some local quantities show a pre-asymptotic power law decay even within the thermal phase. And we discuss some of the implications of it. So with this, let me just begin with the first point, that TDHF misses the dephasing. So here we see the density as a function of time. The density is taken at a particular point in the lattice, we take periodic boundary condition, and particular point in the lattice we take the density for the particular disorder realization. But whatever physics I am going to tell you holds for all realizations and all sites within a lattice. So we start with a charge density wave kind of initial state, perform a quantum quench, and this is a low disordered result. W is 1.5. And here what we see. So if you look at this exact result with at equal to 1.0, this red curve, you see that they start with some oscillation, and this oscillation gradually damps out. And this is what you call the interaction induced dephasing. And this is what gradually leads the system to equilibration at large time. Then if you look at the non-interacting results, which are these blue curves, you see there are some strong oscillations which keeps on happening. And then if you look at this TDHF result, which is the black curve, then of course you can see they don't follow the non-interacting curve exactly. So that means it perhaps captures some of the correlation effects. But the important point is that it also shows this persistent oscillation. So the dephasing effect, which is the damping of this oscillation, is completely missing in TDHF. Okay, the second conclusion, the interaction manifests differently in different phases. So here is already what you have seen, the scenario for weak disorder. Now this is for you for the strong disorder. This is for W equal to 5.0. Okay. So in strong disorder, we again see there are strong oscillations for these non-interacting results, which are the blue curves. Okay. But surprisingly, as opposed to this weak disorder phase, in strong disorder, we see that the exact results, which are these red curves, show a very strong oscillations. And actually, I must point out that such oscillations are actually wrong-lived, and they kind of manifest the lack of ergodicity in the system. And such oscillations actually can be attributed to a two-particle cooperative motion in a largely decoupled system where the cooperation between the two particles are induced by interaction. So this is a effect of interaction what you are seeing. And in this phase where dephasing is almost absent, you can see that TDHF follows these oscillations very well. And in fact, there are cases where it can be quantitative within the short window of observation. But that's not the important point. The important point is that as long as you are interested in understanding the interplay of disorder and interaction, it's often very useful to look at a single disorder and a local observable, very local observable, where you can see these effects very prominently. However, such effects are kind of washed out if you perform some incoherent averaging, which is my next point. So suppose you are now going to calculate something called the imbalance, which involves the summing over the densities at each side. And then if you compute this imbalance and plot it, you see that the difference of the non-interacting and the interacting results that you were seeing in my previous slides are kind of washed out for strong disorder. Of course, there are some differences that are present, but it's sometimes very hard to discern this difference. So that's the point. The point is that if you perform this incoherent averaging, that kind of diminishes the correlation effect, which was otherwise present. Okay. The important thing to notice over here that in MBL kind of things, you do one more averaging, which is this disorder averaging, and you can, and if you do that on top of it, believe me, none of this actually prevails. So that's the point I wanted to sort of point out. The next point is that TDHF fails to capture MBL physics, and how do we show that? To see that, we plot now the disordered average imbalance as a function of time. Okay, so here is the small disorder case. Here you see both the exact result and the TDHF result gradually falls to 0, and that hints towards the presence of local thermalization. Okay, and but I must point out that in this case the exact result falls to 0, which is its equilibration that is brought about by the dephasing mechanism. However, the imbalance falls up to 0 in TDHF case as well, which has a different origin. It happens because the time fluctuating Hartree field that you put when you do the mean field theory gradually actually delocalizes your single particle localized state, and that leads to this fall of imbalance. The point is that now if you go to high disorder, you see that the exact results of imbalance gradually saturates, but the TDHF results keeps on falling, and it gradually goes to 0 if you wait long enough. So put the things in a little more mathematically. IT, which is imbalance of T, goes as T to the power minus beta. It decays in a power law fashion. And the whole point is that this beta is usually 0 for MBL phase, which points towards the onset of localization. However, if you are doing a TDHF calculation, you can show that beta corresponding to TDHF is always finite. It actually decreases with increasing value of W, but it always remains finite. So then it's just a matter of time up to which you have to wait. And then you see at large time, it always goes to 0. The imbalance always goes to 0. And that essentially points towards the thermalization. And in that sense, we say that TDHF actually fails to capture the MBL physics. Okay. So next I will talk about the temporal fluctuations of the local quantities. So which also captures the dephasing and how the system goes through this dephasing stuff. So here is the quantity that we observe, that we measure, which is the time fluctuations of these local quantities. So let me just point out this result very quickly. So first, we see that for non-interacting case, there is no decay of fluctuation, it's just flat. For TDHF, there is actually a decay, but that decay is much slower compared to the decay you see for the exact case. And this is just a manifestation of on the fact that TDHF is very bad so far as capturing dephasing is concerned. One more point is that TDHF does not show any discernible finite size effect. On the other hand, if you look at the exact result, you see that there are strong finite size effect, and actually these fluctuations, even for very small disorder, which is well supposed in thermal regime, decay with a power law fashion. However, this is a pre-asymptotic behavior, because in asymptotically large time in the thermal phase, the fluctuations of local quantities are expected to fall off exponentially fast. But anyway, this is a pre-asymptotic decay, and the pre-asymptotic decay happens to be a power law decay. So you can associate this thing as this. So Fw of t goes as t to the power minus zeta, where zeta is your decay exponent. Now you can find out that this zeta is basically a function is proportional to 1 by w square. So if you plot zeta as a
Okay,
function
Saurabh, we have completed your 9 minutes. Huh?
Okay, sure. I will complete in 1 minute. So if you plot this zeta as a function of w square, 1 by w square, you see that you get a straight line, which tells you that zeta is a function of 1 by w square. And for small disorder, if you calculate both the typical value and average value, you can see that they differ quite a lot. And this kind of points towards a strong sample to sample fluctuations in the weak disorder regime. So some points, some comments are in order. So first, even within the thermal phase, the temporal fluctuation decay with a power law in the transient time scale, that's number one. Number two, that inside localized phase also, the damping occurs as a power law with t to the power minus beta, beta being xi sp. Xi sp is the single particle localization length. But I stress that this decay in the localized phase is the asymptotic decay. And this was actually shown by this paper by Sarvin and his collaborators. Now, we have already seen that this zeta, our exponent, goes as 1 by w square. And this is now quite tempting to associate this exponent zeta with the decay exponent in the MBL phase B, because B is essentially proportional to 1 by w square, because 1 by w square is proportional to xi sp. Okay. So the point is that with this calculation, one can be tempted to associate this B with this exponent zeta, which is the pre-asymptotic power law decay within the thermal phase. But at this moment, we believe that it's kind of premature to associate these two exponents. The reason being that in some sense, it will assume that the mechanism for this transient decay of fluctuations within the thermal phase is somewhat analogous to the asymptotic decay of fluctuations in the MBL phase, which is very unlikely to happen because all these arguments within the MBL phase are standing on the you see the presence of local integrals of motion, or the Lioms within the phase, but the regime we observe, there is no such.
Saurabh, we are done with 11 minutes of the total 12-minute time. Huh?
Okay. So the point is that since these mechanisms are completely different, it's hard to sort of point out that they are same. So, but if such dynamical regime exists, it will need extra attention. So with this, I will sort of finish. This brings me to the end of my talk. I would like to acknowledge and thank my collaborators with whom I have done this work. There's Shomo Bera from IIT Bombay and Ferdinand Ivers from Regensburg, Germany. I have already told you the conclusion. So I thank you for your very kind attention and would be happy to take up questions.
Okay, so let's thank Saurabh for his presentation. And we have little time for questions. So anybody feeling to ask questions, let me check.
Amida, can I ask a quick question?
Sure, you can. Yeah, okay.
Yeah, I'm technologically challenged. So, Saurabh, just a quick question. So, in your introduction and motivation slide, right, there was here. So, you mentioned that there's something called Lindblad DMRG, which works when W is much, much less than WC, and you can go to system size of the order 100, but that's like an ETH phase. So, how can you go to a system size so large? I mean, don't you hit an entanglement wall or something like that?
Okay, frankly speaking, I have not studied these algorithms very in gory detail. So, yes. So
I see. I can imagine that you can go to a big system size for an MBL phase, which is this other thing, W greater, much greater than WC. But I'm just confused with this statement. So.
Arnav, if I may say, that's why it's Lindblad. So the bath take away the entanglement.
Oh, I see. I'm sorry. Oh, I thought it was a closed system. Oh, I'm sorry. Okay, got it. So your entanglement is taken away by the bath. I see. Okay. Thanks. That's it.
Okay, so if there are no more questions, so let us close this session here. We are sorry we are already over time by some amount. So, but before that, let us thank all the speakers of this morning session today. So, thank you, all of you. And is there any announcement from the organizer with time?
Yes.
Because
Yes.
We're
Yeah.
running
So
a bit late, so yeah. So maybe
yes. So
5
let
minutes.
me thank Amit for chairing this session and also all the speakers. Because we are running a bit late, we have decided to start the next session at 11:05 instead of 11. Okay. So that's the announcement. So we're just shifting it by 5 minutes.
Good.
Thank you.
Thanks all.
Thank you. Yeah.
Hello. So Amrita, I'll make you a session co-host.
Yeah, sure.
Yeah, sure. Okay, so I made you the co-host. Let me see if the speakers are all there.
Hello.
Hello.
Hi, this is Mukul here.
Hi, Mukul. Yeah, just give me 1 second. I'm just doing it sequentially as I see people.
No, I was using some device and yesterday it didn't happen. So I was thinking that if you can hear me today.
Yes, no, no problem. Okay, so who else?
Hello, this is Nirmal. Am I audible?
Yes, you are audible.
Great,
Give me
thank
just
you.
1 minute. I'll make all the speakers as co-hosts, and then we can go one by one in checking the links.
Yeah, sure. Thank you.
So only Shujoy Roy probably not here.
Arnab Mukherjee, I don't see as.
Okay.
Sujay Ray, let's see. Sujay Ray, I see.
Yes, I'm here.
Yeah, okay.
Can you hear me?
Yeah, just yeah.
Okay, so let's go from the top. So Nirmal, maybe can you share your screen?
Yeah, I'm doing that.
So Nirmal, you're having some trouble sharing the screen? I mean, hello.
I think so. Probably his screen is stuck or something.
Should we check for others in the meanwhile? Because we have 3 more minutes. Or
Yeah, only 3 more minutes.
yeah, so maybe let's go come back to Nirmal in a bit. So Mukul, can you share your screen?
Yes, I'll try.
I see your screen.
Okay. Can you just tell me that how to use cursors?
You go to the full screen and there is an option as far as I remember. Just go to the full screen first.
Okay.
Yeah, so now go to the left corner.
Oh,
of
there
the
is
screen.
there is the pen there, so you can just directly take it from there.
Acha, this pointer options, automatic laser pointer. Yeah. Fantastic. Fantastic.
Okay, sure. So your thing is fine.
I will unshare it now.
Yeah. So
pause sharing. Am I out or?
No, you are still there.
Yeah.
1 second. Where is this going? Okay, I am out, right? Yeah.
Yeah. So
Yeah, this is Nirmal's screen, I think, also there. So, but I do not understand why we see some screen before that.
Yeah. So Nirmal, maybe can you just unshare and just share it again? It seems to be a bit stuck. It might be a network issue. Yeah, it's not a lot clearer.
Now it's good. Oh, it went.
So probably he'll try it once more. Let him. Nirmal, just go ahead and try it once more.
So are you presenting from a mobile network? I can't hear him either.
Yeah, me too. So Nirmal, can you hear us? Maybe there is some network issue.
So how exactly are we going to proceed right now?
Let's see. I mean, well, I don't have his number.
We can quickly check the others in meantime. And
yeah, so in the meantime, why don't Sumanti, can you please share your?
So I am his I have his number. So
oh, Mukul, can you just give him?
There was some problem with the audio, I guess. Could you see my screen anytime?
Yeah, we could see, but it was a bit frozen. Can you just try it once more?
Yeah, I can try it once again.
Sure.
Oh, I'm not a co-host anymore because I had to disconnect and connect again.
Oh, okay. Give me 1 second. I'll just make you co-host. Yeah, go ahead.
Okay, thank you. Yeah. Can you see the screen now?
Yeah, now perfect. Yeah, good.
Okay. It's moving also, right?
Yes.
Yeah. Thank you. Thank you.
Yeah.
So I stop sharing so that others can try.
Sure, thanks. Good. So Sumanti Patra, can you give it a try?
Yes, I'm sharing.
Sure. Yeah, I can see your screen. Just go to full screen.
Yes. Oh, is it visible?
No, you were visible. Where did you? So it was visible earlier when you were not in the full screen mode.
Okay. Just try. Oh, it's not. Okay.
No, so
is it a PDF?
Yeah, it's a PDF.
Okay.
See, in the worst case, you can perhaps show it as you were showing in case.
Not in the full screen mode.
If that you could do, that's not a problem. I mean, it's
now perfectly fine, right?
Yes,
It's yeah, good.
And your cursor is visible as well.
Cursor is visible.
Yes.
Yeah, sure.
Yes. Okay.
Okay. So Sujay, Ray, go ahead, give it a try.
Yeah, I'll share my screen.
Well, we are two minutes past 11:05 already.
Yeah, and this one speaker hasn't shown up. This Arnab Mukherjee from ISER Mohali. So maybe if he doesn't show up by the time, we'll skip him. And if he shows up at the end, maybe we can have him after Sujay Ray.
Yeah, surely. Yeah.
Okay. Okay, so
Yes, can you see my screen?
Yeah, we can see your screen. And can you just scroll? Okay, good.
Yeah.
Okay, I think we are for now. Okay, so maybe I'll turn it over to you, Amrita. You can take over now.
Yeah, surely. So the first speaker is Nirmal, right? So I request Nirmal to present his screen already.
Okay, thank you.
Nirmal Ganguly is going to be the first speaker of the day. We have 5 different talks. So Nirmal and I started almost our PhD in the same time. So Nirmal is going to, he's a professor in IISER Bhopal now. He's going to speak on perovskite oxide heterojunction for Rashba-Dresselhaus assisted antiferromagnetic spintronics. So Nirmal,
Thank you.
over to you.
Thank you for the introduction. So is my screen visible now?
Yes.
And I'm audible also. That's great. Okay, so good morning, everybody. And I thank the organizers to begin with for organizing such a nice meeting this time during the distress of Corona and giving me an opportunity to show our recent results. Here we are going to talk about perovskite oxide heterojunctions, where we will show Rashba-Dresselhaus assisted possibility of developing antiferromagnetic spintronic material. So what are we going to do here? We are first going to talk about what is antiferromagnetic spintronics. Antiferromagnetic spintronics is, as proposed, going to bring a paradigm shift in the electronics. How? Because nowadays we have computer processors working at a gigahertz speed. Antiferromagnetic textures can be operated at a terahertz speed. So it leads to huge improvement in the computers, and that comes at a much lower power consumption. So it's of a lot of benefit, and it's robust against perturbation due to magnetic field. No stray magnetic field emerges out of it. So how does this antiferromagnetic spintronic works? There are antiferromagnetic spin textures, non-collinear spin textures essentially, that has to be manipulated. The manipulation can be done using spin orbit torque. And the spin orbit torque, with the help of spin orbit torque, electric field and current induced switching of antiferromagnets, we can achieve faster processors as well as faster and non-volatile memories, random access memories, I mean. Now the point comes to realizing spin orbit torque. How can we do that? One of the possibilities is Rashba or Rashba-like effects, where magnetic systems that lack inversion symmetry. So magnetic system is not a necessity for Rashba-like physics, because we are talking about antiferromagnetic spintronics. I'm talking about magnetic systems that lack inversion symmetry. There is a sizable spin orbit interaction and an electric field that leads to Rashba-like effect, and using external electric field, the Rashba strength can be tuned. That may lead to spin orbit torque. So let's investigate the Rashba physics a little more. This is the Rashba-like Hamiltonian, which is given by alpha is the Rashba coefficient times the cross product of Pauli matrix vector and the momentum vector dotted with z cap, which is the direction of the electric field. And the consequence of the Rashba term in the electronic structure, if we consider a free electron model, then the band looks somewhat like this, a parabolic band where both spins are degenerate. If we consider Rashba-like effect, for this kind of Hamiltonian, we have a separation of these two bands in the momentum, not in energy. We have the separation in momentum. So this much momentum is called K naught. This much energy is called ER. So these are the Rashba parameters. And using these parameters, this coefficient alpha can be determined. If we look into 3 dimension, that is, if we plot the energy as a function of Kx and Ky, which can be done in a 2-dimensional system, this is how it looks like. And if we draw the constant energy contours, that is this contour here, that's a bigger circle here with the spins precessing like this, and there is a smaller circle here with the spins precessing in the opposite direction. This is Rashba effect. Now we come to perovskite oxide system, where we are trying to realize this kind of physics. So the famous example of perovskite oxide heterojunction was lanthanum aluminate and strontium titanate heterostructure. The structure is AbO3, which is cubic or near cubic orthorhombic kind of a structure. For this heterostructure LaOSTO, there can be planes of strontium oxide or lanthanum oxide and titanium oxide or aluminum oxide. Now, strontium titanate is a non-polar material. Each plane of it is charge neutral, but lanthanum aluminate is a polar material, meaning this plane has a -1 charge and this plane has a +1 charge. If that happens, that develops an electric field and increasing electric potential. So with that, if we have that kind of a system, that means if we consider strontium titanate in this part, lanthanum aluminate in this part with plus sigma and minus sigma charge density on the planes, we can consider this as a parallel plate capacitor model. And we have, this is the offset of band, the valence band, and this much is the energy gap of one material, the smaller gapped material. So this much we call a critical potential. So the electric potential can be written like this, where this step is given by this term, n number of steps like this is given by this term, and n number of other steps like this is given by this term. And this has to be equal to this critical voltage that I pointed out here. If we have this kind of an arrangement, then we can see that as we increase the number of unit cells of lanthanum aluminate here, the amount of charge transferred here, sigma T, that increases. And with n tending to infinity, this reaches -12, that is half an electron is transferred at the interface unit cell. For lower number of unit cells, it could be less. With this idea, we would do something interesting after introducing this paper. So here in this paper, Matsuno et al., they in 2015 considered the Rudelston-Popper series for iridates, and they considered superlattices for strontium iridate and strontium titanate, where when they consider one unit cell of strontium titanate and one unit cell of strontium iridate repeated many times, they find that the strontium iridate layer became pretty much like SR2IRO4. So SRIRO3 is a bad metal with no magnetic properties. SR2IRO4 is a Mott-like insulator with antiferromagnetic properties. And here, SRIRO3 starts behaving like a Mott insulator with antiferromagnetic properties, because along the C direction, it cannot interact with other iridium atoms. And that's the similar structure of SR2IRO4. So we took up this idea from here, then verified the same thing when we considered strontium iridate, strontium titanate supercell one by one in plane. We found a metallic system, but when we allowed for antiferromagnetism, taking 2 by 2 unit cell, we found a small gap here in the density of states. This band right above the Fermi energy becomes extremely narrow. You can see also from the density of states, and it becomes antiferromagnetic but not collinear. These are the magnetic moment vectors that you can see in the inset. They are not collinear. The structure is tilted with an angle of 14.1 degree of tilt of the IRO6 octahedra about the C-axis. Now we take this heterostructure and take the idea of electric potential development to do something interesting. So before going to that interesting part, here I point out what are the ingredients for antiferromagnetic spintronics. We require a conducting system, which SRIRO3, SRTIO3 is not. We require antiferromagnetism, preferably in non-collinear fashion, which it is there. And Rajba-like spin-orbit interaction is also required, which is not there in SRIRO3, SRTIO3. So we consider capping it with lanthanum aluminate, LaAlO3. When we do that, we expect to transfer some charge at the interface and also at the strontium iridate layer, because Strontium titanate has a large band gap. Strontium iridate has a much smaller Mott or Slater-like gap. So we expect to transfer the charge at the strontium iridate layer, precisely at iridium D states. This structure is also heavily tilted. Here, the tilt angle about B axis is 5.4 degree and about C axis is 13.4 degree. Now, if we look at the charge transfer, if we find out the transferred charge and plot it as isosurface on the structure, we see that iridium oxide layers at both sides are populated by that charge. And also summing over the transfer charge density, we find that exactly those are the places where the transfer charge density lies. Everywhere else, it's almost negligible. And we notice that the charge transfer quickly reaches its asymptotic limit of half an electron. For example, at 5 unit cell thick LAO can lead to already 0.45 electron per unit cell transfer. Here also we have non-collinear antiferromagnetic ground state that I'll come later again. And this is the pattern of the non-collinear antiferromagnetic ground state that we see here. Here we find out the magnetic properties, all possible magnetic orientations we have explored. This is the ferromagnetic, this is striped antiferromagnetic, and this is checkerboard antiferromagnetic. Well, our results are non-collinear. It's not exactly like this, but somewhat similar. You can see that the magnetic moments are canted, not in any arbitrary direction, rather in the direction of the axis of the octahedra. So we clearly find that checkerboard antiferromagnetic arrangement has the lowest energy. So we talk about only this one in future, nothing else. It has 0.2 Bohr magneton per iridium atom of spin moment and even larger orbital moment. And if we change the U value, then also the numbers don't change much. So this is a robust prediction of antiferromagnetism. With this, we move on to the band dispersion. Here we look at in this energy range, we have the bands that correspond to the narrow iridium D band that I have pointed out earlier. After charge transfer, half of that band is occupied and the other half is empty, but that's not exactly true. Here we can see some hole pockets. Here we can see some electron pockets. And it looks like having Rashba-like splitting, but these bands behave more like holes, not electrons. So it's inverted in energy. We have a two-dimensional Brillouin zone here because we have a heterostructure. So as a function of kx and ky, we plot the three-dimensional band diagram. And here, these are the parts that should behave somewhat Rashba-like. So what we do next is plot the upper part, zoom in the upper part here in this picture, which shows not exactly Rashba-like pattern, rather something different. We have two hills in here. In Rashba, we should have something else that I have shown earlier in a picture. And if we now trace the constant energy contours like this, it appears here. There are two almost degenerate lines here, That is a characteristic feature of antiferromagnetism, which is fine. But instead of circle, we get arcs of ellipse here, also arcs of ellipse here, overlapping. If we look at this whole region here, the hole pockets turn out to be like this. So clearly hole pockets can be identified here. And the Fermi contours are shown here. These two features correspond to hole pockets. And at the corners of the Brillouin zone, these correspond to the electron pockets, which is expected from this band picture. But we don't really understand what is happening in this material. This is not exactly Rashba-like physics, although from the 2D band, it looked pretty much Rashba-like physics. So we further investigate this 3D band. Here we develop a simple model for Rajba-Dresselhaus effect. If we consider a free electron-like system, this is the Hamiltonian given, and the eigenvalues are just the kinetic energy. There is nothing else. So for a hole-like system that is negative effective mass m star, we will have this kind of a 3D band if we consider two-dimensional Brillouin zone. Now we add the Rajba term. So here the Rajba term is written after taking the dot product with Z, the cross product and dot product. So it's along the Z direction, our electric field. Then we will have the eigenvalues looking like this. We have plus minus alpha k term here in the eigenvalue. And because of this, as we have shown earlier, for hole-like system, this would be the Rajba band. And the cross section looks like this. The constant energy contours, two concentric circles. Now let's look at the Dresselhaus term. The Dresselhaus term is a bit different. Instead of the cross terms of k and sigma, we have the direct terms here. And the coefficient is beta. That's nothing different. But the eigenvalues, if we calculate, it trivially differs. Instead of alpha, we have a beta here. No other difference. That means all the eigenvalue plots that we have here also hold good for Dresselhaus effect. Although the eigenstates are different, that means the spin precession, if we plot that, that would be different for Dresselhaus and Rajba. Anyway, that is not going to match with our calculation, whatever we find from our DFT calculations. So what we do, we try both Rajba, combining both Rajba and Dresselhaus effect. If we combine both effects, then this is the eigenvalue that we get. And the plotted in
5 minutes left, right?
Okay, thank you. If we plot in 3D, it looks like this. We recreate the double hill pattern here. The cross section looks like this. And here are the constant energy contours. But this is along a diagonal. And these are arcs of circles, not arcs of ellipses. So with combining Rajba-Dresselhaus effect, we came closer, but could not really pin the physics that we are observing in our DFT calculation. So we considered anisotropic effective mass in the system. That means the effective mass along kx and ky should be different, because there are tilts about tilts of the octahedra about A and B axis, and those tilt angles are different. So here we consider a larger unit cell, √2 by √2, the red square here that marks the bigger unit cell that captures the tilted structure. And when we do that, the crystal momenta we call k small kx ky for the smaller cell and capital Kx ky for the bigger cell, and they would be related like this. They are rotated by pi/4 angle, and they are also in size, they are different. Therefore, this is the relationship between them. After obtaining this relationship, we write down the anisotropic Rajba-Dresselhaus Hamiltonian, where H0 is the kinetic energy term, this is the Rajba term, and this is the Dresselhaus term. The kinetic energy term is given by this. Now, assuming the Rajba and Dresselhaus terms as perturbation to the kinetic energy term, we get this as the eigenvalue. If we now plot this, we get the double hill pattern. The cross section looks like this, and the constant energy contours, these are arcs of ellipse, which it should be. And it's also aligned along kx direction because we have a rotation of pi/4 here. So this one agrees with our DFT calculation. We take this further, try to fit this with our DFT results and get the values of mx star, my star, alpha and beta. So alpha and beta values are substantial, not huge, but much larger than, well, 2 orders of magnitude larger than strontium iridate, strontium titanate that was reported earlier. After this, we try to find the constant energy contours by equating the eigenvalue to a constant, and the roots of this equation will give us the constant energy contours. And we find the eigenstates. If plus minus is the eigenstates, it would be given as the normalization constant times plus minus a complex number zeta times the upspin kate and plus the downspin kate, where zeta is given by this complicated expression, and zeta star zeta becomes 1. With this eigenstates, we can now find out the spin projections. So if we find the expectation value of SZ operator within plus and minus states, both turn out to be 0. For Sx, expectation value within plus and minus, they are opposite in sign, and the value is this. For Sy, it is again opposite in sign, and the value is this, where this is a plus sign here, this is a minus sign here, which is the only difference. And if we plot the pseudospin directions now on the constant energy contours, it looks like this. So we can see that the spins are almost along the same direction here, reverses here at this junction, and becomes flipped here in this part. Same is true in the inner part as well. So we can see that the spins are a function of the polar coordinate phi in this system. Then we notice something interesting. We notice that there is also Rashba-like splitting in addition to iridium bands in titanium bands. These are titanium bands at much higher energy than the Fermi energy. These are empty bands. And if we plot the charge density corresponding to this band, we find it predominantly located on the titanium layers with hybridization taking place from iridium 5D bands. Same thing holds for here. For these two bands, we find that iridium gets hybridized with titanium bands. That means the spin orbit interaction is getting induced in the titanium bands because of the strong presence of iridium in the proximity. This is something interesting we find, and this brings me to the summary of the work. We achieved charge transfer. We confirmed charge transfer in the system. That means we attained a conducting system. Antiferromagnetism was confirmed, and that was in a two-dimensional conducting layer. We confirmed Rashba-like physics. We found strong anisotropic Rashba-Dresselhaus effect in the iridium bands, and we also analyzed it using an insightful model. Rashba-like effect is also induced in titanium bands, which can help designing more heterostructures with the proximity effect. Spin orbit torque may be present in this system. It may be tuned, and that is a hypothesis. We could not show that from our calculations yet. So this requires experimental verification, and the properties of this system can possibly be tuned by altering the gate voltage, applying some gate voltage. Therefore, this is a candidate material for antiferromagnetic spintronics.
Thank you, Nirmal. So hope you're done. Oh, okay, yeah, good.
Yeah, so I just wanted to acknowledge funding from ACRB India, help from HPC facility of IISER Bhopal and other facilities of IISER Bhopal, and our group is called TOM, Theory of Materials Properties. The paper is going to soon appear in Physical Review B. Thank you.
Thank you, Nirmal, for finishing up in time. So now we'll be open for questions. So I do not see any hands. So maybe you can quickly ask your question. Yes, Shashwata.
Hi, Nirmal.
Hi,
did you calculate the Rashba coefficient from DFT vis-a-vis the model Hamiltonian?
No, we calculated. So this is a complicated situation where right from DFT, it's difficult to calculate the Rashba coefficient. What we did is we fitted this model Hamiltonian as well as the DFT bands. And these are the parameters by which we could fit it.
Okay. But from K dot P, you can also calculate the Rashba coefficient, right?
Yeah, but then this complicated model has to be taken into account.
I see. Correct.
So that will lead to exactly the same thing, nothing different.
Yes, yes, yes. Okay, I'm done. That's the question.
Is there any more question? So if not, we will like to proceed because we have already started after time. So I'll request Professor Mukul Kabir to share his.
Yeah, I'll share. 1 second.
So the next topic is gate tunable magnetic ordering in two-dimensional materials by Professor Mukul Kabir of IISER Pune.
So is it visible? My slides are visible. Okay, so I'll make it full. I'll go to the laser pointer. Okay. So at the onset, like, let me thank the organizers for putting up the show online. So what I'll try to talk in next few minutes is how to tune magnetic ordering, okay, by electrical means rather than magnetic means. For various reasons that I'll discuss. So what would be the flow of the talk in next few minutes is that, like, it would be very customary to talk about Weinberg-Marming-Wagner prescription for magnetism in lower dimension and whether that's a surprise or not. Okay. And then I'll go and try to convince you guys that, like, for most of the 2D magnetic systems, a long range and anisotropic Heisenberg spin model is necessary and enough. And the third thing that's the most focus of this talk is how to manipulate this magnetism by electrical means. While I'll mostly focus on one particular example, or rather a celebrated example of this 2D magnets, which is CRI3, however, the arguments will be generic and applicable to large class of, if not all, a large class of other 2D materials too. So let me talk about the statements around this Marmin-Wagner theorem and whether having a magnetic 2D material is a surprise or not. So if you look into the statement very carefully, it talks about that if you have continuous symmetries, okay, that cannot be spontaneously broken at finite temperature. In certain systems where you have a sufficiently short range interactions. So if you think in this, these statements, basically the highlighted phrases, then you would expect that in certain systems where you have spin orbit coupling, which will lead to magnetic anisotropy, and then your continuous rotational symmetry of the spins will be broken. So that means in such systems, okay, this theorem is out of the question, and you may very well have a magnetic ordering. So in my opinion, although it took many years for people to realize it experimentally, which came in 2017 in these two celebrated papers, in my opinion, magnetism in 2D is not a surprise, because, like, if you have a spin orbit coupling, your continuous symmetry is gone. Also, another fact that one needs to take care is that in such systems, your short range picture might be not enough. So you may have a long range interactions. So that also is out of the purview of this theorem. So although it's the fast magnetic ordering was discovered in CRI3 and some other materials, there are many other materials at the moment which are discovered in last 3 years. However, there is one drawback, because, like, if you want to have magnetism, I said, like, you need to have magnetic anisotropy, and most of the time this magnetic anisotropy is small. Okay, that leads to a situation that, like, your ordering temperature is not that high, because it's far away from your Ising type of situation, because Ising type is the systems where your magnetic anisotropy is kind of infinity. So more often than not, in realistic 2D systems, you are going to expect an isotropic Heisenberg model, or maybe a weak XY type model. Then let me also give you a couple of experimental observations where this electrostatic manipulation of magnetism has happened. So first, let us talk about, if you take two layers of CRI3, they are coupled, and although they are ferromagnetic in plane, they are coupled antiferromagnetically between the layers. Okay, and if you make a device and dump electrons and holes by tuning the gate voltage, you see that at certain gate voltage, okay, you go from an antiferromagnetic interlayer interaction to a ferromagnetic interlayer interaction. Okay, so that means you are switching the interlayer coupling. So that means like you have been able to change the sign of the magnetic exchange coupling J. Also, in another experiment, okay, one shows that as I was trying to argue that like due to small anisotropy, your TC is very small. For this system is around 45 Kelvin. So by dumping electrons and holes, one can also tune the TC. Okay, so this yellowish line tracks the TC as a function of voltage, and one sees that for hole doping, this increases, the TC increases, and for electron doping, it has a opposite or contrasting effect. Okay. However, this has been experimentally observed. There is no microscopic mechanism attached or like understood as of yet. Then not only in CRI3, in other 2D materials also, it has been observed that by tuning the gate voltage, you can hugely tune the TC, because until you have a formidable ordering temperature, maybe it would be very difficult to use them in any practical purposes. So for this material, you can see that also you understand that if you decrease the layer numbers, your TC would decrease, because your interlayer J is decreasing. And you see that for a 3-layer of this system, your TC is of the order of 100K. Now, in some paper, they also showed that if you take this 3-layer system and if you dope electrons, now instead of hole, you dope electrons, because this is a metallic system. What you have been able to, this is although the behavior is non-monotonous, okay, you can see that your TC is increased from 100 Kelvin to more than 300 Kelvin. Okay, so so all this experiment tells you that although your TC is lower into the magnetic systems, there might be opportunity and tune it by electrical means that we see, and also at certain cases the overall magnetic ordering can be tuned. Okay. So now let us go and look into CRI3 or maybe CRX3. There are many other material, okay, where you can change the ligands. If you look carefully into the magnetic lattice, the CRI3 lattice is a honeycomb lattice. Okay, so you can very well write down an isotropic XXZ Heisenberg model where your Jx equal to Jy, but that is not necessarily equal to Zz. Okay, so you can so once you have that kind of situation, then you are introducing an anisotropic exchange term, and that anisotropic exchange term comes from the fact that your ligand is a heavy element, okay, and that has a very strong spin orbit coupling, and that induces a certain anisotropic exchange into the system. Okay, and that is very, very important for our discussion here. And you also have a single line anisotropy. Okay, so if you look into this term in blue, which is like your first nearest neighbor, because in honeycomb lattice you have, if you are considering the long range interactions, then you have first nearest neighbor, then you have second nearest neighbor, and then you have third nearest neighbors, and you need to write down your Hamiltonian, including all of them. Okay. So there are many attempts where people have used only first nearest neighbor, and in all cases they fail to reproduce the experimental results quantitatively, and in certain cases also qualitatively. And we'll argue that that is just because that, like, you have missed the second nearest neighbor and the third nearest neighbor terms, which makes the system complicated. So we see that these J's are isotropic exchange interactions, and these lambdas are the anisotropic exchange interactions, which are induced by the ligand spin-orbit coupling. So if you have a ligand where the spin-orbit coupling is 0, then essentially these terms becomes 0. Okay, and you have the usual on-site single line anisotropy terms. So the terms that we have neglected here are DM interactions, and we argue that in the systems your inversion symmetry is preserved, so the DM interactions will be 0. Okay, and we also have neglected the off-diagonal T-type anisotropic interactions, and we find that, like, those interactions, if you even consider, are very, very tiny compared to other anisotropic interactions. So it is fair to neglect them. And all the parameters of this Hamiltonian are calculated from the first principles. So once we calculate all the parameters from first principles and put it into a Heisenberg Monte Carlo, we see that like, your TC is of the around 43 Kelvin, whereas your experimental TC is 45. So this is the closest till now. Okay, but we also have shown that what is the importance of second nearest neighbor and the third nearest neighbor. So if you only have considered the first nearest neighbor, that you would have predicted a TC which is 29 Kelvin only, which is far below the experimental TC. If you take J1 and J2, then you will end up overshooting your TC by 10 Kelvin. But if you consider the full picture of J1 and J2 and J3 and lambda 1, lambda 2, lambda 3, then you are able to predict your TC very close to the experiment. So here is the experiment, like, where they measured the TC by the car rotation, and you see, like, you have a transition temperature around 45. I mean, we also make some brief comments that the magnetic order parameter that we have calculated from here is around like 0.24. Okay, and the experimental order parameter, which has been measured from inelastic neutron scattering, which is of the order of 0.25. Okay, so we match very well with the experiments. Now, in comparison to the Ising model, okay, you would understand, I mean, why I'm talking about Ising model, because for a long time, people thought that this type of systems can be represented by Ising Hamiltonian. So the order parameter for 2D Ising model, you know that this is 1/8, which is far away from what we get. Okay. And also, I'd like to make a brief comment that if we have considered this system to be Ising, and then these J's will give you a TC which is humongously higher than the experiment. Okay. Also, as I'm trying to that in the anisotropy interactions. Okay, so that means like you can understand that picture. Oh, okay. Okay, so I'll first. So if you see that, like if you do a spin wave analysis, you will see that your if you have anisotropy, that opens up a gap at your gamma point, and we have calculated that gap to be 0.53, which is very well reproduced within the experimental numbers, which is like 0.3 to 0.4. Also, like, as I said, that I will talk about why this get voltage and how this get voltage tunes the TC. So I'll spend few more minutes on this. First, I'll show the gross result that if you dope hole into the system, your TC kind of monotonically increases, and it can increase as much as 5 times from 45 degree Kelvin to around 230 Kelvin. However, if you dope electron into the system, the TC goes down, which is exactly what experiment has told us. But the microscopic mechanism were not understood. So now I'll tell you the microscopic mechanism, microscopic picture here. Okay. So as you dope hole, your J1 and J2 initially doesn't increase much, but after a critical density, it shoots up very rapidly. Compared to that fact, your J3, which was initially antiferromagnetic, also increases and becomes ferromagnetic and keeps on increasing. Okay. However, for the electron doping, your J2 and J3 has a contrasting effect. One increases, one decreases, and J1 also decreases with electron doping. And if you look into all the anisotropic interactions, that has a very complex behavior. Okay, and so I'm not going to talk about all this behavior here, but you should point out that like after a critical density, which was otherwise an easy axis magnetic system, becomes a kind of easy plane magnetic system or a weak XY type of systems. So you should remember here that as you change your carrier doping, that alters your orbital occupancies, and that also changes your local and orbital moments, and that in fact changes your on-site spin orbit coupling energies. It also induces certain strain into the lattice, but that does not affect the TC. So this is kind of overall talks about the microscopic picture, what is happening on your observation, that like TC increases with hole doping but decreases with electron doping. And I'll also try to argue. So this is going to be this is the last slide, Amita. Okay, so I'm just finishing it. This is last one. Yeah, so I'll give you a qualitative orbital picture also. The neutral system CR has T2G3 EG no electron. So this is the picture. And if you look into the mechanism, then your T2G interaction is antiferromagnetic, whereas your half-phase T2G and MD-EG interaction is ferromagnetic. So in the neutral system, this interaction wins over. That can be shown. I'm not showing here. That wins over the antiferromagnetic interaction, and the system becomes ferromagnetic. Fair, this is understood. Now we can tentatively also understood that once you dope hole into the system, that means like you are partially doping a hole into the T2G system. So that leads to which was your antiferromagnetic interaction T2G that gets destabilized. Okay, and as an effect, you get a stronger ferromagnetism. Okay, and if you increase your hole doping, then your partial T2G hole also increases in density. So your AFM destabilization also becomes stronger. So your TC increases. So this is a kind of qualitative picture. What happens in the electron doping is that you once you dope electron into the system, then you introduce certain partial charge into the EG its EG orbital. And due to that thing, your T2G EG interaction now also has an AFM component. So your overall AFM interaction destabilizes, and that leads to your weaker TC. So this is the summary that, like, you need to think about anisotropic Heisenberg model, and you need to consider all the long range interactions possible. And weak anisotropy leads to low ordering temperature, but your carrier doping is a very interesting way to manipulate magnetism here. And as I said, that, like, this Hamiltonian and the results that I have showed you for CRI3, but we have also other results, and we strongly believes that this picture is applicable to many other 2D magnets. And that's all, and thank you for your patience. Yeah.
Thank you, Mukulda, for finishing overall in time. So we'll quickly have 2 questions, maybe.
Hi, this is Anamitra Mukul. Can I ask a quick question? So
Yeah,
just a clarification. So in the second last slide, when we were looking at the whole doping picture, the T2G was, so doesn't this make the system metallic? I mean, the Fermi level would lie where now? I mean, just to understand.
Yes, it's a very good question. So for hole doping and electron doping, and for both cases, right, your system will become a little metallic, but your it will become metallic, and then putting up this qualitative picture is a little difficult there. But it becomes metallic, but it's very bad type of metals, because, like, your density of state at the Fermi level is very, very tiny. Okay.
So DFT, I mean, if one were to do a DFT, you will find a very narrow band at the Fermi energy. Is that the statement? I mean, which would make that in presence of any sort of other interaction, it will make a sort of bad metal or.
So what I can tell you, it becomes metal with a very tiny density of state at Fermi level.
I see. Okay, sure. Thank you.
So another question from Yogendra.
Yeah.
So, what is the electron-electron interaction role in these materials? Do they play any?
So electron-electron interaction. I mean, what do you mean?
I mean, you are concentrating on the magnetic phases and all, but
so electronic interactions are considered. Okay. And without electron-electron interactions, like, I mean, nothing would happen, right? So the electron-electron interaction here are also supplemented with a Hubbard U. Okay. So, and you need to be, with the interest of time, I didn't talk about that. So the Hubbard U and the spin orbit coupling plays a humongous role here. Okay, so you need to be very careful that what type of Coulomb interaction you are putting on your electrons.
Do you have any reference to that kind of things?
So we have our own results, which we might share with you offline. Yeah.
Okay, thank you.
Yeah.
So there is one more question from Amit Agarwal, but Amit, you have to be quick.
Yes, Amit.
Sorry. So this is a bit technical, Mukul. So how do you choose the value of U?
Okay. Very interesting question.
In the DFT calculations?
Yeah. So you need to be, so there are 2 things. One is you do various calculations and you see that where is your sweet spot, A. And B is also your some physics understanding that, like, if you are having an element which has a high Z, like as a ligand, like, iodine, okay, then your this interactions is kind of weak, and you have a shallow D and all these things there. So so iodine and chromium, if you have this type of systems, then you can guess that your U should be a much lower. Okay. Not on the higher side. It should be around, like, 0.5 or 1. But what is the sweet spot? For that, you need to do a calculations. But you can also understand from a from orbital picture that where your U can be. So you have two things, you have two ways. One is your physics understanding, and the B is like, you go and do some calculations to understand that what can be your good U. So we have done a series of U calculations, and we find that indeed for this system, U is 0.5 eV.
Okay, Mukulda, I think like we are running out of time, so we'll just go over.
Sure.
Yeah. Okay.
So I'd be very happy to take other questions offline,
Yeah,
if someone
surely,
has.
surely.
Yeah. So I have to unshare.
Yeah, unshare, yes. So next speaker is Shumanti Patra. So Shumanti, can you start sharing?
Yeah, but it's still showing the previous slide. So
Yeah. So yeah, after he unshares, you start sharing.
Yes. Sorry.
So our next talk is Shumanti Patra from SN Bose, and she will be speaking on flat bands in transition metal dichalcogenides. When and how do we have them? So that is the title of the next talk. Shumanti, now over to you. Can you try to share?
Is it now visible?
Yes, yeah, visible. Can you try to make it full screen?
No, it's not coming.
Oh, yeah, it went.
Now it's
it is full screen also. So yours is 10 plus 2 minutes, right?
Yes.
So I'll remind you from 8 minutes.
Okay. Hi, this is Shumanti Patra from SN Bose National Center for Basic Sciences. I'm pursuing my PhD under the supervision of Professor Priya Mahadevan. Today, I'm going to present my work on flat bands in twisted bilayer transition metal dichalcogenides. When and why do we have them? Okay, it's not moving. Okay, so we know that transition metal dichalcogenides are well-known layered materials, and in each layer, each transition metal atom is connected to 6 of the chalcogen atoms and forming a hexagonal patterns like this. Nowadays, scientists could exfoliate these materials layer by layer, and it is possible to get monolayers of this material. Now, when one takes one monolayer of the material and put it on the top of the other monolayer, but in a slightly rotated manner, we end up getting the twisted bilayers of this material. Now, moving on to the motivation of our work. We recently so many new physical properties have been reported for these twisted bilayer structures. For example, ultra flat bands are observed for magic angle twisted bilayer graphene. Superconductivity and Mohs physics, those are observed in twisted bilayer graphene. And recently, superconductivity is also observed in twisted bilayer transition metal dichalcogenides at low for small angles. Now, all these properties are only seen in the twisted structure, but are not seen in their untwisted limit. This is making the twisted structure interesting. Now, what happens when one twists the upper layer with respect to the lower layer? So the periodicity of the system changes, and we end up getting large unit cell, which could be commensurate or incommensurate depending on the angle of rotation. And as a result of this large unit cell, the bands get folded to a significantly reduced brilliance zone. Now the question is, should we even talk about the band structure in such a reduced small brilliance zone? So to understand it, we understand the electronic structure for different twist angle. We try to figure out if any kind of simplifications are possible or not. Before we jump on to the analysis of the electronic structure of the twisted bilayers, we will first, I'll first draw your attention on what we know about this material in their untwisted limit. So we know that the most popular technique to separate these materials is Scotch Brite technique, and which is also implying that there is a weak interaction between the layers of this material. And this is also reflected in the band structure of this material. And here I have plotted the monolayers and bilayers band structure both for one of the member of this family, which is MOSE2. And this black line is showing the bilayers band structure, red line is showing the monolayers band structure. Here one could see this along different direction between different high symmetry points. The changes in the band structure when one goes from monolayer to bilayer is pretty small, and which is suggesting that the effect of the one layer on the other layer acts as a weak perturbation. So now even if the changes are small, we need to figure out what is responsible for these changes. So for doing this, we mapped it onto a tight binding model for both. So for both monolayer and bilayer, we calculated the ab initio band structure showing by the black lines, and we tried to fit it with a tight binding model showing by the red dotted line. So for both the cases, we got good fitting, and from this fitting, we extracted the tight binding hopping parameters from here. And the good thing about the tight binding model is that we could selectively switch on or switch off any of the hopping interaction strength we want, and we could see what is the effect on the band structure. So that's what we did. We took the bilayer's band structure and we selectively switch off the interlayer hopping interaction strengths only, and we superposed it with the monolayer's band structure. Here the black line is showing the monolayer's band structure and red line is showing the bilayer's band structure, but with the interlayer interaction switched off, and we're getting the monolayer's band structure back. So from here we conclude that the changes in the band structure when it goes from monolayer to bilayer is solely due to the interlayer hopping interaction strength. Now we are going to use those facts for our further analysis of the band structure of the twisted bilayers. Now I'll discuss one more thing, that what happened when we take a large unit cell or a supercell for our calculation. This is an example for a simple example with a gallium arsenide. So here the left column is showing the band structure of a gallium arsenide primitive cell, and the right column is showing a band structure of a gallium arsenide supercell, where we have taken unit cell size is a double of the primitive cell size. So here we could see that the bands are getting folded and extra bands are coming in, and the dispersional width of the band is changing. But this shouldn't be the case. Our band structure shouldn't be dependent on the size of the unit cell we are choosing. So from this structure, so if we calculate a large unit cell, from this structure we need to extract the primitive cell band structure to understand the actual properties of this material. So for doing this, we basically one needs to unfold the band structure, or in simple word, one needs to project the band structure in the primitive cell band K points. So for doing this, we calculated the spectral weight, which is given by this pKa. This is basically the weight of the set of the primitive cell states, small kin, contributing to the supercell state. And by doing this projection, what we got, we have shown is here is in the right panel. So there we are getting our primitive cell band structure back. So here the supercell is the exact supercell, and we're getting exactly the primitive cell band structure back. Now, how do we reconcile all these ideas to understand what is happening in the large unit cell of the twisted bilayers? We'll discuss that. So our discussion will focus on MOSE2, though our ideas are more general and valid for all the MO and W based transition metal disulfosides. So I'm showing a data for the large twist angle 19.03, where the primitive unit cell size is very large. It's around 16 times of the primitive unit cell size. And here with this unit cell, we relaxed the structure, we calculated the band structure, and is showing as shown in the previous slides, we projected this band structure in the primitive cell direction. Now, for our case, we don't have a perfect supercell, but we previously discussed that for this material, that interlayer interaction strength acts as a weak perturbation, and twist adds on a modification to this weak perturbation, which is even weaker. So our idea is to figure out that after projecting this band structure on the primitive cell K points, how much it's getting deviated from the band structure of its untwisted limit, and which will give us a measure of the effect of the twist on the band structure. So this is the unfolded band structure, or after projecting out the band structure, what we get from the 19.03 degree. So here we could see that properly dispersing bands are coming here. And to understand in a better way, we superposed it with a band structure of a untwisted bilayer, which is given here by the black line. And from here, we could see that in spite of the unit cell size is very large, we recovered the primitive cell band structure here. And most importantly, no flat band is emerging here. So the question is, so the low energy electronic structure is always going to be similar to the primitive cell one. So to understand it, we also considered the small angles, where the angle is 3.48 degree. So here the system size is also similar to the 19.03 degree case. And here we found something interesting. At different regions of this unit cell, we found that there is a patches of different high symmetry stackings. At the corners, we got patches of AA stacking. At the middle, we got patches of AB prime stacking. Now, what is this AA and AB prime stacking? To understand this, we should move to the next view graph. Here I have shown the 5 possible stackings for these bilayers of MOSE2. And suppose and depending on the orientation of the upper layer on with respect to the lower layer, the interlayer separation changes. Suppose for the A stacking, the AC atom sits exactly on the top of the AC atom, so repulsion is high and the interlayer separation is higher here. And for A prime or 2A stacking or AB stacking, this is not the case and the interlayer separation is low here. And this thing is also reflected in the structure when in our structure when we relax this unit cell structure, we could see that the interlayer separation is very high at the corners.
Last 2 minutes, Shumanti.
Okay, it's 3.74 angstrom at the corners, and it's going minimum 3.18 degree at the center. So there is a large variation in the interlayer separation of this structure, and we calculate the band structure with this unit cell, and we projected it on the primitive cell direction and sorry. Okay, primitive cell direction, and this was what we got actually. So here also we could see that the dispersing bands are coming in here, but when we zoom on the top of the valence band, we could see that the primitive that the splitter band is emerging here, and this band is not connected with the rest of the bands below, and this band has a dispersional width of 19 MeV. So we thought that the modulation in the interlayer separation that could cause this emergence of the split up band. So this time we take the same unit cell, but we kept the interlayer separation fixed and calculated the band structure. So here also we could find that a splitter band is emerging here. So the variation in the interlayer separation is not playing the role. So to understand it, we plotted the histogram, we count of the interlayer selenium distances, and we for the 3 of the cases 19.03 degree optimized and 3.48 degree with fixed interlayer separation and 3.48 degree optimized interlayer separation. But the last case we found that there is a huge count at the short interlayer selenium distances, but for 3.48 degree and 19.03 degree, both the cases is randomly varying. But still for the 3.48 degree fixed interlayer separation, we are getting a split up band. So this is not playing the roles. To understand what is playing the role, we now we plotted the spatial profile of it. Like we here connected all the shortest set of the selenium distances which are less than 3.8 angstrom. So for both the cases, for the with the relaxed structure and the unrelaxed with the unrelaxed structure and the relaxed structure, for both the cases we see that the shortest set of the selenium distances, those are concentrated at the particular regions of the unit cell. So those are particular regions of the unit cell. And when we plotted the same thing for the large twist angle 19.03, we could find that the shortest set of the selenium distances, those are randomly distributed over all the unit cell. So and which is not the case for the small angle 3.48 degree. So from here we conclude that the subband formation emerges from the concentrated regions of the enhanced interlayer interaction strengths.
Well, the time is over. So
okay, so I'll just conclude then. So for large angles, the electronic structure is similar to the untwisted bilayer, whereas the small angles electronic structure deviates from the untwisted bilayer's band structure, forming subbands. The structural relaxation needed to get the correct character of the subbands, and the concentrated regions of the enhanced interlayer interaction strengths lead to the subband formation for twisted bilayers. So I'd like to thank my supervisor, Professor Priya Mahadevan, my senior Poonam Kumari, and other groupmates, and thanks to the organizers for giving me the opportunity to present here. Thank you.
Thank you, Shumanti. So we will be open for questions now.
Hi, Amrita. This is Ashish. Yes. I have one quick question.
Yeah, go ahead.
So this is regarding this unfolding of this thing. Is it possible to have the superlative nature you can find out during this unfolding?
Superlative nature means that. So I didn't get it actually.
Hello, Ashish.
Yeah.
So you have to probably elaborate your question to her.
Okay, so it means the superlative, if you do, when you rotate this one, then could be possible that from top that you can have a superlative structure.
Yes.
Okay.
Yeah.
So this superlative structure, once you have the superlative structure, so that information will be embedded in your band structure.
Yes.
So can you just get information of those structure when you basically unfold those bands?
Yeah, I mean that's what we have done. We From this structure, we started our calculation. So for the large unit cell, we have a very reduced Brilliant zone get reduced, and the bands are getting folded. So we don't have the actual information. So everything looks very flatter. So with this eigen's functions of this band structure, we projected onto the primitive cells K points, and then we find out that then we find out this unfolded band structure actually.
Okay.
Over here.
Okay. So we are already running behind schedule. So I request, Shumanti, thank you for your talk. So I request you to unshare. Yeah, the next speaker is Arnab Mukherjee. So Arnab, can you share?
Yes, I'm sharing. Hello?
Yes, go ahead.
Hello?
Yeah, we can hear you.
Hello? Okay.
Yes, Arnab, we can hear you. So can you speak? Yeah, can you hear us?
Hello everyone. I am Arnab Mukherjee, and today I'm going to present our recent archive paper on antiferromagnetic Skyrmion and Skyrmion density wave in Rashba-Hunds insulator. So this is my outline of my talk, and these are our recent works from our group. So Deepak has already presented his talk about this paper. So now today I'm going to present about our work in this archive paper. So magnetic skyrmion are a class of topologically protected objects observed in chiral magnets. So they have very promising behavior for the use in the technological sense and the use in the spintronics devices. So like they are very weak, they have very weak sensitivity to the defects and very low current density, critical current density, and high topological skyrmion conductivity, high topological Hall conductivity, etc. So, but they have also a drawback, like they suffer from skyrmion Hall effect. But in the case of antiferromagnetic skyrmions, this SHE is not there because these antiferromagnetic skyrmion are composed of superposition of two ferromagnetic skyrmion of different opposing topological indices. So the Magnus force gets cancelled exactly. So they don't have a transverse velocity component, these antiferromagnetic skyrmions. So in this work, we have explored the Rashba coupled Horn insulator as a potential candidate for realizing antiferromagnetic skyrmion, even though these the Mott insulating state, the same idea can be also applied to Mott insulating state. So I'll start with the microscopic model Hamiltonian. So here we have taken the Rashba induced ferromagnetic control lattice model. The Hamiltonian has this form, and here T is the tight binding hopping parameter, lambda is the Rashba spin orbit coupling strength, and JH is the Kondo coupling strength. So we have used a unitary rotation operator, so under which the electrons, fermions, lattice fermions, the spin orientation of lattice fermions gets parallel and anti-parallel to the local spin moments. And the transformed Hamiltonian has this form where we can see that the Kondo term gets diagonalized, but in cost of a complicated projected hopping amplitude, which has contribution from tight binding part and also from Rashba part. So this is a schematic diagram of one of the virtual hopping that can be there under this model. So namely the parallel to anti-parallel hopping. And so when JH is too large and at half filling case, we can easily see that the ground state is an insulating state, very much like Mott insulating state. So in this situation, it is sufficient to work with just two sides and the problem reduced to two sides problem. So here we have dropped the summation over all the side indices. So so the Hamiltonian now have a look like this. So here the J, we can treat the JH as the original Hamiltonian, and this hopping term can be treated as the perturbative term. So the first order perturbation correction, energy perturbation correction is 0. We have checked that already, but the second order correction has this form. And after some algebra, we have arrived with this closed form, classical super exchange model form. So one can check our archive paper, the supplemental of our archive paper for the detailed calculation and the derivations. So, so here I'm going to present our result on this model. So this is the phase diagram. So, okay, so I should also mention here one thing. So this, we have parameterized T and lambda as a common parameter alpha. So like T0, alpha 0 means T1, and so alpha is 1 minus, T is 1 minus alpha, and lambda is alpha, something like that. So in this phase diagram, we have some very trivial phases like antiferromagnet, single Q, spin stripe, FM, and of course paramagnet. We have also have this antiferromagnetic string-like structure and antiferromagnetic Skyrmian lattice structure. We'll see the spin configuration in the later on. So all these boundaries, phase boundaries, has been drawn by the help of component resolved structure factor. Here we can see the component resolved structure factor as a function of temperature. So in this panel B, this is the structure factor evolution of all those phases. So in the panel B, we can see that there is a circular pattern about pi point. It is very similar to what we have already see that in Deepak's talk. So here, after getting that interesting and exotic phases from zero Zeeman field case, so now we are interested in also the effect of Zeeman field. So here we have a phase diagram between Zeeman field and alpha. So here we can see that this CAF is the canted antiferromagnets because of the Zeeman field. And on top of this antiferromagnetic string, we get a sparse anti-Skyrmian state. This was a new state after applying the Zeeman field. And also on top of single Q and antiferromagnetic Skyrmian lattice, we see a exotic Skyrmian density wave state. So here also, to draw these boundaries, we have used the Z component of the magnetization, the total Skyrmian density of the spin Skyrmian density, and also the pi component of structure factor. So after discussing all those results, so now we should also validate our model. So we to validate our model, we have energy comparison, energy versus 1 by JH. JH is the Kondo coupling strength between the original ferromagnetic Kondo lattice model and the classical super exchange model, of course, in presence of Rashba spin orbit coupling. So we can see that these two models matches PT well up to 0.2, 1 by JH 0.2. So this is the spin configuration. This from all our calculation results part phase diagram. So this is a phase, so antiferromagnetic string-like structure. We can see some domain-like structure here. And if we switch on the Zeeman field, then we can see that these Skyrmians are emerging. this sparse fermion are emerging. So this, when we have relatively large alpha value, these strings are getting narrower here, and so this narrower string-like structure give a more denser fermions, but of smaller size. So this is the antiferrometric fermion lattice. Alpha is equal to 0.6 without field, and this is the fermion density wave states. So this G and H panel is the fermion density map plot for fermion crystal lattice and this fermion density wave states. So in this H panel, we can clearly see that this is a diagonal stripe of positive and negative modulating positive and negative values, and this inset shows that the structure factor of this map plot, this fermion density map plot. So this is the structure factor of this map plot. So here we can see that this we have a finite QQ peak, which is not sitting at 0 or pi. So we can conclude that this is indeed a fermion density wave, but we need to also explore more about this state. So here in my conclusion, the derivation of classical super exchange uncovers an elegant analogy with the effective spin model, effective quantum spin model originating from the smart insulator. So all those ideas what we have used in these problems, these ideas can also be used in case of Mott insulating state. Hund's coupling can serve as a proxy for Hubbard interaction for the purpose of understanding influence of spin-orbit coupling on magnetic ordering, similar concept. And this we have got some exotic spin structure out of our model. These are antiferromagnetic string-like structure, antiferromagnetic fermion lattice, and the fermion density wave. But still, I would say that this fermion density wave state needs to be studied more properly, and we are also working on this now. The key ingredients to realize that antiferromagnetic fermion lattice or antiferromagnetic, the formation of the antiferromagnetic fermion, we propose that this key ingredient are like Hund's coupling and Rashba spin orbit coupling, maybe also Mott insulating Hubbard
Arnab,
model
your
with
time's up.
spin orbit coupling, like that. So these Hund's insulator and Mott insulator, these are natural model to realize in the multi-orbital system like 4D and 5D elements. So this concludes my talk. Thank you.
I think he cannot hear us, so he won't be able to answer any question, I suppose.
Hello.
So he's not able to hear us. So
hello.
Yeah, Arnab, you are not able to hear us, so we will go over to the next candidate.
Hello. Hello. Okay.
Hi Arnab, can you hear us?
Yes, I can hear you.
Okay.
So can you hear?
Yeah,
Yes.
but
Can you hear me?
12 minutes is well past, and you could not hear us for a long time. So
Oh, sorry. Actually, I couldn't hear. Sorry, maybe
Okay,
some
so
technical
you
problem.
can
Sorry.
go for the next talk then.
yeah. So maybe like
sorry.
one
I'm extremely sorry.
quick question. Maybe we can still go ahead with, and then we will move ahead with the next one.
Yeah, sure. Yeah, sure. Go ahead.
So maybe then I can ask one question, quick question.
Yeah, sure.
Yeah, sure.
So in your this antiferromagnetic fermion, that one, how did you choose your DMI and your? Is there any DMI?
No. So there is no DMI interaction
It's the electronic
built.
model from.
So the model actually in my Hamiltonian,
I may
the
miss that
DM-like
part.
interaction are emerging. Hello.
Yeah.
So the DM-like interaction are coming naturally from our starting Hamiltonian, which is the Kondo lattice model in presence of Rajba. So we didn't start with a particular DM-like term per se.
But did you check that it's the symmetry of this DM interaction, because it's a square lattice, right? And as per I see that your and this fermion looks like a Niels fermion. And
Yeah, that's true.
and
Niels
did you check the
Fermion.
symmetry of the DMI, that whatever the emerging DMI comes?
No, not that. But these are not Niels fermions. If you look closely, if you go to the paper and look closely, these are not Niels fermions because of these Niels fermion. Yeah. So if you just separate two sublattice, then it will look like two Niels fermions. But when you overlap these two sublattices, it is not actually Niels fermions. So if you go and check the paper.
Oh, okay.
There.
Yeah, I think
Maybe the spin configuration are not clear here.
Okay.
Yeah, we are well past the
Yeah,
time,
thank
so
you.
we will go ahead and finish up with the last speaker of the day, right, of the session. So Sujoy Rai from IISc. So, and he will speak on a hierarchy of multi-order Skyrmian phases in twisted van der Waals magnetic layers. Sujoy, over to you.
Yeah. Am I audible?
Yeah, perfectly audible.
Hello?
Yes, audible.
Okay. Thank you. Yeah, I'd like to. Yeah, I'd like to thank the organizer for giving me the opportunity to talk about my work, which is a hierarchy of multi-order Skyrmian phases in twisted van der Waals magnetic layers. So as this is a short talk, I'll not go to the details of Skyrmions. I'll just show you this figure. This shows a Skyrmion lattice, and these Skyrmions are topologically stable field configuration. Here the field we are taking spins, and if you calculate the topological number which is given by this term around this structure, you will have a non-zero integer. So now we'll go to ask the question, what happens in bilayer system? So suppose this is a bilayer system and the bottom layer is a substrate layer where all the spins are pointing upward. And on the top layer, we have a Skyrmion lattice. So here you can see at some region, which are given by these red arrows, we have ferromagnetic interaction. At some other regions, which are indicated by these blue arrows, we have antiferromagnetic interaction. And this kind of spatially varying interlayer interaction is very important to get Skyrmion in bilayer system. So now we'll go to a different picture. So this is a Moire bilayer system. So here you can see in the Moire bilayer system, in this central region you have AA stacking, and at some other region you have AB stacking. So the stacking order varies with position. And it turns out that this spatially varying stacking order gives rise to spatially varying nearest neighbor, and which in turn gives rise to this interlayer, spatially varying interlayer interaction that we are looking for. So guided by this observation, we write our spin Hamiltonian for this system, which is given by H1 and H2. And this H1 is the intralayer term and H2 is the interlayer term. So this intralayer term it consists of a Heisenberg exchange term and a z-axis asymmetry term. So this z-axis asymmetry favors the spin alignment in z direction. And this interlayer interaction, which is important, this consists of a Heisenberg exchange. And in this Heisenberg exchange, the coupling term is spatially dependent because of this Moire pattern in bilayer. And also we have a dipole-dipole term, which is also spatially varying because of this R dependence. And this R is coming from the Moire pattern formation. So we incorporate this Hamiltonian and do a Monte Carlo study to get the ground state spin configuration. So here I discuss the results of our simulation. So this is the phase diagram that we got from varying two interlayer parameters. So here we have this intralayer coupling term J parallel, interlayer exchange coupling J perpendicular, which is, as I told earlier, it is a spatially varying function, which can be written as J perpendicular as a constant term times a function. And this function is a periodic function, which has the periodicity of the Moire lattice. And we also have a interlayer dipole coupling term, JD. And in this phase diagram, we varied J perpendicular from negative to the positive values so this is from ferromagnetic to antiferromagnetic regime. And JD is always greater than 0 as standard dipolar coupling term. So we can see here we have 5 distinct topological phases with topological number varying from -1 to 1, which is given by this term, where n is the ground state spin configuration. And all these phases, these 5 phases has distinct topological characteristics, which should be clearer when we look at the local topological charge density distribution, which is given by this rho xy term. And this rho xy is the integrand of this integration. So now let us look into let us look into these topological non-trivial phases 1, 3, and 5. Let us look into phase 1 first. This is the spin configuration we got from our simulation. So as you can see here, it represents a spin bubble term where within this circular region, all the red spins are pointing upward and all the green spins are pointing downward. And in between, we have the spin canting happens in this thin circular region, which forms the block wall. This should be even clearer if we look into the Z component color plot, which is given here. This white ring is the block wall. And as a result of this thin block wall, if we look into the topological charge density, this is concentrated around this ring. And this is very similar to the d orbital electron probability distribution of H atom. We just draw this analogy. We did not do any angular momentum analysis. So as we go along, we'll find more such interesting analogies with hydrogen atom. So next move on to phase 3. And this is the spin configuration. Again, the skyrmion structure appears at a different position. Here you can see. This is the Z component. And if you look at the charge distribution, you can see it does not have the circular symmetry. It breaks the circular symmetry, and the distribution is rather in a dumbbell shape like fashion, which is similar to the p orbital distribution of H atom. And now the phase 5. This is the phase 5. As you can see, it has a very nice skyrmion structure. The structure appears at the same position as phase 1, but the polarity is opposite. And not only that, now we have a very thin region where the spin canting happens, and it forms a very white block wall. So we have this block skyrmion lattice phase in phase 5. And if you look into the local charge distribution, the charges are concentrated around these point-like centers, and which is again have an analogy with the s orbital of H atom. Now I'll briefly mention about phase 2. In phase 2, we have this one-dimensional stripe order, and this is a topologically trivial phase because the total topological number, the charge is 0. But if you look into the charge density distribution, there are some interesting things. So you have these point-like charge centers, which consists both of negative and positive charges. And this kind of charge centers can give rise to a finite moment in the system. So to look into that, we zoom into our charge centers. So we have this charge center which forms out of this skyrmionic structure here, and the other charge centers are formed out of anti-skyrmion structure. So if we treat these charge centers as our electric electric point charges, then we can apply the Gauss law to extract the field lines similar to the field lines in EM theory. And the field lines suggest that there are dipole formations, which are given by these red and blue arrows. And now if we look into the whole lattice, we can see the dipoles are oriented in a nail-like order. And so we dubbed this phase as topological anti-ferroelectric phase, which are made out of dipole of topological charges. So
Last 2 minutes.
I'll conclude.
Yeah.
I'll conclude. So in conclusion, we analyzed a bilayer spin system to get the skyrmion, which naturally arises from interlayer Heisenberg and dipolar interaction. And we also have found skyrmionic charge distribution, which are very analogous to the hydrogen atom orbital electron charge distribution. And we also found a novel anti-ferroelectric phase, which are made out of topological dipoles. And we also studied spin orbit and Dyson-Schimoria interaction, which we found not significant as long as their values are small. But there are some effect of Dyson-Schimoria interaction, which I have not discussed here. Yeah, thank you for your attention.
Okay, so we will be open for questions now. Thank you, Sujoy, for finishing up in time.
Hi, Sujoy, can I ask one question?
Sure.
Yes.
Yeah. So in the last slides where you showed this is dipolar thing, if I look at this, mainly the first phase to that first figure, so it's if you calculate the topological charge, did you get any plus up or minus up state there? Topological charge plus up.
The numbers are I don't remember the numbers, but
because it looked like
exactly,
to be a mirror pair.
Yeah. I can understand what you are asking. But the charges, I don't think it is exactly half.
And also this this Meron pair, it generally comes. So if you look at your phase diagram, if I correct that, you are going from Q equal to +1, 0, and -1 state, and it is a kind of continuous deformation there. Okay, and then it generally happens that if it is a continuous deformation, so it can go +0 and then minus up, and +1 to 0 and -1. Then in between we can Meron pair. So it is also happens if you switch the skyrmion from +1 to -1 state.
Yeah.
There is a paper in the scientific report paper that you can look at it. There also it's mentioned that but during that time we didn't say those are Meron pair, but those are topological charge plus up minus up, and you can get it. That's so switching from +1 to -1, you can get the Meron pair.
Okay. Yeah, then I'll look into this number of these charge centers.
No, I'm surprised that why you are didn't call it as a dipole or something. Okay. Okay, but it's a new name.
Okay. So I called it dipole because of basically due to this field lines, which shows dipolar kind of field lines.
Then what about in between this dipolar field? This is a topological defects. The two dipoles, there is another
this. Yes. Yeah. So there we can think of it is so there can be another dipole, opposite dipole in these regions. But I mean, we call it dipole because of this field, basically. Yeah.
Okay. Okay. Okay.
Okay. Any other question for Sujoy? Maybe one quick one. Okay. If not, then I think we will conclude this session. So I thank all the speakers for giving such excellent presentation, and then we will again come back with the next session.
Yeah, so I thank you, Amrita, and also all the speakers in this session. And so we'll start from 2 o'clock. Okay?
Okay, thank you very much. Yeah.
Thank you.
Over to you, Ganesh. So Ganesh, this is 25 minutes.
Yes.
So I'll give you a, warning at 20 minutes.
Sure, please.
Okay.
Yes.
Yeah, good.
Good.
So
Okay.
that's
Thank you.
25
Thank you,
minutes,
Shubhro.
including, that's 25
Questions,
minutes, including question time. Okay. Yeah.
Yes.
Okay.
Yeah, sure.
Okay.
So thank you to the organizers. Thank you, Chair. Thank you, all of you, coming after lunch. So I'll talk about order-based singularity. So this is a concept that we've been developing over the last couple of years. So it's presented in these 3 papers, and these are written with a combination of these co-authors: Shubhankar, my student, Professor Bhaskaran from IMSc, summer student from Pilani, BITS Pilani, and Professor Deeptiman Sen from ISC Bangalore. So I'll go ahead and I'll start with a principle. So I'd like to make this case first, that any magnet at low energies resembles a single particle that moves in the space of all classical ground states. So this is a grand statement, and this can be rigorously shown in certain cases. So let's not go into the details now, but we believe it's true in general. So I'll show you some examples, or I'll show you one example of this principle, and then I'll show you some very interesting consequences of this. So let me first show you what I mean by this. So any magnet at low energies maps to a single particle problem, where the particle is moving on the space of classical ground states. So let me show that with a very simple example, just 2 spins. Let's take a very simple magnet with 2 spins. So spin 1 and spin 2. They're coupled by an XY Hamiltonian. So just 2 spins coupled. And we can immediately guess the classical ground state for this. Right? So to minimize the classical energy, I should take the 2 spins to be classical vectors. They should both lie in the XY plane, and they should be anti-aligned with each other. Right? So I fix spin 1 using some angle phi, then spin 2 is opposite to it. Right? So let me now ask, what is the set of all such classical ground states? Right? So that simply corresponds to changing this parameter phi. So making spin 1 pointing in some other direction and spin 2 having spin 2 pointed in the opposite direction. So the set of all such states is parameterized by a single angle variable. So it's actually a circle. So according to the principle that I just read out to you, the low energy physics of this magnet, 2 spins, should map to a particle moving on a circle. So let me show you some evidence for this. So this is exact diagonalization of precisely this very simple magnet, this very simple Hamiltonian. So it's done for various S values, where S is a spin quantum number. For now, just take one particular value of S. Let's say spin 9, S9. So we take this Hamiltonian for spin 9, diagonalize it, and this is the low energy spectrum. Okay. And so the y-axis is the energy, because we shift the energy by some constant and divide it by some scale. Not too important. But at the end of it, you see what the energy looks like. It has a remarkable form. It has a non-degenerate ground state, doubly degenerate excited state, more doubly degenerate states all the way. And if you look at their energies, they're 0, 1, 4, 9, 16, 25, 36. So this is precisely of the form n squared, where n is an integer. And this is precisely the energy spectrum of a particle moving on a circle. So this, I claim, is evidence, or at least a demonstration of this principle, that this magnet at low energies, if you look at its low energy states, looks like a particle moving on a circle. So now let's go to more complicated examples. So let me first give a very simple example. So I'm trying to demonstrate a symmetry related degeneracy. So let us imagine a 1D chain where where we have XY, an XY antiferromagnet in a 1D chain. So the classical ground states are again very simple. You take the 1D chain and all the spins have to lie in the XY plane, and neighbors have to be anti-aligned. So you point one spin with some angle phi, the next one has to be opposite, next one can point along phi, next one is opposite, and so on. So once again, we can ask what is a set of all such ground states? This simply corresponds to fixing the first spin, right? Changing this angle phi. So I can again call the first spin is this, second spin is this, all other spins follow. So once again, the set of all ground states is a circle. Right? But here there is something special here. What we should notice is that this circle, the set of ground states, it's a circle. It has to be a circle due to symmetries of the Hamiltonian. Or in other words, you take any 2 points on the circle or any 2 different ground states, they're related by a rotation about the z-axis, but a rotation about the z-axis is a symmetry of the Hamiltonian. So this ground state degeneracy in the classical limit is a consequence of Hamiltonian symmetry. So this leads to a very special property. So in low energies, it maps to a particle moving on this space. But because this space is symmetric, or every point in the space is symmetry related, the wave functions at low energies are evenly spread on the space. In other words, you have a particle moving on the circle. If you look at the low energy wave functions, the wave function has the same weight at every point on the circle. Okay, so it may not sound like a big deal. So let me give you a counterexample. So a counterexample is this. So now I take the original XY model and I add another term. And this term is a Kitaev term. So let me just describe physically what this term means. So I have the XY antiferromagnet. In addition, I add this term where on some bonds, it's a YY coupling. The next bond, it's an XX coupling. The next bond is YY and so on. So this is the additional term that we've added. Now, if the parameters J and K are positive, this actually has a very nice form. So this additional term does not change the classical ground state space. I'm not demonstrating this here, but you can just take my word for this. So the classical ground state space is still the same. It's still an XY antiferromagnet, and it's equivalent to a circle. The set of all such states is equivalent to a circle. However, now there is no longer a symmetry that connects different points in the circle. So if I want to connect 2 different points in the circle, or not 2 different values of phi, I'll have to do a rotation about the z-axis. But a rotation about the z-axis is not a symmetry of this k term. So now we have a classical degeneracy that is not symmetry related. So we call this an accidental degeneracy. So in this case, our principle still holds true. The problem maps to a particle moving on the space, but now there are some additional effects that come in because we no longer have a symmetry. So one consequence of that is that the wave functions at low energies can be unevenly weighted. So this is just for example. So imagine a circle, and then the wave function of a particle may look something like that. So it has some 4 peaks. So it's just a probability with the wave function square. So the probability is not evenly spread. It is high in some points, low in some points. So this is allowed because it's no longer a symmetry. So our interest in this talk is a special case of this, where we want to consider a case where this kind of wave function weighting becomes extreme. So imagine that the wave function of the particle becomes something like a delta function. So it's sharply localized at one point. Right? So this has strong physical consequences. So what this means is what is called state selection usually. So what we've discussed so far is a classical degeneracy. Now, if you go and introduce quantum fluctuations, these fluctuations can break the degeneracy and select some of the classical states, or maybe one of the classical ground states. So what does this mean for a mapping? We claim that this maps to a particle moving in the space of classical ground states. So now that particle gets localized at one point. It gets stuck. It doesn't move about freely. So we have made the case that, at least in the most recent paper, we made the case that localization of the particle occurs in 2 ways. And the first is what we call order by disorder. Second, we call order by singularity. The first can be understood in a rather simple fashion. So we imagine that the x-axis is a space in which the particle is moving. And the y-axis is some kind of a potential that's generated. And the potential is generated by quantum fluctuations. And if this potential is very deep, so there is a particle moving on the space, but if the potential is very deep, the particle will get stuck at a well of the potential, at the deepest point in the potential. This also corresponds to localization. The particle no longer sees other parts of the space, it just gets stuck in one point. So this is called order-based disorder. So I will not discuss this for this talk, but we've discussed this in some detail in the paper. So in order for this to happen, typically what you need is some combination of large system size and the spin quantum number. That has to be large, only then this can be effective. So in this talk, I'll be focusing more on the second option, the second picture, which is order-based singularity. So imagine that we have the space of ground states is something like this. It's a figure of 8. So you see something special happens. This space intersects itself at this point, at the node. It's not it intersects itself. So if this happens, so this is a necessary condition. If this happens, then the particle will form a bound state near the node and it will get stuck at the node. So very crudely speaking, imagine the particle comes down one of the leg, approaches the node, then it cannot make up its mind. It doesn't know, should it go straight, turn right, turn left, turn back, so it just gets stuck at the node. So this can also lead to localization. So I'll demonstrate this to you in a crude model, and then I'll give you some examples. Okay, so let me first explain to you why the particle can form a bound state like this. So let me first explain the name. So we call such a self-intersection point a singularity. That's because the space has well-defined dimensionalities elsewhere, but not at the intersection point. So here, for instance, I have a cartoon picture. Imagine there is some, I have many wires coming in. So wire 1, 2, 3, 4, all the way up to wire n, and they all intersect at the central point. Now, in general, you look at some point on this wire, it's one-dimensional. But at the central point, dimensionality is not well-defined. You can no longer say it's one-dimensional or two-dimensional, or zero-dimensional for that matter. So the space itself has well-defined dimensionality elsewhere, but not at a self-intersection point. So that's why we call it a singularity. Now, this kind of a geometry can, by itself, lead to a bound state, even in the absence of a potential. Right? So let me just show this to you very simply in this one slide. So let's say we have this kind of a space. We have these wires going out to infinity, and they intersect at this point, and we want to study the motion of a particle on this space. So this is actually a hard problem. So you see, because this dimensionality is not well defined at the central point, you cannot easily define a kinetic energy operator on the space. You have to do some tricks. You have to solve, say, Schrodinger equation separately on each wire and match boundary conditions. You have to do something like that. But there is an easier way. The easier way is to simply use a tight binding model. So what I'll do is I'll take these M wires, and each of them I'll replace by some points, by some sites, and we'll assume that the particle hops on neighbors. And the central point is common to all nodes. So you can hop here, and then you can move here if you like. So in this case, if we take the tight binding model and you can try it numerically, and you'll immediately see that the lowest energy state is a bound state, as long as M is greater than 2. Of course, if M is 2, there is no singularity. It's just two wires meeting at one point. It's just one wire. But as long as M is greater than 2, you have a bound state. So this state is peaked at the central node, and it decays exponentially on each leg. In fact, you can analytically write the wave function for the state, and the form looks like this. So imagine a site given by j comma gamma. So j denotes distance from the central node, and gamma is just the wire index. So this wire is gamma 1, that wire is gamma 2, gamma 3, and so on. So I can write a wave function ansatz of this form. So that is just an amplitude A, which will get fixed by normalization. And then there is an exponentially decaying form, and it decays as e power minus alpha mj. Alpha m is some kind of decay constant, and j is just distance from the node. So this is the wave function, and you can plug this in and check that this is actually a ground state. This is actually an eigenstate of the problem, and it's in fact the lowest energy state. And you can actually find explicit expressions for what this alpha m is, what's the energy of the state. So the end result of all of this is, if you have a tight binding model like this, the lowest energy state is a bound state. It's peaked at the center and decays exponentially as you move away. Okay. So why is this at all important? What does this have to do with magnets? So I'll show you in just a bit. So for this, I'll take an example, which is the Kitaev chain. So we've showed in a few examples. We have demonstrated this effect, but let me specialize to the case of the Kitaev chain here. So now I have a one-dimensional chain with this Kitaev Hamiltonian. So there are some bonds that are y, there are bonds that are y, x, and so on. So now I have to ask, what is the classical ground state for this system? Just like I did for the dimer a long time ago. So it turns out that the classical ground state is given by very simple conditions. The condition is simple to write down. So what all you have is this. On every X bond, say you have this X bond, so you have two spins, spin 1 and spin 2. Their X components must be anti-aligned. So S1X must be minus S2X. But on every Y bond, the Y components must be anti-aligned. So this is the ground state condition. It can be found using some arguments, using some Lagrange multipliers. So this was actually shown in this very beautiful paper by Bhaskar and Sen and Shankar in 2008. So now let's ask, how do we find, okay, this is the ground state condition. How do we find states that satisfy these conditions? So this was also shown by Bhaskar and Sen and Shankar. So let me just show their argument here. So the way they enumerate all ground states is to first define a Cartesian state. So it's just name. So the name is defined as in the following way. So you first take the system and you put a dimer cover on it. So you put dimers on nearest neighbors such that two dimers don't touch. So this is an example. I can put a dimer on X bond, dimer on the next X bond, dimer on the next X bond, and so on. So this is a dimer cover of this 1D chain. Now on each dimer, you minimize the energy, the bond energy. So say I take this dimer. So this is on an X bond. So now I have to satisfy the ground state energy condition. So I can say the first spin is pointing along plus X, second is along minus X. Or I can say the first is along minus X, second is along plus X. And I do this independently for each dimer. So if I do this, the claim is this is automatically ground state, classical ground state. It satisfies the conditions. So you see on the X bond, by constructions, it satisfies this. The two spins are anti-aligned. If you take a Y bond, the Y components are anti-aligned trivially because the Y components at either end are 0. So this automatically satisfies all classical ground state conditions. So in the same fashion, you can also construct a dimer cover and a different dimer cover with dimers on the Y bonds. And there again, you can take each dimer, you can assign so the first spin up plus Y, second spin minus Y, or first spin minus Y, second spin plus Y. And you can do this independently for each dimer. Right? So these are all ground states, classical ground states that satisfy this condition. But are these the only ground states? So here, Bhaskar and Sen and Shankar came up with a very beautiful idea. So just to recount, so on the left, I've named some states. Let's just say these denote some states. These are X states. These come from the X dimer. So one example is this state. So I put the dimers on the X, and on each dimer, I have anti-aligned the spins along the X axis. So one is along minus X, one is along plus X. And then I have a second column, which are states that come from the Y dimer cover. Here I've put dimers on the Y bonds. So one spin is along plus Y, one is along minus Y, and there are many such states because I can independently assign this. So I have a whole set of states. So now Bhaskar and Sen Shankar came up with a very beautiful argument. They showed that you start from one of the X states, and then you designate one particular Y state as a target state. So this is my source state, my starting state, one particular X state. And target state is one particular Y state. It doesn't matter. You can take any X state and any Y state. So they showed that you can smoothly connect them by a transformation that preserves energy. Right? So let's just take this example. So my starting state, the spin is pointing on minus X. My target state is pointing on plus Y. So in an intermediate state, I simply smoothly rotate the spin by some angle theta towards my target position. And I do this for every spin. So now, whatever state I have in the middle is also a classical ground state. Right? And you can see this in the following way. I'll just give you the gist of it. So here in the X Cartesian state, if you look at the bond energies, it's 0, -1, 0, -1. So the -1 is on the X bonds. But in the Y Cartesian states, the -1 is in the Y bonds, -1, 0, -1, 0. In the intermediate state, it looks like this, minus sine squared, minus cos squared. So if you just add them, add the energies, you get the same. So essentially, you take any X state, any Y state, you connect them, and every point in the middle is also classical ground state. Right? So this leads to a very beautiful structure that I'll show this picture. So let's first take so the left, I have the Kitaev chain with only 4 sites and periodic boundary condition. The next is 6 sites, the next is 8 sites, and you can build more if you like. So let's just take the 4-site case. So I want to enumerate all classical ground states. So it turns out there are 2 types of Cartesian states, one from an X dimer, there are 4 of them, and one from a Y dimer cover, that's 4 of them. And now you have like 2 families. you can take any element of the first family and any element of the second family, and they're connected by a smooth line.
Ganesh,
this is the
it's
set
roughly
of,
20 minutes.
Yes, it's 19 in my clock. Yes. So this is the space of all classical ground states. So we see that the space of classical ground states is a network, and the nodes of the network are these Cartesian states. Right? And you have some intermediate network. So you see the nodes actually look like that, the earlier picture we had of M wires intersecting. Good. All right. And this just becomes more complex as the size increases. So what does this have to do with this? So we take, say, the Kitaev chain with spin 4, and we diagonalize the problem. We again find some eigenstates, but we see that there are precisely 8 low-lying eigenstates. Right? We've just shown them in blue. The others are also just higher energy eigenstates are in magenta. But you see that precisely 8 eigenstates. And as you increase S, these states get better and better separated. So we interpret this as these 8 states as bound states. So these are the low energy states of this Kitaev chain are bound states. There are 8 of them precisely. And if you go to larger chains, say spin 6, so sorry, N6, which is larger system size, then you precisely find 16 bound states. And spin N8, an 8-site chain, you get 32 bound states. So this is our claim. So in the low energy, the particle gets stuck at the nodes of the network, and that's why the states have been selected. All other states have been ignored. So it's as if the particle gets stuck in one of these states. So let me this is my penultimate slide. So we believe there is a signature of this that can be seen. So we define something called a binding energy, separation between the lowest unbound state and the average of these bound states. And here we plot the binding energy versus S for different N values, different system sizes. So essentially what you have to see here is the binding energy is always linear in S. It's a straight line fit. It's just leave some scales as S. So the binding energy in this case scales as S. It's what we find in our numerics. But in the case of order bit disorder, where there's a potential, it should scale as S power half, square root of S. This is being shown from Max Planck, actually. Good. So that I come to the summary. So I hope to have convinced you that every magnet at low energies maps to a single particle problem, with single particles moving on a classical ground state space. Now, state selection can happen in a system with accidental degeneracy. That corresponds to localization of the particle. That can happen in 2 ways, either due to potential or due to these singularities of self-intersections. So the low energy physics, when there's self-intersections, is dominated by bound states. So we are looking for materials where this can be tested. So materials where, say, S can be tuned. Okay, thank you very much. Thank you, Shubho.
Thanks, Ganesh. We have about 4 minutes for questions. So if you want to ask a question, just raise your hand or just unmute yourself and go ahead and ask.
Sorry, I cannot raise my hand because I don't know how to as an organizer.
Okay, sure.
Can I have a quick question?
Go ahead. Yeah, just go ahead.
So Ganesh, nice talk. Yes. I just wanted to clarify one thing. So, I mean, this smooth rotation, let's say from one ground state to another. See, I know certainly for double exchange models. So, for example, spin fermion type models where there are some classical spins coupled to heavy spins coupled by inherent electrons. So there are arguments by Chomsky et al. Which basically says that you necessarily go through a phase separation. So you cannot take, for example, a ferromagnet and smoothly rotate it to an antiferromagnet without going through a phase separated state. So in what the generality of the sort of claim is what I'm trying to understand.
So within this model, this is very precise.
Sure. No, So I think it's to do with your first statement, the first general statement that you put up. So, I mean, even for example, if one were to think of, integrating out the electrons in a spin fermion model and writing an effective spin model.
Yes.
There, as far as I know, I think these are probed by Chubukov, and so they tried to do some spin wave theory of those things.
Yes.
To my knowledge, it seems that it always goes through a phase separation. So there is no smooth.
So that could be, but then you're probably tuning the parameters of the Hamiltonian itself. Right. So here is given a certain Hamiltonian, then this picture holds. So,
of
what
course
this will mean is yes, go ahead.
Oh no, I think the way they tune, I mean, at least what they have in mind is because they're itinerant electron, you change the density of the electrons, and that causes from a ferro to an antiferro, and that goes through a phase separation. So that is
So I can
not
imagine
what you are
something like, yes, that's not what I'm saying. So imagine that there is a particle moving some space, but the space itself distorts, goes through some Lifshitz transition. So from one circle, it pinches out to something. So that's perhaps what is happening.
Sure. Okay, thanks.
Okay, any other quick question? Shumiron?
Hi.
Hi, Shamiran.
Hi, how are you? So this substructure that you see in your low energy subspace, is there any more to understand there? There's some substructure, right, in the low energy subspace?
Yes. Yes. So we believe, so something like these 8 are not all equivalent. There's some spread between them. Right? So far what we have, I've not shown it in the talk. So we quantify the spread in these, and what we see is as S increases, the spread decreases. Or in other words, this arises from, so imagine there's a particle moving on this network. So there are bound states localized here, but there is still some hybridization between the bound states. So
Right.
that gives rise to this spread. As S increases, the hybridization weakens, and they move towards degenerate subspace.
I see. Okay. Thank you.
That's as much
Okay.
as, yeah.
Very quickly, Arnob and then Ravi, and maybe in the meantime, Yasir can set up his slides.
Hi, Ganesh. Can you hear me?
Yes. Hi.
So I just have a quick question. So in this wired network example you showed, of course, there was just one ground state, right? But when you increase S here, or when you increase N for that matter, is there a simple formula for the number of bound states that you have?
Yes, yeah, it is. So I showed a single bound state for a single node.
Right.
Now in the network, you have many nodes. So each node has a bound state. So it exponentially increases with n. It's some 2 to the power n by 2 plus 1.
I see. So you just count the number of nodes in that sense.
Cartesian.
Got it.
Yes,
Thanks.
yes. And each node gives a bound state.
Okay, very quickly, Ravi. Ravi, you have to unmute yourself. Hello, Ravi?
Yeah. So Ganesh.
Yeah, very quickly.
So the gap that you are showing in the middle, what do you expect it to do as you increase your size? You only showed it for 3 or 4 5 right? Do you expect it to remain finite?
We expect it to remain finite, but the numerical data is not very conclusive because we can only access so many system sizes. So we believe it remains finite, but we don't have concrete evidence for that yet.
Okay.
Thanks.
Okay, let's thank Ganesh once more for the nice talk. And we have run out of time for questions, so we will immediately go to Yasir's talk. Thanks, Ganesh. So Yasir, are you ready?
Yeah, I'm just making it full screen, although I lose the cursor now, so it could be a bit irritating, but anyway.
Okay. So then let's start. So the second talk is by Yasir Iqbal from IIT Madras. Yes.
Thank you, Shubro, and thanks to the organizers for inviting me and giving me the opportunity to be among our community and present some of the recent results we have. So what this talk is going to be about is about trying to find classical spin models where the Hamiltonian permits you to rewrite it as a complete square. And what this leads to is the fact that such Hamiltonians where you can complete the square generally feature degenerate ground state manifolds. And therefore they set the stage nicely for the realization of classical spin liquids in case order by disorder mechanism fails, or in the corresponding spin models with small values of spin like spin 1/2, they could lead to potential realizations of quantum spin liquids. So Ganesh in the previous talk has very nicely set the stage for me to deliver my talk. So let me. I'm unable to move to the next. Oops. I'm sorry, but My
Maybe just go out of the full screen and
my keyboard seems hung actually. Oh no. It happened yesterday once and now I'm like stuck. Oh my God. Oh, just giving me the beep sound and wait, stop. Let me try. I stopped sharing. I'm sorry. I went out and I hope.
No, I can still hear you. So
Yeah, but now my keyboard is typing again. So maybe, sorry for this, but let me share again. And yeah, so share screen. Okay, share. Okay, you can see it. So let me not go to full screen mode. So I hope this is fine. Okay,
yeah.
Great. So yeah, to continue. So whenever a Hamiltonian permits you to rewrite it as a complete square, what happens is that you have degenerate ground state manifolds. So these degenerate ground state manifolds and their dimensionality typically is reflective of the degree of frustration in the system. So let's take a simple Heisenberg Hamiltonian, but write it in Fourier space. In Fourier space, it's generally written as a summation over all the points in the Brillouin zone, J of Q, which is simply the Fourier transform of the exchange interactions, times the dot product of the Fourier components of the spin operators. Now, in order to find a ground state, I mean, all you have to do is to minimize the J of Q. And the set of Q points for which J of Q takes a minimum is basically defines you the ground state manifold for that model. Now, if you take typical, commensurate orders like a ferromagnet or a, antiferromagnet on a bipartite lattice, this Q manifold typically consists only of a discrete set of points. Say for a ferromagnet on a Bravais lattice, it will simply be 0, 0, the origin, right? Or on a non-Bravais, there'll be a few discrete, subdominant peaks in the Brillouin zone. However, I mean, when you have a frustrated model, this generally takes the form of an extended manifold, that there exists a continuous range of Q vectors which all serve as good ground states. So at zero temperature in the Luttinger-Tisha approximation. But Luttinger-Tisha on Bravais lattices is exact. So for example, if you take a square lattice and you take a J1, J2 model, then we all know that at the highest, the point of high frustration, which is when J2 over J1 is 1/2, the ground states are generally formed by generic spirals, which are Q comma pi and pi comma Q, and therefore span this, this manifold, which you see in a red line, the border of the Brillouin zone, and they form a codimension 1 ground state manifold. The same thing happens in the face-centered cubic lattice at the nearest neighbor Heisenberg antiferromagnet, where these red lines denote to you the degeneracy in the Q vectors, where you can pick out any Q vector, and that'll give you a degenerate energy as any other Q vector and span the ground state manifold. The frustration can be even higher. For example, you can have surfaces, spiral surfaces forming, as happens in the J1, J2 Heisenberg model on the diamond lattice, where you see that you have different kinds of spiral surfaces where you can pick out any point, and that gives you a ground. That's a well-defined ground state. On the face-centered cubic lattice also, if you take a J1, J2 model and you're sitting at the 1/2 point when J2 over J1 is 1/2, you have this kind of a Schwarz P surface, as mathematicians call it, with some Euler characteristic, which is say -4 in this case. And then you have the most frustrated lattices we all know, like in 2D, you have the Kagome lattice or the pyrochlore lattice, where you can choose any point in the Brillouin zone. And that actually serves as a good ground state. And these two we all know, feature classical as well as quantum spin liquids. So the aim of this talk will be that besides these few examples that we know, like the pyrochlore or the Kagome, where you can have a completion of the square, does this possibility exist also, for example, in other lattices, for example, the face-centered cubic lattice, which remains rather unexplored. So just to elaborate a bit more on completing the square, you take the Heisenberg Hamiltonian, which is simply Si.Sj, and you see that if you take a Kagome lattice, which is just an arrangement of corner-sharing triangles, then you'll be able to rewrite this Hamiltonian as a square of the sum of the vector spins on each of these elementary triangles, right? And if you expand the square, you clearly see that you just get back this thing. All you get is S1 squared plus S2 plus S3, which gives you 3. And you just have to subtract that. And then you get the dot product terms. And then J over 2, the 2 takes into account the double counting, right? And these two are absolutely identical. And from this reformulation, it's very clear that the ground states are simply those in which the sum of the spins on every elementary plaquette is identically 0. So the magnetization per triangle is 0. And then these gives rise to actually these beautiful patterns in the structure factor called bow ties and pinch points, which are just reflective of the flat band physics or the dipolar correlations that follow from that. You can do the same exercise actually on any corner sharing geometry, like the pyrochlore lattice, which is a corner sharing arrangement of actually tetrahedra. And you can rewrite the Hamiltonian as a sum of the 4 spins occupying the vertices of the tetrahedra squared minus a constant. And the ground state is simply those in which the S1 plus S2 plus S3 plus S4 is 0, right? And then you see these characteristic bow ties and the pinch points. And indeed, in this model, I mean, we know that, the degeneracy is so severe that thermal order by disorder fails to lift it. And therefore, if you try to simulate this model in classical Monte Carlo and plot the specific heat here versus temperature, you see this blue line right at the bottom. There is no sign of a phase transition down to the lowest temperatures. And therefore, the system realizes what we call as a classical spin liquid, right? Okay, so let me come to the example I'm going to study, which is actually the phase-centered cubic lattice. Now, this phase-centered cubic lattice was already known, 400 years ago, where Johannes Kepler actually thought of tessellating 3D Euclidean space by various ways of tiling the FCC lattice. So the FCC lattice is a Bravais lattice. You can take one point and apply translation vectors A1, A2, A3 and generate the entire lattice. And there are various views of actually tiling it. So one is that if you look at it in the 1, 1, 1 direction, then you can stack it with triangular planes, as I show in panel B. Or you can also think of it as a covering by tetrahedra, which are edge sharing, like in panel C. Or you can also cover it by edge sharing octahedra. And you will see that each of these different ways of tiling will help you actually complete the square at various points in parameter space for this model. So this talk is, the results of this talk are actually presented in this paper, which recently appeared. And this work has been done together with the PhD student of Carlo Penn's, Peter Balla and Carlo. And the main question we address is how many ways can one complete squares on the FCC lattice? So we first started by mapping out the zero temperature classical phase diagram of this model with long range Heisenberg exchange interactions. So J2 and J3. And you can already see, for example, here in the top panel, we show the J1 is set to -1, so it's ferromagnetic. And J2 is on the x-axis, J3 on the y-axis. And you see a multitude of, commensurate orders, spirals, and you see, other. But then you see these triple points where multiple of these phases meet. And these points, actually, we identified that these points are host to, one-dimensional ground state manifolds where the Hamiltonian permits you to, complete the square. Similarly, in the case of when J1 is antiferromagnet, you have the nearest neighbor point, which is, already known to be degenerate. But then we also identified a two-dimensional, ground state manifold, the M2 point in the J1, J2 model. And actually, this nearest neighbor point is not unique. There's an entire line which extends up to a triple point where you can actually do this, play the game of completing the square. And this sets the stage for further explorations by order by disorder, What happens when thermal fluctuations are introduced? What happens when the spin is brought down from infinity to a finite value? And then for spin 1/2 and spin 1, can quantum fluctuations stabilize a quantum spin liquid? And since many of these manifolds also involve a ferromagnetic phase, the whole question of spin nematics arises, Magnon bound states and other things. So, okay, in a Fourier space picture, I mean, this is how these manifolds. So I already showed you for the nearest neighbor model, for the two-dimensional, degenerate manifold in the J1, J2, I also showed you. And then the other manifolds feature different, one-dimensional lines of, of Q vectors. So the thing is that let's start with the two-dimensional manifold, right? So you have this thing, and this is realized as I circled here in a J1, J2 model when J2 is precisely 1/2 of J1. So this immediately raises the question, how should you tile the FCC lattice to complete the square? And you will see that if you tile it with the octahedra, each nearest neighbor bond will be covered twice, and each second nearest neighbor bond will be covered only once. And therefore, this is a natural tiling that you must do to actually complete the square. So you can rewrite this Hamiltonian as simply this way: 4 times SI dot Sj and 2 times SI dot Sj with a 1/4. This is simply the original J1 and J1 by 2 model, right? And when you complete the square, you can see that you can rewrite this Hamiltonian as a sum of spins residing on the 6 vertices of the octahedra squared minus a constant, which is simply the ground state energy. And any spin configuration which satisfies this rule, the zero magnetization rule on the octahedra is a good ground state. However, beyond this zero temperature, we don't know much about it. So we looked at it in a previous work of ours, and within harmonic order, spin wave theory, we found that type 2 order, where certain points in the center of the hexagonal faces of the Brillouin zone are actually selected by order by disorder. But what happens for small values of spin, for example, or what happens when you go beyond the harmonic approximation, even in the classical, limit, when you do exact classical Monte Carlo, it's an open question. And I will tell you in the end that we actually, like with FRG, we found actually a quantum spin liquid for low values of spin. Similarly, we also tried to understand the origin of these degenerate manifolds in the ferromagnetic part of the phase diagram, where you have one-dimensional ground state manifolds. And for example, this point where J2 is simply minus J1, right? So the Hamiltonian takes this very trivial form. And then in order to complete the square, you must simply rewrite it by tiling the FCC lattice with these signed rectangles, so, or these signed squares. So these signed squares simply means that the black dots and the white dots come with spins with opposite, signs. So when you complete the square, you must be careful to put the appropriate sign. Wherever there is a spin sitting on a white dot, you must put a minus sign, and a black dot with a plus sign, and then you can complete the square. So you again understand the origin of this degeneracy, that any ground state, any spin configuration which satisfies this rectangle rule, let's say, is a good ground state. Okay, and then we did some numerical simulations for Ising spins, XY planar spins, and Heisenberg spins, and found interesting spin textures. For example, when you take the Q vector to be pi pi pi, which is part of this manifold, you get solutions which are decoupled, alternating 1-1-1 ferromagnetic planes. So if you look at the FCC lattice from the 1-1-1 direction, it's simply a triangular lattice. So this is what it looks like here, right? And it is stacking of triangular lattices, right? So when you rewrite this Hamiltonian, you can basically rewrite it as an effective model of coupling within the planes of spins, the 6 spins within the plane, and then the 6, 3 below and 3 above. So that takes into account the 12 coordination number of the FCC lattice. And so the Hamiltonian simply takes this form of coupling between different neighboring planes and within the planes. And at this special point, the first term basically just disappears. So you put J2 equals to minus J1 and J3 is 0, and the first term disappears, and you get basically decoupled planes. You get decoupled ferromagnetic planes, which are the ground states. Okay. Similarly, you get very more interesting solutions where, for example, if you take Ising spins, when you fix them on one layer, they basically, by these constraint rules on the rectangles, you basically determine their order uniquely throughout the lattice, and you realize some kind of an antiferromagnetic order. But once you go beyond the Ising limit and you treat planar and Heisenberg spins, more interesting textures arise. For example, you get these Kagome ferromagnetic, lattices with some orphan spins which are completely decoupled from the remaining. So you do a one quarter depletion, of the triangular lattice, and you land up with these orange Kagome lattices, in every triangular plane, with these purple and blue spins which are completely free from the rest. So in numerical simulations, we found, various kinds of, interesting textures. I've just highlighted a few. By no means they're all. Okay. Then, for example, we found the chain solution. So you have, interacting chains going in the 1 bar 1 0 direction in these 1-1-1 planes. And then again, you can rewrite the Hamiltonian as, as basically, a 2D model of interacting chains here with some effective couplings K1 and K2, which are just determined from the Heisenberg couplings. And you can see that you realize lattices which are topologically equivalent to a square lattice with, J1, J2, with J1 being ferromagnetic and J2 being antiferromagnetic. And this model is known to be strongly frustrated and having a co-dimension 1 manifold. And there have been some, claims of actually spin nematic behavior around the highly frustrated point. So you get chains. So you basically get a manifold in which XY and Heisenberg spins give rise to interesting textures of, interacting ferromagnetic chains, which are not there in Ising models. You get, Kagome ferromagnetic planes, which are, decoupled from each other, and, and the whole question of what happens when you add temperature. What do thermal fluctuations select, and what happens when you add quantum fluctuations, either within the semi-classical limit or in the extreme quantum limit of spin 1/2. remains, you know, an open question. Then, I mean, similarly, you can play the game with other manifolds, and you know, you will find that, you know, you can always tile the FCC lattice with various kinds of motifs, and you'll be able to complete these squares, you know, and construct interesting solutions, you know, by taking either one arm of the star or two arms of the star. You get either, you know, alternating trivial ferromagnetic planes, or you get stacked antiferromagnetic planes, and, you know, various kinds of solutions. So yeah, so you can, for example, you know, simply rewrite these models as, you know, interacting 100 planes, with the interaction between the planes and interaction within the planes by various kinds of tilings, you know, and these Hamiltonians are simply very trivially written by just noting down how many connections you have, you know, within the plane and outside the plane. And in most cases, what happens is that you will see at this manifold, you know, parameter point, these interaction terms between different planes actually just disappear. Right, and you're left with some decoupled, you know, planes, stacked planes. But then this is all at zero temperature, as I said, in the classical limit. So then, you know, what happens with temperature and quantum fluctuations? These are all interesting questions to explore. So we explored all these, you know, in this paper, we explored various solutions. I mean, you know, you have interesting, you know, constraints that arise, you know, that how you should stack antiferromagnetic planes, you know, and you know, and various kinds of stacking patterns that we identified, you know, numerical simulations. And some of them don't occur for Ising spins, and some of them don't occur for XY, but only for Heisenberg. So there's a lot of, you know, interesting directions one can go in these, you know, frustrated models. So you can have, you know, also ferromagnetic chain solutions similar to what I described, where these chains are, you know, just forming a square lattice. So if you look at the FCC lattice from the 100 direction, you will see that it's simply projected onto a square lattice, you know, and then you have the effective model on the square lattice with long range interactions, you know, and each of these chains is represented by an effective, you know, spin of unit length, SI, you know, I simply referring to the point at which these chains pierce, you know, thing. So yeah, so we found a bunch of interesting spin texture, you know, textures for the ferromagnetic part of the phase diagram, and which I just described to you. Similarly, you know, you can play also the game on the antiferromagnetic side, where till now we only knew that the nearest neighbor, you know, model is actually a degenerate ground state manifold. But what we identified is that you can, this is not a unique point. You can actually traverse this entire line up to this triple point, and you have actually a one-dimensional, you know, ground state manifold. But the things become more tricky here, since you have two free parameters, J2 and J3, which vary. The completing the square actually is not that trivial, since you have two free parameters, and you can't tile the FCC lattice with just one motif. You need two motifs. So you have the tetrahedras and you have the signed rectangles. And you will see that along this line, you will be able to complete the square. This will take a while to, you know, figure out, is that you will be able to still complete the square, but in this way. So you tile the FCC lattice by tetrahedra and by signed rectangles. And along this line, any spin configuration which satisfies these constraint rules, you know, will be a good ground state. And this additional constant you can verify simply just gives you the ground state energy, which for the nearest neighbor model is correct, you know. And when you're in the two extremes, when you're either at the nearest neighbor point, only the tetrahedral rule survives. So you only need to satisfy that. The other one is automatically satisfied. Whereas in the other extreme limit, only the rectangle rule needs to be satisfied. Okay. So, you know, we basically, and along this entire line, you again find these interesting interacting ferromagnetic chain solutions, you know, which decoupled, you know, which give rise to some, you know, Heisenberg Hamiltonian on a square lattice with some effective couplings, you know, with long range interactions. Which, you know, so the whole, sort of to summarize, you know, one part of my talk is that we found ground state manifolds in Q space of dimension 1 and 2, which are sub-extensively degenerate. In all cases, we could understand the origin of this degeneracy by actually expressing the Hamiltonian as a positive definite sum of complete squares on different kinds of motifs which were used to tile the lattice. And this reformulation then provided us with hints to explicitly construct large classes of non-trivial aperiodic ground states. So all you have to do is to actually, you know, you have these constraint equations, which are homogeneous equations. So all you have to do is, you know, solve them and find the kernel, you know. Then
Yes,
now,
sir.
right.
You have about 5 minutes, including questions.
Okay. Thank you. And okay, I'll be done so in a couple of minutes. And then we described relations of these real space patterns to the Q space picture. So the future directions to take into this is basically, these triple points and phase boundaries that I told you are host to these manifolds. So in case order by disorder fails to live this degeneracy, you could realize, quantum spin liquids or spin nematics. So recently with a student of mine and a student of Johannes Reuter, we did a projective symmetry group classification of quantum spin liquids on all these cubic crystal systems. But there still is more work. So if you want to study nematics, you'll have to, extend this classification to include triplet pairing and spin-dependent hopping terms. For example, as Shubro did many years back on the Kagome lattice, in the context of Herbert-Smithite. And then you have to apply state-of-the-art numerical quantum many-body methods to, study candidate ground state, wave functions. So in this classification on the FCC lattice, we found some unusual Z2 spin liquids, a Z2 spin liquid, which has actually an interesting lock pattern of hopping and pairing amplitudes in the ansatz. So what we found is that there are some symmetry protected line-like degeneracies, in the Brillouin zone. So if you look at this in this Brillouin zone of the FCC lattice, and you look at this network of lines, this is where basically the spectrum is gapless and it is symmetry protected. So it arises, the question arises, can it give rise to a spin liquid with some kind of pinch line singularities as has been found on the pyrochlore lattice by this group in Okinawa by Owen Benton, Ludovic Jobert, and Hanya and Nick Shannon. So these are interesting questions to explore whether this kind of a Z2 spin liquid can be realized in one of these manifolds of the FCC lattice for spin 1/2 models. So in a recent work, we applied the pseudo-fermion functional RG method, which is basically a technique of treating these complex 4 fermion interaction terms in their full complexity by doing infinite order diagrammatic summations, since there is no small parameter, and solving these FRG flow equations for up to 2 particle vertices to get the spin-spin correlation function. And what we found, applying a recently formulated scheme which was done by in the group together with Cologne, Simon Treps and a student, and Tobias Müller, who's a student of mine, and Ronnie, where we developed a multi-loop formulation of pseudo-fermion FRG, basically, which takes it to implementing the first order Parquet equations exactly. And we went up to 6 loop order and found that indeed in the FCC lattice in the J1, J2 model, this 2-dimensional manifold that I showed you, which is the 1/2 point, actually the order by disorder fails to live the degeneracy and realizes a magnetically disordered ground state, which could likely be a quantum spin liquid. And it is not just at the isolated point, but also in an extended region of parameter space from around 0.35 to about 0.65. However, what remains to understand is the nature of this magnetically disordered state, whether it is a spin liquid, and if so, what kind of a spin liquid. And also the whole question of thermal fluctuations on this 2-dimensional manifold remains open. So if someone wants to pick up these problems of, trying to understand either, in the semi-classical limit or, doing classical Monte Carlo, which we've been stuck for 1.5 years, so we haven't made, it's still a very difficult thing to capture this. Okay. So yeah, so I mean, that brings me to the end of my talk. I mean, all I wanted to sort of convey is that there's a lot of interesting physics once temperature becomes non-zero and, the reciprocal spin becomes finite to explore on the FCC lattice. Yeah, thank you.
Thank you, Yasir. So we have almost run out of time, but a quick question.
Sorry for
Manoranjan? Yeah, Manoranjan.
Yasir, very interesting talk. Yasir, I was just wondering, just like you're doing completing a square, just like the MG model, Majumdar-Ghosh model, where you try to complete the square. So in that case, particularly, you have a very large gap, right, in the spectrum. Do you find this kind of a gap here as well?
Well, I mean, sorry if I understand your.
So your ground state is degenerate, right?
Yeah, the ground state is degenerate. I mean, if I look at the spectrum of excitations around it,
yeah.
I mean, then I mean, so it depends. I mean, so you're referring to order by disorder, and then how like, but one has to compute the spectrum of excitations around it.
That's correct.
Yeah, and then I mean, then only can one address if you're referring to something along that.
Okay.
Because thermal fluctuations will then select these states which have the highest, density of excitations, around these, so these degeneracy, of course, is accidental, right? So the spectrum will be different around each of these ground states. And if you want to study thermal order by disorder, you'll have to look at, magnons with energy order T. And if you want to study quantum order by disorder, then the states with the lowest average magnon energy will be selected. But we haven't computed the spectrum of excitations, let's say, around these.
Okay, that's fine.
Open question, yeah.
One more question I have is like, do you find
just a point. You can go on asking the question. Yasir, would you unshare your slides so that Srijit can share his slides, and in the meantime you can continue with the question?
Yeah. Okay. So Yasir, so in Majumdar-Ghosh model, you have the singlet formations, right? But mostly those are.
Yeah, we're old friends. Okay, so let's move on to the last talk of the session by Kamal Das from IIT Kanpur. And so, Kamal, you can start now. Yours is a 12-minute talk, and I'll basically sound you when it's about 10 minutes. Okay? So,
okay,
yes.
okay, thanks, sir. Yeah. So, am I audible?
Yes.
Okay. So, hello everyone. Myself, Kamal Das from IIT Kanpur. And the topic of my talk is chiral anomaly in wild metals and its implications on transport properties. This talk will be based on our recent papers with my boss Amit Agarwal. Okay, so I will start with some preliminary ideas about semi-classical transport. In transport, we calculate current, and the charge current, for example, can be written as a product of charge, velocity, and the probability of occupying a particular quantum state known as the distribution function. To explicitly calculate current, we need the velocity r dot, which is the momentum derivative of energy. We also need the distribution function, which is calculated using this equation. For that, we need force given by this, and IC is known as the collision integral, which we generally consider to be like this. Now, these expressions of velocity and force may look familiar to you, because this force is nothing but the classical electromagnetic force on a charged particle. And this velocity of expression is the group velocity of a wave packet. Now, what happens if these expressions of velocity and force are incomplete? That is what we will explore here. Okay, and this is indeed the case in systems with finite Bary curvature. Now, to make sense, this Bary curvature is a geometric property of electronic wave function, and it can be thought as a kind of magnetic field in momentum space. So in presence of this Bary curvature, this velocity and force is modified like these two equations. So these red shaded parts are the only terms which I showed you in the earlier slide. So as you can see, there are many new terms in this velocity and force, and therefore many new phenomena can be expected from this. Okay, so here I will focus only one phenomena, which is known as chiral anomaly, which is a breakdown of chiral symmetry. So let's understand the chiral symmetry first, and then we'll discuss how does it breaks down. So you may be familiar with the fact that the Dirac spinors can be projected into two components, left chirality as well as right chirality. So if P is a projection operator, then the left and right parts can be calculated like this. Okay. Now, if a Lagrangian of a particle remains same when we rotate the chiral components independently, let's say we are rotating only the left part where right part remains invariant, then we say that the theory is chiral symmetric. And as a consequence of that, the number of particles of individual chirality remains conserved. Okay. And interestingly, the massless Dirac fermions, which are also known as wild fermions, hold this chiral symmetry, but a breakdown happens in presence of electromagnetic field. And due to this breakdown, the conservation of individual chirality is now not guaranteed. Okay, so the takeaway message from this slide is that in presence of electromagnetic field in massless Dirac fermions, something interesting happens, and as a result, the conservation of individual chirality may get violated. Okay, so as you probably have guessed that we will try to see that whether this physics, this non-conservation part can be realized with the help of these new expressions of velocity as well as force. So the answer is of course yes, but for that we need a particular type of Berry curvature, which I have shown by this equation. And this kind of Berry curvature can be realized in a material called Weil metals. The band dispersion of Weil metal look like this, where this black lines are the energy, and this blue part is the finite chemical potential, hence the name metal. And now if we zoom near these band crossings, we will find linear band crossings of non-degenerate bands. The Hamiltonian need these band crossings can be represented like a Hamiltonian of sigma dot k. And interestingly, these two different band crossing will be denoted by something called chirality, which I denote by S. Okay. One may ask this, that whether this violation of chirality conservation really happens in Weil metals or not. And the simplest way we can show that is to construct a continuity equation from the Boltzmann equation. So I have constructed here a continuity equation of the number of particles with individual chirality, and you can see that if these two constants Ce and C tau is non-zero, then the number of particles in each node or each band crossing will change with time. Now, due to this chiral anomaly as well as in scattering, a steady state can be reached in these Weil metals. And in the steady state, the overall scenario can be thought like that the two band crossing will have different chemical potentials. So this is the story of chiral anomaly in Weil metals. Now we will see that what are the fingerprints of this chiral anomaly when we go to experiment. Okay, so one of the key thing we as an experimental consequence is negative longitudinal magnetoresistance. So longitudinal magnetoresistance is magnetoresistance when magnetic field is applied along the direction of current. So in this field, we have explored that what happens to this magnetoresistance when we include a tilt in the dispersion of Weil metals. So the tilt can be induced by a term like this, and as a consequence of that, the dispersion of Weil metals are not ideal cone. I have plotted the conductivity as well as MR for this tilted Weil metals. And one thing I want you to look at that in presence of tilt, the MR curves are not symmetric. That is, it behaves differently for B greater than 0 and B less than 0. Okay. So the other thing we have done is that we have explored what happens if we apply temperature gradient in place of electric field. And we have come out with a picture that maybe the overall thing can be thought like that the two band crossing will have different temperatures. Okay, and as a consequence of that, we have also shown that planar Nernst effect can be realized. So briefly, the planar Nernst effect is like a transverse voltage measurement. Let's say we are measuring the voltage along the y-axis when we have applied the current along the x-axis, and as well as the magnetic field is also in the xy plane. So this is different from ordinary Nernst effect in the sense that in ordinary Nernst effect, the magnetic field is applied along the z-axis. So we find that this Nernst effect has quadratic magnetic field dependence, and the phi, the angle between the magnetic field and x-axis, has a sine square cos square phi dependence. Okay, so in summary, basically I have broadly discussed the physics of chiral anomaly in wild metals, and I have shown 3 of my works. So the effect of tilt on longitudinal magnetic resistance, what happens in presence of temperature gradient to the chiral anomaly physics, and as a consequence, we have predicted the planar Nernst effect. So that is all I have to say.
Thank you, Kamal. Questions, we have about 4 or 5 minutes for questions. Okay, let me start with one question myself. Is that, when you put these biases across the 2 wild points, is it sort of feasible, even within calculations or experiments, to disregard the relaxation through the valence band?
So
the bulk?
So
can you go to one of the pictures that you so suppose I take this one and I think about the chemical potential difference. The part that you haven't drawn in blue, these 2 bands are really connected with each other. So there is some relaxation through the valence band or this filled band. So
yes,
is it okay to disregard that?
So no, it is not okay to disregard that. So we need this consideration of relaxation when we explicitly calculate the distribution function. Okay. So, and when I have calculated the distribution function and have calculated the current, I have included also this relaxation time in the Boltzmann equation. So we have to include that relaxation time.
No, but so what is the physics of this relaxation? I think.
Okay. So as you can see this continuity equation, right?
Mm-hmm.
And with time, the number of particles in individual nodes is either increasing or decreasing. So we have to include a relaxation where with, let's say, with some scattering time tau v, internodal scattering time, where ultimately, so that we can find a steady state, that is del ns by del t has to be 0.
Okay. Any more questions? Further questions? You can just put up your hand, or you can just unmute yourself and ask the question. Okay, there seems to be none. So in that case, let's thank Kamal for the nice talk. And with that, we come to the end of the session. We should conclude by thanking all the speakers of the session for the nice talks. And I guess that brings us to the end of it. So thank you.
So thank you, Shubhra, for chairing the session, and thanks all the speakers for very nice talks. So we're running a bit late, so maybe we'll start in 10 minutes. So we're supposed to start at 3:45. So maybe we start at 3:55. Is that okay with so Amit, you're the session chair. So
yeah, sure, I'm around.
So in 10 minutes we start. Then I'll have a chance to, people will have a chance to just look at their slides and check, etc.
Sure.
Okay, so thank you again, Shubhra, for chairing the session. Yeah. So let me see. So Amit, I'm making a co-host, and I request, let's see if the speakers are all there. So I see Samir.
Yeah, Shumiran was there in the last talk also.
Yeah,
I'm
so
there.
Samir,
Okay, great. And Manoranjan has to be there. He cannot be not there when I am around. And I hope the students are also there, no? Shayan Lahiri.
Yes, sir, I am present.
Okay, Ruchira Bhatt and Shurjit Bera. I think let's just check if slides are working one by one. I think that will,
So, Sumiran, I made you a co-host. Can you check first, and then Manu can go?
Yeah, one by one. Yeah, in the same.
Yes. Okay, I'll go ahead. Is it visible?
Yes.
Yeah.
And I'm also visible, audible now.
Yeah.
Yeah.
Is it full screen now?
Yeah, it is full screen.
And the red cursor?
Red cursor is also visible. Yeah.
Okay, thanks a lot. So I'll unshare.
Great. Ranjan.
Yeah, let me try. Yeah. Okay, so. Is it visible?
Yes, I can see
your screen is visible. Yeah, slides will become visible in a minute. Yeah.
View and full screen mode. Is that okay?
Yes.
Yeah. This is okay. This will work. Yeah.
Yeah. Well, I don't know why this is okay. So is it because of this? I mean, when I make this one, it goes out of the screen.
Yes. Wait. No. We are able to see actually. So the green box is smaller, but we are able to see your full screen. So it's sort of okay actually.
Okay. I don't know why this green box is coming.
So green box is whenever you share in Zoom, then the Zoom shows that this is the boundary of what you're sharing.
Okay,
but for example, I see where alpha is equal to J2 by J.
Okay, you can see that. But
I see that, yeah, which is outside the box.
So I think better to be in this mode. This one is better or the previous one was better?
Previous one was larger, so better. And we are anyway able to see, Matla, so it's okay.
Okay, so then I put it like this.
And I think just don't mind the green box. I think that's okay.
Okay. So I think then it's okay.
Yeah. Great.
Shall I stop sharing now?
Yeah, please. We will give you another opportunity.
Thank you, sir. Amit.
Okay. Lahiri, Sayan and Lahiri, please, let's try.
Yes, sir.
Yeah, please.
Sir, is it
so
visible?
I see. Yeah. Your slides are visible. Results in 1D is what I see.
Yes.
Okay. And looks beautiful. Okay. You want to try. So your cursor is also visible. If you want to use your cursor, the hand was visible actually.
Okay. Thank you, sir.
So feel free to use that.
Yeah.
Let's see. So Ruchira.
Yes, sir.
Yeah, so I see your slide actually. Yeah.
Okay.
So there's 5 lattice I see. Yeah.
Yes. And am I audible, sir?
You are a little less audible, so you have to increase either your volume or you need to bring your speaker closer.
Okay. Is it fine now?
Yeah, it's better.
Okay.
Okay, so this will work actually. This volume will work, and I am like in 70% of my volume, so it should be fine. Yeah.
Okay, sir. Thank you.
Okay. Yeah, slides are nice.
Okay.
Okay, Surajit.
Yes, sir, I'm back.
Yeah, let's try once basically.
I'm sharing. Yes, I'm doing.
So you're going to talk about many body quantum chaos.
Yes, sir.
Just chaos is hard enough for me.
So.
Yeah, I see your slides actually. Yeah, chaos in structured class. Yeah.
Okay, is the cursor is visible?
Cursor is visible.
Okay.
Just a bit. So your so you want to increase the size a bit, or are you on full screen already?
I'm actually in the full screen mode.
Okay. So this will work. This is beautiful.
Is it?
No, this is work. I can see your.
Okay.
So it's, yeah, basically okay. Okay, great.
Okay, thank you.
So you can stop sharing and then Shumiran can put up his initial slide, and then we can take a break for a few minutes and come back again in 2-3 minutes. Thank you, Shumiran.
Yeah, should be okay. No?
Yeah. Okay. Make it full screen. Yeah, that's great. Okay, so I'll take a break. I'll be back in 2 minutes. Huh?
Sure.
Okay, great. So I hope everybody is having their tea.
I think this is not responsibility of our second.
I'll sound the claps now. We can all go back to the lecture hall.
I think it's almost time.
Yeah, I think it's almost time. So, let's go back to the lecture hall and start. Right. So a very warm welcome to all of you to this last session of today. And so the last talk, we saw a bit about wild semi metals, which talked about the, let's say, twofold degeneracies. And Shumiran, our next speaker, is going to talk about probably threefold degeneracies. So triple point for sure. And nexus fermions. Okay. So over to Shumiran.
Okay, thank you. Am I audible?
Yeah.
Yeah. So thank you, Chair, for the introduction, and good afternoon, everybody. And I would like to start by thanking the organizers to keep this going in this online mode. And I have to say that I am also missing the banter and the relaxed conversations in a physical situation, but we do what we can. So what I'm going to talk to you today is about the band topology of what are called nexus triple point fermions. And as Amit said, they are triple point degeneracies. So I'll define or describe what they mean. And so this work has been done in collaboration with Ankur Das, who was a graduate student at University of Kentucky. And now recently he has moved to Weizmann for a postdoc. And the details of the work are available below. So let's start. So what are these nexus triple point fermions? So as we said, there are some triply degenerate points in the Brillouin zone, and the low energy excitations, if they're coming from around those points, they are called triple point fermions. And then I'll go to what nexus means in this context. So we know that in 3D, doubly degenerate points are not exceptional, and these are more familiarly called Weil fermions. But you can also have 3 and higher fold point degeneracies in 3 dimensions, but they require certain symmetries to be present, certain crystallographic symmetries. Additionally, you can also have line degeneracies in 3 dimensions, but they also require symmetry protection. They are often called nodal line semimetals. And so in this context, the nexus triple points, they are essentially triple points, triply degenerate points that are connected to each other by line degeneracies, or in other words, line degeneracies which terminate in triple points. So these points have been called nexus points. They also require symmetry protection, and there is a host of candidate materials which have been predicted to host such nexus triple points. And this particular nomenclature of nexus comes actually from a precursor work of Heikela and Volovik. They were thinking about line degeneracies in graphitic systems joining at these nexus points. But okay. So these nexus fermions are, in a sense, what have a beyond Weil structure, and that's the reason for this talk. So Weil fermions, we know how to understand their topology, band topology. So in this, on the right figure on the top panel is a cartoon or a schematic of a Weil fermion, and we generally talk about this topology by surrounding the point degeneracy by a sphere, and on the sphere I have a completely gapped spectrum, and I can calculate some topological invariants, in this particular case, Chern number. Whereas this nexus fermions, the band structure is as follows. As I mentioned, they have line degeneracies present in the band structure. So this is a particular example. Let's not concern with the details. This is the Brillouin zone on the left side top panel. And this line, this blue-red line, is a line degeneracy which threads through the Brillouin zone. And because of this line degeneracy, when I enclose that triple point, and these line degeneracies actually meet at these black dots, there's actually a triple point sitting. So on the red part, 2 bands are degenerate. On the blue part, 2 different bands are degenerate. And when we surround this triple point by a sphere, similar to, say, the Weil fermion, they actually have gapless points on the sphere. So we can't use the technology of Chern numbers. And so that's why we started thinking about how to describe the band topology of such points. So I'll start the story in 2 dimensions. So I'll skip the details, but we are familiar with 2-dimensional Dirac cones and even quadratic band touching when we have a bilayer system, and they have interesting physical effects, but we often use Berry phase windings to describe the Dirac point topology. So these are the Berry phase formulas that we routinely use to calculate these band topology, the Berry phase windings around the degeneracy. They were flashed in the last talk as well, so I'll skip that. And this is a very standard argument for why a Dirac cone has a topological aspect. I will skip the details, but I'll just say that if you follow the technology, you will find that there's a Berry phase of pi that is independent of the parameters of the Hamiltonian. It is, in this sense, it's a topological object. And the same idea extends to higher dimensions where we get Chern numbers. What is helpful for me to describe what comes next is that these Dirac cone wave functions, instead of doing the calculation, I can actually look at the wave functions. So the details are on the right-hand side. But if I just look at one loop which surrounds the Dirac cone degeneracy, and I just look at the phase factors that are inherent in the Dirac cone wave functions, we see that they have a sense of winding when I loop around the degeneracy. And this topological aspect is essentially capturing this fact about the wave functions. So now, since we know that these nexus are actually beyond while, let me first start by going beyond this Dirac idea in 2 dimensions. And so I would, the basic generalization consists in going beyond 2 bands if we want to have semi-metallic or degeneracy condition. And this is a simple generalization of a 3-band case, but this is still within the Dirac or while terminology and or condition or system, and I can use Chern numbers and similar ideas to characterize the band topology. But let's look at instead this 2-dimensional generalization, 3-band generalization, and its spectrum in 2 dimensions also now has a triple point degeneracy, obviously at p equals 0. But now we have these line degeneracies that sort of come out of these triple point degeneracy, very analogous to in 3 dimensions. I hope you can see the line degeneracies. And this line degeneracies is what makes it beyond Dirac in some sense. And the way to understand the geometry or the wave function geometry of this situation when we have these line degeneracies is that, first of all, we can't do any Berry phase calculations, but I can still monitor the phases of the wave function. So now there are 2 different phases because the 3-band, 3-index wave function, and both wave functions, it's easier to see on the right panel, actually shows a discontinuity when I circuit the degeneracy. So this is the cause of beyond Dirac. And the actual geometry, the way it works is that the 3 bands are actually intertwined with each other, which in other words means that when I hit a line degeneracy, as I'm looping around the degeneracy, I actually have to cross over to the other band. And that's how I can analytically move if I want to move around the degeneracy. And so this is a special structure. This is a contrasting model where also I have line degeneracies, but you don't have this exact intertwined band structure. So let's skip that. But the main message is that I have to analytically move across line degeneracies. And this idea will help us to describe the band topology of nexus fermions in 3 dimensions. So for this toy model in 2 dimensions, we can actually explicitly write down the eigenfunctions. And the benefit of that is in the eigensystem, you see these factors of e to the I theta for a loop, circular, symmetrically located circular loop around the degeneracy, which is actually is a non-analytic function, and it requires Riemann surfaces to describe it analytically. And so in this toy model, this aspect becomes explicit. And so this then allows us to give a winding number description of the whole idea. So in this particular case of the 2-dimensional model, because of these e to the I 2 theta by 3 factors, what we find is that as I move in the parameter space around the degeneracy, as I described before, I have to cross over into the other bands. But then if I want to return to the starting point in the system or in the whole system space, the parameter, the Hamiltonian, and the eigenfunctions, then you can convince yourself that you have to actually make 3 circuits around the degeneracy before you return to the same point. So you need 3 circuits to come back to the same starting point. But in the process, what you will find is that the wave functions actually wind not thrice, but twice. And so this mutually prime way of how this parameter and the Hamiltonian is winding with respect to the wave functions is what you can call as a beyond Dirac property. And all the Dirac and other generalizations of that don't have this mutually prime property. So this very basic idea, maybe I went a little too fast, is relevant to the 3D problem because this beyond while structure, as we saw in the second slide, that when I surround the nexus triple point degeneracy with a sphere, I have a point degeneracy sitting on it. It's actually a 2-fold point degeneracy. So to describe the band topology of a single nexus triple point, I have to handle that point degeneracy in some way. So I have to find a language or some method to describe something that is topologically invariant even when this point degeneracy is present on this enclosing sphere. So the same thing actually happened in our 2D toy model, which is, and here found that any loop which enclosed a 3-fold degeneracy in the 2D toy model actually always encounters these line degeneracies. But then we understood we could actually explicitly work out in this case that this is this Riemann surface structure, and whenever I encounter the line agency, I move to the other band and so on. And so these gapless points, this model teaches us, are not really a fundamental roadblock to describe the wave function geometry, and rather analytic movement across them is what governs the geometry. It turns out for this 2D case, we don't have to do this analytic movement and go across to the bands and circuit 3 times to describe the wave function, essentially to give a binding number description. We can actually use the usual Berry phase techniques, and I'll skip the details. It is possible to give a non-abelian description by doing a single circuit around the point degeneracy. But it turns out this, at least I don't know how to generalize this way of capturing the 2D nexus geometry or band topology to 3 dimensions. So that is still an open problem. So the way we go ahead is as follows. So we have this nexus triple point, and we are considering some sphere which surrounds it and which has 2-fold point degeneracies. And I need a way to state some topologically invariant data of the situation. So the way I will do it is by stating the analyticity behavior near the point degeneracies, because as we have learned already, the point degeneracies are not a fundamental roadblock. So whenever I encounter it, I move it to the other band. Another way of saying it is let's start with the case of the Dirac fermion, again in 2 dimensions. This is the eigensystem, but the same eigensystem has 2 very important, one important properties. The first property is if I'm on a gapped loop around the degeneracy or wherever, in fact, the wave function, when I go around the loop, comes back to itself. This is a clear, obvious property. But the interesting thing, analyticity property of the Dirac point degeneracy, is that if I just go by, if I circuit the loop halfway around, so theta plus pi, it's the exact wave function of the other band. So that you can just verify with this wave functions. And so what this teaches us is that if I hit the point degeneracy, I just have to go to the other band. But in this precise sense, in the sense that when I come from one direction, I go out in the other direction. This is what analyticity is teaching us. This is how I have to analytically move in this space. So for Dirac points, it's easier to show the energy spectrum. So I've shown it on this left panel. But really, we can concern ourselves with just this right panel and imagine these 2 surfaces are the parameter space, so Px, Py. And if I want to analytically move in this Px, Py space, I actually need 2 copies to fully analytically move. If I don't hit the point degeneracy, I can just move any which way. I don't care. But if I'm moving and I hit the point degeneracy, then I necessarily have to go to the other copy of the Px, Py plane. And then I'm as if I'm moving analytically again. So you might think of it as 2 bands on a single copy of this Px, Py plane, or a single band, quote unquote, single analytic band on this generalized domain with 2 copies of the Px, Py space. And the same idea carries over to other cases. For example, for the 2D quadratic band touching, so this yellow dot shows the quadratic band touching. So here, analytic movement, when you touch the point degeneracy, actually forces you to remain on the same copy. Okay, and so the one way to see it is think of this quadratic band touching as resulting due to the mixing or combination of 2 Dirac point degeneracies. And then you go to the other plane, come back, and you just push them together, and you have to stay for analytic movement. And a similar way, you can state the analyticity information for the 2D nexus problem that we saw before. So this information we had already seen diagrammatically, and this is just a different way of stating the same information that we saw before. And the generalized winding number, they're all different ways of saying the same thing to a certain extent. And the main thing that underpins all of this is analyticity. And but since we want to focus on a 2D sphere surrounding the nexus point with the point degeneracy, now I have to deal with this. And so if I want to do that, I'm forced to consider this idea of the generalized domain, this right panel, or in the previous slide, this right panel, these 2 copies of the Px, Py plane is forced on me if I want to move analytically. And similarly, the 3 Riemann surface structure for the 2D nexus band structure. So with this basic understanding of analyticity, we can now go towards characterization of the nexus points. So the nexus point, again, the 2D nexus point that I had written before actually can be recasted in this form. Px plus these lambda matrices are what are called Gelman matrices. So for 3x3 matrices, you use them. They're often convenient to express the Hamiltonian in a 3x3 basis. So the 2D nexus Hamiltonian looks like this. Turns out there's an additional structure, an SU3 structure of the 2D Hamiltonian, and there's some extra details which I skipped. You can find it in the paper. But I'll start this as the base case where we know how to analytically move for this Hamiltonian. It is the same Hamiltonian as before that I've described, the 3 Riemann surfaces and all that. And to this, I will add quote unquote mass terms. So in the very same sense as if I had a 2D Px sigma x plus Py sigma y, and then I add a Pz sigma z. So similarly, I will add a Pz lambda 8. It has a certain structure. When you add this, what you find in the 3D momentum space around the nexus triple point. So the nexus triple point is at p equals 0. I get 2 line degeneracies. Okay, so that is the result of adding this kind of a mass term. And then when I do this, now I know that on the surface, on the sphere that encloses the nexus point degeneracies, there are actually 4 points where I have point degeneracies. So but now I will go to the generalized domain. So since this is a triple point, I actually need 3 copies of the sphere in this case. So that is the difference of the nexus fermions as compared to wild fermions, where you need 2 copies if you want it. Of course, for a wild fermion, you can enclose it without any point degeneracies. But for this nexus case, you are forced to have 3 copies of the sphere, and that forms your generalized domain. And these spheres are connected to each other through these points, through these point degeneracies. So for example, the first band is connected to the second band at these points that are shown here, and the second and third are connected at these points. And on this generalized domain, I now can draw non-contractible loops. So non-contractible loops, we are familiar, are topologically invariant data, and they're quite reminiscent of how we describe the topological difference between a sphere and a torus by non-contractible loops. So I can do the same game. I can use the same visualization or imagination to describe something that is a topologically invariant data. So this is the example of non-contractible loops that I can draw for this particular nexus triple point. And I'll give 2 more topologically distinct examples. And so the count of these count and types, so there are different kinds of these loops. For example, this set of loops does not touch any point degeneracy. This kind of loop, for example, the one on the red actually starts on red, ends on green, then goes back to red. So it touches only 2 point degeneracies, whereas these loops actually touch all the point degeneracies. These count and the types of the loops actually are topologically invariant data for the nexus fermions. So these are the 2 other examples. So one is a different kind of diagonal mass term that you can have in a 3x3 matrix structure, which has only a 1 line degeneracy. So this is actually quite similar to the example that I introduced before, but it turns out that this is actually topologically distinct than this kind of a single line degeneracy. So if I just focus on this point, it turns out that the band structure details are such that this the point degeneracy on the sphere enclosing the nexus point is actually a quadratic band touching, whereas here it is not the case. So therefore, you can actually, the loop drawing, for example, look at this loop in the middle panel on the right side. It touches the point degeneracy and then stays on the same loop. And this kind of loops you can't draw for this case. So that is how you distinguish between these 2 cases. And so this is a very reminiscent way of describing, this is sometimes called the homological description, how these 1 cycles are topologically distinct 1 cycles you can draw on your geometric surface that you want to describe the topology of. So in this case, I have to do this extra step of that whenever I encounter these points, I have to go to the other surface and so on, other copy of it. So that brings me to the conclusion. I hope I was able to convey the basic idea of this, what our work consists of. This whole drawing non-contractible loops idea was covered in a second paper, which we had not realized when we wrote the first paper, obviously. And so this is the main message of the talk. The future questions are, is there some generalization of the standard Chern number or Berry phase technology in 3 dimensions? We don't know. One physical consequence of these nexus points and the fact that they have a topological character is that there are implications on the Fermi arc behavior in these systems. And so we have discussed this point in this preprint. If you're interested, you can have a look. That is a more physical manifestation of these systems. There are more general mathematical physics questions, which is the general homotopy classification of nexus bands, which is the effort is being led by Eyal Confed at Weizmann. But I would like some constructive techniques, more in the spirit of Berry phase technologies. And with that, I would like to acknowledge Ganpati Murthy for some initial conversations, my funding sources, and ICTS, where the second paper was actually a lot of discussions happened there. And thanks a lot for your attention. And I would just take 10 seconds to highlight a recent work of a postdoc here at IIT Bombay, Shantanu Pal, who didn't get a chance to present his work. This is a collaboration with me and Hitesh Changlani at FSU. And it's in quantum magnetism, and it relates to some of the points described by Ganesh and others. And this is the archive preprint. If you're interested, please have a look. So thanks again. Hi, Arnav. I see your raised hand.
Yeah, so I guess I can ask the question if the chair permits. Okay. So, yeah. So I was just wondering regarding these nexus points, since they have this interesting topological character, is there some simple thing in transport also which sort of brings out this point?
Yeah, that's a good question. I don't know the answer to it. I mean, I don't know how to understand it. And maybe Amit has something to say about it if he has thought about it. But I'm also thinking about it, but I don't have a way of thinking about it, frankly. I mean, there are people have studied the Landau level structure, so you can get some clues, but I don't understand it well.
I see. Because somehow it seems that there should be some way, but okay, yeah.
Yeah, there must be some way in the Son-Spivak sense, but it is slightly beyond that. So at least I don't know. This is something that I'm thinking with Hitesh Pal here, but we don't have a clue really at this point.
I see. Okay.
Yeah, so I think a priori it is not obvious actually what specific signatures you can think of. But I mean, initially I would think of signatures probably in the surface states or
Yeah, surface states, we have some remarks to make. So this Fermi arc stuff that I mentioned. So maybe I can just say one sentence that, when you have a regular while points, you get the Fermi arcs, which you can think of it as slices of Chern bands, right? So on certain 2D slices, you don't have Chern number. On certain 2D slices, you do have Chern number. So if you think from that point of view for these triple points, what you find is that certain slices, the line degeneracy is occupied, if given the many-body chemical potential, whereas certain slices, they are not occupied. But both cases, the Chern number are 0. But whenever the line degeneracy is occupied, there is a non-zero topological invariant that you can define with the chiral winding number. So that has to go on something. There has to something has to happen. And in numerical simulations, they have seen Fermi arcs and surface states. So what we believe is that since the Chern number is 0, these are probably two counter-propagating modes. But we don't know. So that's a separate research project of what is the edge state phenomenology of when you have chiral winding numbers as a topological invariant instead of a Chern number.
Yeah. Okay, so we have a couple of more questions. So Avdesh.
Hi. Can you hear me?
Yes.
Yeah, this is Avdesh Nayan from IFC. Hi. Thanks for the nice talk. So I have maybe two small questions. One is that if I want to write down a lattice model for some of these, what would be the symmetries that they should obey?
So in the lattice case, I know the symmetry. You mean what crystal symmetries protect them or something beyond this?
Yeah, something along,
The crystal symmetries that I know, so I wrote space group 220 in some of the slides, right? The particular symmetries which protect these nexus line degeneracies are threefold rotations around Z-axis. and a mirror around x-axis, but the 3 symmetry-related mirrors. So then you can make an argument that you have to have these excess.
I see, and that would be sufficient to generate all the different let's say different classes of the classification that you showed, or do we?
No. So the first two that I put by putting the mass terms, they don't come from this class. So they might not be realizable in some real crystal. Maybe this was just our way to understand, make progress. Yeah.
Okay. And the other maybe short question is, what happens if you kind of break this degeneracy? Because I'm just asking because in case of these what are called these unconventional fermions, if you break these certain symmetries and then you gap them out, then certain interesting, let's say, other topological phases might arise. So does something similar also happen here?
Okay, I have not thought about this, but if you break the symmetry of, as you said, April, you would open up a gap, and then I'm not sure, but maybe there's something in this work. So they are coming at it from a very different direction. So they actually asked this question not for these symmetries, but a different class of symmetries, and they have some discussion on when you break the symmetries, but on the spot, I can't think of any interesting comment.
Okay, thanks a lot.
Yeah.
So just to add to that question, so suppose I lift the double degeneracy of the nodal line.
Yeah.
Then I get what, probably 2 band crossings, right? Which are both doubly degenerate.
Yeah, I would guess so. Yeah.
If you just lift the degeneracy
Of the the nodal line, let's say, along gamma A in your WC.
Yeah, then you will get like a spin 1 spectrum, no? At the
Then
point. Yeah. The spin 1 spectrum you can describe using Chern numbers again. So you will have similar chiral transport, I suppose. I think there's a paper by Vita and Roy. I was recently told that it has similar chiral, like sort of bulk transport as YIMQCMT fermions. But yeah.
Yeah. Okay. Ravi had a question, but I think that got answered.
Yeah, but I mean, it was about the lattice model. I think you already spoke about it.
Yeah.
The symmetries. But does he know the Sumiran? Do you know any specific Hamiltonians that you can use on any lattice where you get this?
Yeah. So these papers, right? So this PRX and even this, they wrote down real materials, and so they have some tight binding, effective tight binding models where you can just diagonalize that and see. So I mentioned. Yeah, and you can calculate Landau levels and so on. I have not done that, but it can be done.
Okay. So if there are no more questions, then let's thank Sumiran for a very nice talk.
Thank you. Yeah. Bye.
Okay, Sumiran. Thanks. And so we can. So Manoranjan, you can share your screen. Yeah, please share the screen so that we can start.
Okay, so you can see the slides.
Yeah, I see your slides. Yeah, very nice. So Manoranjan is going to talk about thermodynamic properties of strongly correlated systems using a combination of exact diagonalization and DeMargy techniques. So over to Manoranjan.
Okay, thank you, Amit. I'll start thanking organizers for taking so much pain to organize this conference and let it continue even in this pandemic situation. So today I'm going to talk about this thermodynamic properties of strongly correlated systems with hybrid ED DeMargy. So I'll first explain 2 model Hamilton, very simple models. And then I'll talk about the motivation behind this work. I'll briefly mention about the quantum phase diagram of this J1, J2 model, a frustrated spin model. And then I'll introduce this hybrid ED DeMargy. And then I'll talk about the application of this method to model the magnetic properties of copper germanate. Okay, so we'll start with very simple model, the Hubbard model on a 1-dimensional lattice. Here you can see my cursor, right, Amit?
Yeah, your cursor is visible.
So here you have the first term, which is kinetic energy term, the electron hopping term, and second term is the electronic repulsion term, and this is effective only when the 2 electrons come to the same site. this model is very well known for modeling the metal insulator transition. Unfortunately, this model can be solved only if you have a regular model. I mean, just no dimerization, nothing. Then you can use the analytical technique like Bethe and SAS to solve it. And also quantum Monte Carlo technique, only if it is a half-filled system. Okay, away from half-filled, you can't solve it. If you have some kind of dimerization, there's no way you can solve these systems. And in large U limit, you know that the charge degree of freedom is going to be frozen. Only the spin can be active. And then you can map this model to spin models. So I'll take another model Hamiltonian, which is frustrated 1D spin model Hamiltonian. Here I'm showing you the cartoon picture of these frustrated spin system, where each spin is going to interact with their nearest neighbor and next nearest neighbor. And if you take J1 as an antiferromagnetic, which is nearest neighbor, and J2 is next nearest neighbor, also antiferromagnetic, what you see is both wants their nearest and next nearest neighbor to be the antiferromagnetic, and which is impossible. So then what it does is it gets frustrated. Okay. And with certain values of ratio of J1, J2, what you find is neither it is going to like align antiferromagnetically or ferromagnetically, but it is going to be completely non-collinear behavior. I mean, the spin arrangement is such that the two neighboring spins will have some certain pitch angles. This is what in cartoon I'm showing you. This model Hamiltonian can be written like this. This is first term, which is nearest neighbor. This is exchange term, and then second nearest neighbor, J2, is representing the second nearest neighbor. Alpha will be using some time, and this alpha is just ratio of J2 by J1. Why I'm like using this model, because like this J1, J2 model, a very interesting phase diagram. And if you take the antiferromagnetic J1, and J2 should be always antiferromagnetic, otherwise there will be no frustration in the system. So this all interesting thing happens because of you have J2, which is antiferromagnetic. So if you start with J1, which is antiferromagnetic, you will start with antiferromagnetic gapless phase, and you have a quasi-long range order in the system. So if you crank up J2, you go to the dimer phase around 0.2411. When the ratio of J2 by J1 is 0.2411, you open a small gap, and as you keep going up at ratio 0.5, you have a Majumdar-Ghosh model, well celebrated, exactly solvable model in the ground state is at least. And then if you further crank up the J2, you have incommensurate gapped spiral phase. And if you go further up, you have completely decoupled phase. So basically this system behaves like there are two chains separated from each other. And if you start from the ferromagnetic side, basically J1 is ferromagnetic, then you start with ferromagnetic ground state, which is gapless. You have a long range order. You go further up around at ratio J2 by J1, mod of J1, basically. Then you go to the incommensurate phase from ferromagnet to the incommensurate gap phase. And then further up, if you go again, go to the decoupled phase. Okay, so I mean, mostly, I mean, for these systems, the ground state properties are more or less well settled. But the problem is how to solve the finite temperature. I mean, most of the techniques will give you the ground state. I mean, especially DMRG, low dimension is going to give very good, very accurate ground state. But if you want to like heat the sample, and you know that most of these systems will have finite temperature. So, I mean, you want to explore that. And what you find is if you have a frustrated system or fermionic system, which is away from half filling, it's very difficult, okay, to solve. The first reason you'll say that, okay, why not I'll use the exact dilation? Then you'll be immediately finding out that you cannot solve it for very large system because the degree of freedom goes exponentially. with the system size. Then quantum Monte Carlo, as I said, this is going to work for a spin system like SSE kind of quantum Monte Carlo, that is going to work very well for non-frustrated system. Even for fermionic system, if you take the quantum constant path quantum Monte Carlo or auxiliary field quantum Monte Carlo, those are, again, it's restricted to half-filled system. If you are going away from half-filled system, you have a sign problem. There are DMRG-based temperature-dependent numerical techniques like transfer matrix renormalization group method. Again, this will have the same problem that if you go to the very low temperature, you have a problem with the convergence, and your accuracy is going to deteriorate very quickly. Sorry. Then there is another method which was proposed by the Steve White and group, which is Ancilla-based method. This also works well only for high temperature, and T by J, if you take it, is going to be in that range. And also valid for only short range. So if you take the long range Hamiltonian, it's not going to work out. And we are interested in a temperature range where like it should be valid, it should be sufficiently low so that your quantum fluctuation and thermal fluctuation both should be competing. And that's where all the interesting stuff are there. Okay. So our goal is to design some method which can give a reliable result for all temperature regime. So we proposed hybrid ED-DMRG method. Why it should work? At high temperature, you know that your correlation length in the system should be very small because of the thermal fluctuation. And if you sufficiently go to low temperature, then your correlation length is going to be large. In that case, we'll be using the DMRG method. In general, DMRG is very good for ground state and some of the low-lying state, and it's well known. Okay, so I don't want to go to in details of the DMRG because there is a lack of time. So what I will do is I'll just give the overview. So DMRG is based on the systematic truncation of irrelevant degree of freedom. So you start with very small system like four side, and you grow the system to step by step. And every step you throw out all the irrelevant degree of freedom. Okay, so in that case, how do you throw it? So you know that if you have some operator A, and if you have density matrix of that particular system in the ground state or any specific state, then you construct the density matrix and multiply with the operators, and take the trace, you get the expectation value of that particular operator. Okay, or you can do is you diagonalize this density matrix and go to the diagonal basis and then calculate the expectation value of A. And here W is your eigenvalue of the density matrix, and I is and this is your wave function of the density matrix. And you see that if your W is very, very small, then what you can do is you can just get rid of that and or just throw it out. And it's not going to change the significantly to your expectation value of A. So in that case, even in the truncated basis, if you have ignored all the relevant degree of freedom, still you get the very accurate expectation value of A. DMRG exactly works on that principle. Okay, so if you know how to manipulate your density matrix, you can solve most of the system. Okay, so all the tricks are playing with the density matrix. Okay, so what I'll do is I'll be using the finite periodic boundary condition for one-dimensional system, which is a very, and we'll be using a very efficient algorithm which was developed by our groups recently. And okay, so that's another thing which if people are interested, I can talk about that later. So to get this, okay, so I was talking about this density matrix. So you have to manipulate the density matrix. See, we are interested here in DMRG to get some of the excited states. When I talk about the excited state, we are talking about hundreds of excited states. Okay, so to do that, what you do is like you take a projection of density matrix from every higher excited state and take the and do it with certain probability, and the probability is decided by this Boltzmann factor. So E is I mean, you can think of K beta T, and this Q is a constant normalization constant. And here rho J is density matrix projection from all the different higher excited state. Okay. So, okay, so let's try to make the partition function. So you know that for a spin model or a spin half, your degree, the energy spectrum will have 2 to the power n number of eigenstates. Okay. So partition function can be written in sum over all the energy state with a Boltzmann factor like this. And if you want to go for, so you see that if you want to go for, you are at very high temperature, every state will contribute. But if you come to the low temperature, okay, so then you please see this expression where you can write the partition function. You can take out this ground state energy part, and then it is just some 1 plus sum over exponential with minus beta delta and j. So basically this gap delta j is what matters here. And if your beta is very large, means you are at sufficiently small temperature, then only few of the eigenvalue, I mean this gap will contribute, because larger delta is going to make the whole thing vanish. So what you have to worry is only few eigenstates from the only few low-lying eigenstates. Okay, I hope this is very clear from this expression. Okay, so let's see what happens like to your gaps when you are doing the DMRG. So you can do the calculation for a spin half system, like for n is equal to 20 and 32 also, using some symmetry and all. So here I'm comparing the 10 lowest lying excited states. So these are gaps, and you see that these are so accurate. So almost like your highest error in the calculation or the gap is going to be less than 0.1%. And you know that it's exponential factor, right? Even 0.1%, I mean, this kind of a error is not going to like matter at all, especially for the low temperature.
So Manoranjan, you should converge in 3-4 minutes.
Okay, very good. I'll do that.
Thanks.
Yeah, so here I'm showing the Heisenberg antiferromagnetic spin half system, which can be solved using the quantum Monte Carlo. Okay, and here these circles are quantum Monte Carlo result. It's very accurate. For this particular system, quantum Monte Carlo is very accurate. And you see that it really passes through every line. And this is C by T curve, and this also gives you very accurate result. And these arrow represents the zero temperature calculation, which is solved in these papers, and the quantum Monte Carlo we have taken from Sandvik's paper. Okay, so the most challenging one is the Hubbard model. And for DMRG especially, if you can solve the tight binding, which is where we have the highest amount of error, and if you can solve that, that means you can solve any interacting model, especially Hubbard-like model, because in Hubbard you have just on-site interaction, and there is no renormalization of these operators while forming the super block. Okay, so what we do is like we can test these calculation for the tight binding limit, and we can solve this exactly just by doing the band picture, right? So then what we do is like we solve it for tight binding, one-dimensional tight binding model. And this is for half-filled system. And you see that your red curve is the exact calculation. And these are for different system size. And the 4n, 4n plus 2 system are going to converge from two different, one from up, other from down. And then it should converge to a certain point. And from there, you can calculate everything. This is S by T and so on. So it really works very well. This has been just communicated. Okay, so let me talk briefly about the application of this one, this technique. So we talk about this copper germinate, which is very classic system, and in the olden days, in 90s, 95 up to 2000, almost all the, I mean, lots of people try to model this. Unfortunately, most of them model only the high temperature part, and low temperature part was not done. And actually, this Castellas, Chakrabarti Emery, and these people thought that it is in the gapless regime, whereas the other people thought that it is in the frustrated regime where the gap opens. So it was still like lots of PRL and everything what got published, but never got resolved. So why you have to, why it was not got resolved? Because of the reason that you have to optimize the or minimize the your free energy to get this equilibrium dimerization at various temperature. And you know that at low temperature you can't do that with other techniques. So when we developed this, then we thought, why not let's take a chance to see that what happens. And then we minimize this energy, and you know that dimerization, this electronic dimerization is going to be opposed by the electron phonon electronic vibration, phononic vibrations. So in that case, these two should make an equilibrium, and you have and just by doing this minimization, you can calculate the equilibrium dimerization. So I'm going to move fast because
I think you're going to the summary, right?
Yeah. The next is summary. Okay.
Okay, great.
Okay, so I'm skipping this. So here I'm showing you the modeling of spin parallel transition of this copper germinate, and you see that this is just by doing all this calculation, and you have to, for every like temperature, you have to get the equilibrium dimerization, and you see it fits very well, and even the specific heat fits very well. And we actually did even the neutron scattering. So with one parameter, we can fit all sets of experiment. Okay, and with that, I'll conclude my talk. So with this summary slide, I'll finish, and I'll thank my collaborators and thank all of you for your.
Yeah, thank you, Manoranjan, for the very nice talk. So we'll take a few questions if we have any. I don't see any raised hands, so let's say we have an open mic. If anybody has a question, he can ask. Okay, so we do not seem to have any question actually, Manoranjan, for you. Okay, so great, very nice.
Amit, sorry, can I ask?
Yeah, please go ahead.
Okay.
Yeah, my microphone was echoing, so I have to move to a different computer. So Manoranjan, the benchmark results that you showed with the 0.1% accuracy, can we go back to that table?
Yeah, sure. Yeah, this one or spin system?
No, the benchmark for the method that you showed with 10 different levels.
Gap you are saying, right?
Yes. So this is for what model?
This is for this is for just Heisenberg, simple normal Heisenberg, like a HAF spin half.
Yes, but I mean, if it's a simple Heisenberg nearest neighbor model, then I mean, this matching is not surprising, right? I mean, the debate in the community is not about the levels of the simple Heisenberg. So if you now put in a J2 and go to a limit where the chains are, let's say,
by the way,
close to the disconnected point, do you still expect this kind of accuracy?
Sure. This is where the finite size effect is very bad. After if you go once you introduce J2, okay, and you are in gapped regime, your correlation length decreases, so your calculation converges very fast, and also the accuracy improves. Unless and until you go to the very large J2 limit, again there is a problem because of degeneracy.
Yeah, so it is in that limit that the method is problematic, because if you remember in the...
No, but when we are saying this, we are talking about J2 is equal to 2 or so. And so basically in completely decoupled limit. Okay. Otherwise, if you go to 0.5 or so, we have done it and it's very good.
0.5, of course, is a completely gapped system. It's Majumdar.
No, even you take like 0.6, 0.8.
Yeah.
There's no problem.
Okay, we can talk about it later.
Yeah.
Thanks.
Sure.
Okay. So if there are no other questions, I see no raised hands. Okay, so let's thank Manoranjan once again for the very nice talk.
Thank you, Amit.
Yeah, you're welcome. Okay, so you can disable sharing your screen, and I would request Sayan Lahiri to start sharing his screen. And Sayan is going to talk about correlated photon pair propagation in circuit QAD with superconducting processors. So over to you, Sayan.
Yeah, thank you, sir. Good afternoon, everyone. Today I'll be talking on the correlated photon pair propagation in circuit QAD with superconducting processors. And I thank the organizers for allowing me to present my research work. So this is the content of my talk. So first, the motivation. So about the motivation, I say that the phenomena of pairing plays a very important role in different areas of physics. And one of the pairing we see, one of the cases we see in the Cooper pairs or the superconductors. But the pairing of bosons in atomic or molecular system is not stable, meaning it's not, one cannot find a stable bound pair in the atomic system. But using the interacting photons, it is one way to achieve a stable bound pair is using a set of interacting photons. And one can use the method, or one can use the circuit QED system to simulate the phenomena of the pairing of bosons. So here in the circuit QED system, we actually we replace the real atoms by artificial atoms, which is made of Josephson junctions. And the photons are stored in the on-chip resonator. And these Josephson junctions actually gives rise to these different enharmonic potentials. And by appropriately tuning the enharmonicity of the system, one can get either a 2-level qubit system or a 3-level qubit system, whatever it is desired. But for our case, we have considered a 3-level qubit system. And here I have shown the cartoon picture where you see for the qubit system, there is only 2 levels and the allowed transition is within the red arrow, and rest of the levels are actually discarded. Similarly, for the qubit system, it is only their allowed transition is between only the 3 levels, and rest of them are discarded by yes. So now let me come to our work. What type of model we are using? What type of cavity array we are using? So here we see that this is a coupled cavity array system where each cavity contains a superconducting circuits, and these cyan lines are the transmission line resonators. The deep blue lines are the Josephson junctions, and the red ones, these are the gate couplings. And the equivalent lumped circuit, meaning what is inside the equivalent lumped circuit of one particular cavity, is represented here, where we have shown the Josephson junctions in red color, and rest of the capacitance or inductance are used to couple with the microwave resonator. And in figure C, we have I have shown the energy level configuration what I am using. So here we are actually driving the 3-level system using the same laser, and the associated enharmonicity to the second excited state is alpha. Now, now let me talk about the JCH model for a 2-level system. So a series of coupled cavity array with each cavity having a 2-level atom interacting with the photon can be explained by JCH model. And the first term, which is this term, this is the Jens-Cummings term, which is the atom-photon interaction term, and the second term is the photon hopping term, which is the Hubbard type hopping. And this JCH model for a two-level system has been widely studied in the literature of cavity QED. And this physics of the two-level JCH system is very well known. So we get a normal superfluid to Mott insulator transition. And this phase diagram, the left-hand side is the phase diagram that is obtained using this side decoupled mean field theory, and the right-hand side is the diagram which is obtained by using DMRG, and the references are given below. Similarly, now if we add one more level to the two-level qubit system, so our Hamiltonian gets modified like this. So we have the extra coupling term, which is the coupling between level 1 and level 2, which is, and with the strength beta, coupling strength is beta 1, 2. And there is this alpha, which is the anharmonicity associated to the second level due to the laser transition. And here we define the total polariton number, which is the photon number plus atom number, and this is a very conserved quantity in the system. And here this three-level Jens-Cummings-Howard model is the only phase diagram that is obtained in this three-level JCH model is using the mean field theory by this Prasad Martin group, and this phase diagram is obtained for when this ratio beta 1 2 by beta 01 is for equal to 1. So we see that this higher Mott lobes are getting enlarged in this figure. Now what we are targeting is the following, that we want to investigate the pairing of photons or polaritons both in 1D and 2D. And in 1D we use the DMRG method, which is based on the matrix product state scheme states algorithm, and complement our result in 2D by using the cluster mean field theory method, which is an improved version of the side decoupled mean field theory. Now what we have done is the following, that we have actually tuned this coupling ratio, the beta 1 2 by beta 01, to root 2, and we have introduced anharmonicity, this anharmonicity to the second excited state. And we have and if we can tune the coupling between the photons of the adjacent cavities, and we get that get the Mott 1 lobe completely vanishes, and there arises this pair superfluid phase. This pair superfluid phase is characterized, and we characterize this pair superfluid phase by looking at the rho mu plot, this density versus chemical potential plot. And we see that there is a jump of two particles in steps of two particles or two polaritons in the PSA phase. And these Mott boundaries are calculated by looking at the different plateaus of the rho mu curve. Now, now we want to look more rigorously on in this pair superfluid phase. So here we have calculated the different correlation functions, and these the two correlation functions are one is photon pairing correlations, and two are the single correlation functions. So we see that when this hopping is very small, that is kappa by beta 01 is 0.01, we see that this pair correlation functions, which is represented by the black dotted line and this green solid line, these pair correlation functions are decaying very slowly or algebraically, and the single correlation functions are decaying much faster. It's exponential decay. This means that there is this pairing phenomena is going on throughout the system, through the coupled cavity system. And now if we increase this photon hopping strength, we see that these pair correlation functions are now decreasing much faster, and the single correlations are dominating. So the physics, so what is happening in the cavity system, here we have shown in the cartoon picture in figure C and D. So in figure C, we see that there can be three possibilities. One is that there can be zero atom and and the zero atom is in the ground state and with two photons, or zero photons with atom is in the second excited state, or there is one photon and one atom. So all the cases correspond to the two polariton case. And in figure D, we see that there are only two possibilities. That is, there can be atom in the first excited state with zero photon, and atom is in the ground state with one photon. Okay. Now what we do is that we complement our result by using this cluster mean field theory method, which is a robust version of the side decoupled mean field theory. So here we have considered a square lattice, and we have found that this pair superfluid phase is actually squeezed between mod 0 and mod 2, which we have also characterized by looking at the density versus chemical potential plot, and also by looking at these correlations. And
so you should
and for
start
the discussion, I said, yes, hello.
Yeah, Sayan, you should start summarizing.
Okay, yeah, sir. This is the last thing.
Yeah.
So, so the physics behind the system is the follows. That here I have shown the different energy versus beta ratio plot, beta 1 to a beta 0 1. So this black dashed curve are the single polariton energy. Red solid is the 2 polariton. Green dotted is the 3, and blue one is the 4, and the magenta is 5. So here we see that by changing this beta ratio, this is the energy diagram for a single cavity system. So by changing the beta ratio, so this system actually becomes goes from repulsive to attractive. So that is the reason behind this this pairing of polariton phase. So this although there is a pairing in the polariton phase, but this pairing occurs due to the propagation of 2 photons in the system. So so I conclude this by saying this. So our finding that we use a Q-treat system, and we are able to find this atom photon by tuning the atom photon coupling ratio and the photon hopping amplitude. We are able to find this pairing phenomena, and when we've shown the phase diagram using DMRG picture in 1D and cluster picture in 2D. Thank you, sir.
Yes, so thank you, Sayan, for a very nice talk. So questions? If we have a few questions, we can take them. Yeah, Manojan, please go ahead.
So, I mean, I was just wondering why there is when you're showing this step of 2, what exactly that means? Is it something that there is some kind of a condensation?
No, sir, it's a steps of 2 meaning, and the polaritons are changing in steps of 2 meaning. There are jump of 2 particles.
Why not 1? I mean, why there is a 2 polaron jumping? I mean, condensating at every time.
That is, sir, by tuning the ratios appropriately, if we can tune it to that value, so the system go to the attractive regime. So in attractive regime, you always get a pairing type phenomena, right?
Okay. So there is you are saying that there is a pairing. Okay.
Yes.
Sorry, I missed it. Okay, actually. Yeah.
Okay, so let's thank Sayan once again for a nice talk. And yeah, so let's go on to the next talk. So the next talk is by Ruchira. So can you please share the screen?
Yes,
and Ruchira is going to talk about out of equilibrium chiral higher order topological insulator, let's say.
Sir,
Please
am
go
I
ahead.
audible?
Yeah, you are audible.
Okay, thank you, sir. Good evening, everyone. I'm Ruchira from Department of Physics, IIT Bombay. So today I will present the work which we have done on higher order topological phases, which appears from a periodically driven trivial square lattice, pi-flex threaded square lattice. So before going into details of my work, I would just like to tell a few basic ideas of topological insulators. So topological insulators are characterized by a bulk gap and zero energy states that are localized at the boundaries of the system. For example, if we consider a 2D system, we can get states localized at the edges. For 3D system, states can be localized at the surfaces and so on. And recently, this idea has been extended to systems where we get zero energy states localized at dimensions lower than that of the edges. For example, at the corners of a 2D system, or at the hinges or corners of a 3D system, and so on, which are generally known by the name higher order topological insulators. And usually the first order topological insulators are classified by non-spatial symmetries like time reversal, particle Hall, or sublattice symmetry. Whereas the higher order topological phases, they are generally classified by, or they are generally protected by spatial or crystalline symmetries like inversion, mirror reflection, or combination of time reversal and rotation, fourfold rotation symmetries, etc. So in this work, we would like to study such a higher order topological phase, which is realized on a periodically driven trivial square lattice. So the outline of my work is like we study this periodically driven square lattice by two different methods. One is we study the exact dynamics using the Floquet operator, and the second method we use is a high frequency approximation using Brillouin-Wigner perturbation theorem, and the diagonalization of Floquet operator, as well as the diagonalization of effective time-independent Hamiltonian, which is obtained from the high-frequency approximation, gives us zero energy states that are localized at the corners of our square lattice, and they are also found to be protected by the chiral symmetry. So let us first try to understand the model on which we probe this higher order topological phase. So the lattice is as shown in the slide, and the blue arrows, it represents the allowed range of hoppings, and long range hoppings are allowed, but diagonal hoppings are not allowed in our model. And the pi flex threading through the square plane, it is represented by these dotted lines, where the hopping amplitude takes an overall negative sign along these dotted lines compared to the hopping amplitudes along these solid lines. And the on-site potential value is represented by AXY, and it is chosen in a special way so that the difference between the on-site potential values between neighboring sites, it takes a dimer-like pattern in the entire square lattice, which is represented by these red dots, and the dimer pattern appears as alpha beta throughout our square lattice. And we are modulating this on-site potential value by means of a square wave pulse as shown in equation 2. Now, to understand better, in the absence of this drive, whether our model possesses any topology or not, we analyze its symmetries when f of t equal to 1. So when we analyze, we see that it possesses only the time reversal symmetry, and the other two non-spatial symmetries, including particle Hall and sublattice, are broken because of equation 6 and 7. So when we look into the tenfold way of classification of topological insulators, we see that our equilibrium model belongs to class A1 with only the time reversal symmetry. And as we see in D equal to 2, we do not have any topological index. So our equilibrium model do not possess any non-trivial first order topology. Now, to understand what happens in the presence of the periodic drive, we use two different methods. Uh, One is we studied exact dynamics using the Floquet operator, and the Floquet operator is given in equation 8, and it is defined as the time evolution operator at integer multiples of time period, where this tau represents the time ordering operation, and the diagonalization of this Floquet operator will give us the quasi-energy spectrum. The second method which we use to study the time periodic system is a high frequency expansion, and the method which we use here is the Brillouin-Wigner perturbation theorem. So the corresponding high frequency expansion with first two terms is given in equation 9, And we have neglected the higher order terms here because the higher order term appears as 1 over omega square, omega cube, and so on. So under high frequency, we can neglect those terms. And when we apply or when we use this expansion to our model Hamiltonian, we get an effective Hamiltonian as shown in equation 10. So as we can see earlier in our model, the hopping amplitude was just jxy x prime y prime. But now after doing the Brillouin-Wigner expansion, we get an effective Hamiltonian where the hopping amplitude is renormalized to a complex value. And uh, after arriving at this step, we set the values of axy and ax prime y prime in such a way so that the hoppings between odd and even sides becomes zero, or we suppress the hoppings to the same sublattice by choosing the on-site potential values in a special way, thus restoring the sublattice symmetry in the system. And the corresponding effective lattice looks like this, and the same sublattice hoppings are suppressed. Now we have a four atom unit cell, and with intercell and intracell hopping amplitudes given by VR and WR. And under periodic boundary conditions, the equation 10 can be rewritten in terms of equation 11. And the corresponding sublattice symmetry operation is given by tau z times sigma 0, where tau z and sigma 0 are Pauli matrices that represents these sublattices. And when we again look into the classification table, now our effective model belongs to class A3 with only the sublattice symmetry. And as we can see in D equal to 2 in spatial dimension 2, we do not have any first order topological index. And hence this model, the effective model, do not possess any first order topology. But when we diagonalize the effective Hamiltonian, which is obtained from the Brillouin-Wigner theory, as well as the quasi-energy spectrum, which is obtained by diagonalizing the Floquet operator, we see, so figure A and C, A represents the energy spectrum of effective Hamiltonian from Brillouin-Wigner theory, and C represents the diagonalization of the quasi-energy spectrum. So we see that we have fourfold degenerate zero energy states. And when we look into the distribution of this zero energy states, we see that they are localized at the corners of our square lattice. Since we have the
Actually, you should
hopping.
summarize.
Yes. We define, since it do not possess any first order topology in spatial dimension 2, but if I look into the lower spatial dimension, we have a topological index which is represented by Z. And as we can see, the edges of our effective square lattice is also a dimer chain, which is sublattice symmetric. So we define our topological 2D topological invariant from the corresponding 1D topological invariant, which is the winding number given in equation 13. And the corresponding number of corner localized states is given as 4 times the 2D topological invariant. So the figure, the results here represents the 1D and 2D correspondence. So figure A represents the winding number for the set of parameters that gives winding number equal to 1 along the X edge, and figure B represents the winding number of Hamiltonian, edge Hamiltonian along the Y direction. And figure C, this represents the diagonalization of our effective Hamiltonian, 2D Hamiltonian, and we get the expected zero energy states, eight zero energy states. And these are also found to be protected by the chiral symmetry. Since when we add symmetry breaking perturbations, it will lift these states away from the zero energy. So summarizing or concluding my work. So in this work, what we have found is we get chiral symmetry protected zero energy corner states out of a periodically driven trivial square lattice, and they are protected by both the bulk as well as the boundary gap. Hence, they belongs to the classification of extrinsic second order topological phase, and the corresponding invariant is also defined from the 1D winding numbers. Thank you.
Okay, Ruchira. So thank you for the very nice talk. We are
Thank
open
you.
to questions now. So I don't see any raised hands. So yeah.
Can I ask a quick
Please
question?
go ahead. Yeah.
Ruchira, I'm just thinking, what is the motivation behind using this very special kind of long-range hopping in your model?
You
Hello,
mean?
can you hear me?
Yes, I can hear you.
Yes, the question is, what is the motivation behind using this special type of long-range hopping in the model?
Okay, so actually the long range hopping allows me to access higher boundary.
Yeah, no, but there is a very special type of long range hopping you're using, right? It's not that it's long range from any side to any other side, right? So as I could see that there is no long range along the diagonal.
Okay, actually I want to preserve only the sublattice symmetry in the system, and the way which I choose the long range hopping allows me to do that once I calculate my effective Hamiltonian, time independent Hamiltonian.
Okay. Okay, thanks.
Yeah. Okay. So I see no raised hands. So if there are no further questions, let's thank Ruchira once again for the talk.
Thank you.
Okay. Yeah. So Ruchira, you can stop sharing your screen. And Surajit, can you please share your screen? So the
Yeah,
next
I
talk
am
is by
good.
Surajit Bera, and he's going to talk about quantum to classical crossover in many body chaos using a specific model, which is the quantum spherical p-spin glass model. So Surajit,
Okay.
over to you.
So is the screen visible?
Yeah, screen is visible and you are audible. So
Okay,
please go
fine.
ahead.
Hello everyone. I am going to talk about this quantum to classical crossover in many body chaos in the quantum spherical p-spin glass model. So this is in collaboration with Lokesh and Sumilan. So first of all, what is chaos? So in a simple way, it is a sensitivity to initial condition. So you can think of a trajectory in the phase space, where the phase space the trajectory difference at time t diverges in exponentially with time with respect to this initial perturbation. So in recent year, also quantum Lyapunov exponent is also introduced. So which has actually emerges as an important tool for thermalization, ergodicity, and information scrambling. So this quantum Lyapunov exponent actually can be computed from this out of time order correlator, OTOC, which is nothing but a special kind of 4-point function. So there is a remarkable upper bound to this quantum chaos. Lambda L equal to 2 pi kBt by h bar, which is actually realized in this black hole, and also this model Sajdev Kitai model, SYK model. So now you can ask this interesting question, how does this Lyapunov exponent change from quantum to classical limit? And also, can this Lyapunov exponent break this bound in the h bar tends to 0, that is classical limit? And also, how chaos behave across phase transition? Can chaos be a tool to classify these quantum phases? So for this, we need a model where this h bar can be varied from quantum to classical limit. However, this SYK model, which actually realizes this quantum upper bound, actually would not work because it is actually fermionic model, so there is no classical limit. Um, we take this quantum spherical p-spin glass model. So here actually you can vary this quantum parameter h bar, and this classical limit h bar tends to 0 is very interesting. It describes actually supercooled liquid in structural gases. So actually, so the classical limit actually gives the so chaos in structural gas also. The model Hamiltonian is actually this second term, which is actually the interaction term, which describes the interaction among p-spin variable, and which actually coefficient is actually random and taken from Gaussian distribution. To have dynamics add actually the kinetic term, and the spin variable and its conjugate momentum follow the usual commutation relation. Also, there is a constant, the spin square equal to n. So you can think of as a particle moving on a surface of n-dimensional hypersphere with this potential. So to calculate the thermodynamic quantity, you need this free energy, and free energy is actually minus kBT log z. Here the overline actually denotes this disorder average, and so using this replicatic, which is actually log z, can be written of this limit 1 over n z to the power n. Then you actually can write down the imaginary time path integral for this z to the power n, which can be written in terms of this order parameter. Q is order parameter. So uh, so, uh, so the Swinger Dyson equation is actually this. This is the term free term where omega k square by gamma. So this gamma actually contains this actually quantum parameter h bar square by mj. And the self energy, actually we are talking for 3-spin interaction, for which the self energy actually the order parameter square. And in the paramagnetic phase, the order parameter is actually diagonal. On the other hand, the spin glass phase, actually there is also off diagonal term, which is actually Edward Anderson order parameter. So this is the phase diagram when the thermal fluctuation and quantum fluctuation is large. This belongs to paramagnetic phase, and when the fluctuation is actually small, it is actually ordered spin glass phase. Also in low temperature, there are actually two kinds of paramagnetic solution appears. Also there is a phase transition between spin glass and paramagnetic, which is actually first order. So now you can ask the questions like what is the Lyapunov exponent across these phases and phase transition, and also what is the classical limit of Lyapunov exponent, that is h bar tends to 0. So for this actually we to calculate the Lyapunov exponent, we need this actually OTOC, the out of time order correlator, which is actually the 4-point function of 4 spin variable with different time t1 t2, which are actually not time order, but you can make it actually contour order in this extended Swinger-Keldy's contour, where the two real-time branch is separated by beta by 4 imaginary time. And this is the diagrammatic for actually your order for OTOC, and this is a ladder diagram. So using this ladder diagram, and also you actually have to use this growth ansatz of the OTOC. So you can we can then calculate this Lyapunov exponent lambda L. So this is the result. So this is the Lyapunov exponent as a function of this quantum parameter h bar. As we see here, when the h bar actually large, the Lyapunov exponent is small compared to its classical value when h bar tends to 0. Also we observe that when T actually like 0.7 temperature, this blue curve, which is actually non-monotonic in the h bar. So also the T actually closes to the transition temperature, spin glass paramagnetic transition temperature. So it is observed that when the T is actually closes to this transition temperature, there is a non-monotonic behavior, and you can you can actually calculate also the Lyapunov exponent in supercooled liquid, which is actually like this, where this tail high temperature tail follow this activated form e to the minus gap divided by temperature. So this is a paramagnetic phase, and for calculating the Lyapunov exponent in OTOC, just it is like the paramagnetic calculation, but in the real time here you have to introduce the replicas. Here A and B as replicas. So this is like OTOC. Along with time, you have to introduce the replica in the real time. Again, the ladder diagram and under exponential growth and such, lambda L can be computed. So this is the result. Lyapunov exponent as a function of the quantum parameter h bar. So here actually we see that as quantum fluctuation increases, it helps actually to increase the chaos in the spin glass phase. So it is unlike the paramagnetic phase. In the paramagnetic phase, it is actually decaying, it decreases, but here it increases. And so the in the spin glass phase, the Lyapunov exponent in the supercooled liquid case is like this as a function of temperature. This low temperature tail actually follow some power law, T to the power alpha. So now what is the behavior of lambda L across the phase transition? So for this, we take this kind of cut. So this is a spin glass paramagnetic phase transition line, and we take this cut for some constant T and for some constant quantum parameter h bar. H bar tends to 0 and h bar equal to 1. So this is lambda L as a function of temperature for two values of actually this quantum parameter. One is h bar tends to 0 and another is h bar equal to 1. So this is actually the your transition temperature is here for these values of quantum parameter. So we see that at the transition temperature, lambda is finite, and actually after that there is a maximum of the Lyapunov exponent is appear. So similar behavior also you can plot as a lambda as a function of h bar. So cut along actually these and these for different temperature. Here also this is the transition temperature of the spin glass to paramagnetic for these two temperature. Also the similar behavior like the maximum of Lyapunov exponent appears after the transition h bar. So so to summarize, actually my talk is actually we have studied this crossover of Lyapunov exponent from quantum to classical limit, and the classical limit of the Lyapunov exponent gives the information scrambling in supercooled liquid in structural classes. So that is very valuable information. And also we observe that as I have shown earlier, the Lyapunov exponent can be non-monotonic in h bar, and it is the finite value in the classical limit in this model. Also, as I said earlier, this Lyapunov exponent is actually finite across the spin glass paramagnetic transition, unlike the thermodynamic quantity like susceptibility, which actually diverges in the phase transition. And also observe that a maximum of Lyapunov exponent actually appears close to spin glass paramagnetic transition. So, however, actually this model in the low temperature phase and does not saturate actually this chaos bound lambda equal to 2 pi kBT by h bar. So for future work, it will be need a model where you can tune the h bar. Also, the low temperature phases saturate the chaos bound. So that will be very interesting. So so we'll archive soon. So you can actually follow the details there. Thank you all for this short talk.
Yeah. So yeah. So many thanks for the very nice talk. So we'll take a few questions. So there are no questions. Okay. So if there are no questions, then let's thank Surjit once again for the very nice talk. Okay. And with this, we come to the end of this session. So let me thank all the speakers for the very nice series of talks, all of them. And then let me hand it back to the organizers, whom I should personally thank for organizing this very nice conference.
Hi Amit, thank you for sharing the session, and thanks all the speakers for nice talks. So we'll resume tomorrow at 9:15. As usual, the speakers and the chair are requested to join in 10-15 minutes earlier. So with that, let's close for today, and thanks Amit once again.
Yeah. Thank you.
Okay, see you guys.
Bye.